to do some demos, some live demos.
Perfect. Yeah. So Moez will be connecting with another Zoom link, I believe.
Yeah, you guys actually already put him in as a panel member, so I think he will come in. But him and George are together, so I guess they only need one connection.
Okay, great.
Yeah. All right, so we're set.
Perfect. Then I will start sharing my screen for the video.
And I will.
Oh, sharing yours, right?
No, he's going to share his.
Okay.
All right.
Yes, exactly.
Yeah, and I'll turn off I'll mute myself.
Can you see my screen, Livia, Elsa?
Yes.
Okay.
Yes, we can.
Great. So yeah, I also mute myself, and at 12, exactly 12 o'clock, I will click on the video. Well, actually, I need to share again my screen because I didn't share with audio.
David, can you test the click on play to test the audio? Can you hear me, David?
Okay, one moment, Moez. Elsa, Moez just called me that he's trying to log in, but he has problems to log in. Maybe you need to allow him to get into the room.
Okay, so once we start the webinar, he will access the room and then we will make him panelist, okay?
Okay. Moez, we're about to start. Once we kick off the webinar, then we'll try to put you into the room, okay? No, in 1 minute, we're starting. Okay, see you.
David, bueno, I will call Moez.
Yeah, better.
Just
yes.
Audio control. Just an audio check. Is it okay?
Yes. Yeah,
thank
that
you.
Works. No problem. Niels.
Yes, hello. Thank you.
Hello. Okay, 1 minute to go. David, I will click on the start webinar, okay? And then you can play the video. I hope the sound is okay. We didn't test it today.
Okay, great. Hello, good day, good evening, everyone, and welcome to the second day of the IAHR Young Professionals Online Congress. My name is David Ferras, and together with my colleague from the organizing committee, Livia Pitorak, we'll be chairing this opening session. We also have in this virtual room, Professor Mohamed Ghidaoui, who will give the keynote lecture of today. And also, Moez Loati will join to assist him on this, let me say, special keynote lecture. But before that, I would like to briefly go through the program that we have ahead today. So I will quickly share my screen to show the program. Please, Livia, let me know if you can see my screen. Can you confirm?
Yes,
Livia,
I can see your screen.
Okay,
Yes.
thank you. So yesterday we had quite an intense day. 35 posters were presented in 4 different technical sessions, which main theme was on hydroenvironment. Today the focus is on hydraulics. So the main focus is on the core business of the IAHR hydraulics division, with technical sessions such as experimental methods and instrumentation, fluid mechanics, fluvial hydraulics and reservoir sedimentation, hydraulic machinery and transient flows, hydraulic structures. We have ahead more than 40 presentations, 40 posters will be presented during the day. So again, it will be quite a long day, but also a very promising day. I wish, therefore, all the success to the presenters and also to the participants to enjoy their presentations and also to engage in the respective discussions. Said that, I would like now to pass the floor to my colleague Livia, who will introduce today's keynote lecture. So Livia, over to you.
Thank you, David. I'm going to introduce today's keynote speaker, Professor Mohamed Ghidaoui, who is a Chinese Estates Professor of Engineering and Chair Professor of the Department of Civil and Environmental Engineering at the Hong Kong University of Science and Technology. His general interests are in the fields of hydraulics, water resources, and environmental fluid mechanics. In particular, unsteady friction, turbulence in water hammer, and defect detection in pipes using transient waves. Currently, he is leading a large-scale theme-based project on smart urban water supply systems. He is the editor of the Journal of Hydraulic Research, the flagship journal of IAHR, and he served as an associate editor for 15 years. He received numerous awards for Best Paper, for Outstanding Faculty Award, as well as 2 Teaching Excellence Awards from the Hong Kong University of Science and Technology. First time I met Professor Ghidaoui was at the Pressure Surge Conference in Bordeaux in 2018, where he introduced me to the topic of time reversal of waves, which for me at the time as a young researcher was epiphanic. Today, Professor Ghidaoui is going to talk about time reversal of waves, an active area of research in engineering and physics over the past 3 decades, but not in hydraulics. His talk will provide the experimental and theoretical evidence of time reversal of waves in a variety of fields, introduce the basic physics of time reversal, and expose numerous potential time reversal-based applications in hydraulics. Have you ever thought about the fact that a spilled glass of milk has never been observed to spontaneously reverse course? Why waves are actually time reversible, but particle motion is not? Also, why dumping does not invalidate time reversal of waves? Such questions will be addressed in this talk today, so please welcome Professor Mohamed Ghidaoui.
Maybe Control L. Okay, can you hear me?
Yes.
Okay, thank you. Good morning, good day, good evening. Depends where you are. let me share my screen. I thank you, Livia. I thank you, David, and the rest of the organizing committee. It's really a pleasure to be with you. I was looking forward to it and preparing for this. So I enjoy talking about this subject. I enjoy talking about any subject I don't know much about. And in fact, I only started to look at this about 4 years ago or so. So I'm learning and we're all learning. So, but hopefully I know enough to excite you about this field. Moaz Alwati and George are downstairs in the lab. They will also do some demos for us. So I'll be flipping back and forth. So hopefully everything will be working well. I also here list some of the contributors to this talk. All right, and also some of the supporters. Now I'm trying to get, okay, my screen is already stuck. Sorry about this. We'll get it going. You always like to go to that one. Sorry, just give us a minute. High tech. Okay, well, I hope you can still hear me while Juliana is helping me fix this. So I'll take you through the content. What I really hope to do is first begin showing you some experimental evidence of time reversal, and then some theoretical support as to why it works. Then I will discuss the factors that challenge time reversal. And then I will share with you some applications. Some are in pipeline hydraulics. That's where I first start working on this, but I will also share with you some results on this in the general hydraulics field. And I would like to finish, if I have a bit of time, about kind of my thoughts on the future prospects for young professionals, which I think are very, very bright. So here's what I just, now, what is time reversal of waves? Let's first define it so we agree and we understand what we are talking about. So imagine you have a wave source. The wave source could be me now talking here and sending sound waves, or you're reaching it through electromagnetic waves. Yes. Okay, sorry. I'm being asked to be quiet. Valuable time. What happened? Is it okay?
Yeah.
No,
all right. Apparently we're back on, but this is stuck. I thought it was fine, no?
Okay, no, it's okay.
Now it's okay. Okay, so this is where we were. So now you have a wave. This wave is emanating. Nothing new here. There is no. This is the forward progress of waves. So let's imagine here you're doing some measurements on of the pressure. And what time reversal is you take your pressure measurements and you send it in the reverse chronological order, last in, first out. So what we do is we reverse the signal and then we send it back. And what the wave can do magically is actually retraces all its steps and finds its source. It will refocus on the source and the source only. Now, there is just one limit. The one limit is the refocus on size. You see the dot, that could be actually the actual source. What the wave refocuses as theoretically is lambda over 2, the wavelength over 2. But the wavelength over 2 is the wave speed divided by frequency. So if you want to refocus well, you need high frequency. And that's why you see in all of technology, they're going to megahertz, you know, in imaging, in medical imaging, it's ultrasound and so on, because with the F, it gives you higher and higher resolution. So now for us, the source could be, for example, the tsunami source. It could be a burst in a pipe. It could be rogue waves. In a medical field, it could be a kidney stone. All right, so these are the sources that we like to discover. But the question we still have is, does it work? Is there evidence of this? So I'll show you here an experiment. So you're going to see now first the forward wave, a stone coming down from the ceiling. The waves are emanating. And what they are doing here is they are measuring the pressure on the right-hand side. Essentially, they are measuring the water height. Okay, they are not measuring everywhere, just on the right-hand side. So they're measuring the head, and now they're going to reverse it, meaning whatever they measure, they're going to send it back into the pond. So this is the time reversal stage. Now we're speeding it up, and you will see what will happen at the end. It's actually a cool result. The waves will find where the stone was dropped. You see the wave coming back? There it is. And it's actually here. That's where the location of the stone. So if I didn't know that, the wave will find it for me. So everything reverses. The only thing that does not is, of course, the stone does not come back up. And that has to do with the particles. And hopefully, particle mechanics is not reversible. And hopefully become a bit clear later as to why. The other thing that I want you to notice, when we started with a very flat tank. But now there is a reversal, but you see some ripples. These ripples are what we call side lobes. Why they are there is because we did not, if to get rid of them, you either have to measure around the basin or you have to measure in a longer time. Essentially, we did not reverse the whole energy. We did not reverse the full energy of the wave. And that's why, so these are always artifacts of imaging. Okay, here is another experiment. This is again a cool one where they show the Eiffel Tower. So now this is dropped in a channel. This is also on a water channel. So the source was an Eiffel Tower shape. That's the forward. Now you're going to see the reversal. So they're going to reverse it and you're going to get the image of the Eiffel Tower in a channel. Okay, next to it is the smiley face. Okay, so again, the source with a smiley, and that's the forward. Now they're going to reverse this, and you're going to see the smiley face come back up. And that's in a hydraulics application. That's a gravitational waves, what you're looking at. This one here, let me see. Oops, sorry. Okay, this is acoustic waves in a room. So again, what they're measuring is they're measuring here where these dots are. Okay, so that's where they got the measurements, and then they want to reverse them. So you'll see the reverse stage. Now it's going to be the reverse stage. And you will, again, you see what happens is that the waves will refocus back at the source. So we showed it works for gravitational waves, it works for acoustic waves. Actually, one of the videos I skipped because we're trying to save time is electromagnetic waves are also type reversible. This is one of the early experiments that was done in the ocean. Actually, they've done these experiments over in the Mediterranean Ocean over 30 kilometers. You see here the wave source, acoustic wave. They measured that these locations here 30 kilometers away. They reverse it and the wave refocuses back at its original location. So now that became a very high technology in environmental application, in ocean acoustics, in wireless communication in the ocean and so on. Now I'll skip again a couple of videos, unfortunately. Here is also for elastic waves, because especially when we're looking at pipes, we need to make sure it's reversible on the wall and it's reversible on the fluid. So elastic waves are also reversible. So what you're going to see now, you see there, we're going to send a wave and it's going to be received at where the arrow is. And that's the signal that got received here. So remember, it was sent from this soldier to this point. Now they're going to reverse the wave. So when you reverse it, it's sending back stress waves. And what happens, because the stress only focuses on the guy who sent it out and the guy falls down. And it's showing you all the other ones are stable. Sorry, let me again. Okay, let me play this again because I think it's also nice. It shows you some visual. Okay, there is another video here. So now the middle soldier, they send in waves. Then we reverse the waves at them and watch. Okay, all the other ones. So the stress focuses back. That's now one of the early applications for this was actually for kidney stone. So now it's a technology used for kidney stone. So what they do with the kidney stone is they send a test wave, a small amplitude wave. You get the reflection. Once you get the reflection, then you time reverse it because the stone will send back the highest reflection. You time reverse that and you put a lot of energy. And with time reversal, like I just showed you, it focuses on the soldier, right? And the rest becomes intact. Well, it does the same for the kidney stone. The energy will go and destroy the kidney stone and leaves everything else intact. Okay. Now, when we kind of saw this about 4 years ago, we start to think maybe this could be really our answer for trying to do defect detection on pipes. So we could send the source of a wave. There may be leaks, blockages, wall thinning, and so on, because all of these defects are sources of waves. So the idea was we can time reverse it and then study that process, and we should be able to localize and identify all these defects. First, again, we had to prove it because seeing is believing. So we needed to do the experimental setup for numerically initially. So we send a high frequency wave here. High frequency means we're going to excite longitudinal and radial waves because the waves radially are of the same size as the pipe diameter. Now we're going to take it. So that's the dispersed wave. So you see you have three packets because there are three modes. So we're going to reverse these and send them into the pipe from X 25 meters. And if all goes well, they should only refocus at the dot, which they do. Now, what happens here? There are three modes. We excited radial modes. So let me give you a sketch of what's happening. We have three modes. One is the plane modes. The red one goes directly. The other one zigzags. Some of these modes go laterally. So you could see they arrive at different times towards the end because one is faster, then there is a second, then there is the slowest. It's still in the pipe. This is what you call echoes. This is when you go and speak in a tunnel, you hear your echoes. So those are the echoes, is slows. You get all these modes that are, some are faster, some are slower. You get a multipath effect. So when we time reverse, essentially, we're sending the slowest first, the second slowest second, and the fastest last. This is like having three runners. You send them out, you receive them after 100 meters. The person who arrives first, you say, okay, you hold them back. The second person, the last person, you send the last person first, and then you send the second, and then the first, and hopefully by the end, they will meet at the very end because you handicap them. And that's what's happening here. We're sending the slowest first. Okay, that's really what time reversal does. Okay, then the second slowest, the blue, and then the red is direct, and then they all constructively interfere. So now we're back to talking the language of waves. The waves only constructively interfere at their source. Now, this was the numerical proof when I presented this a couple of years ago, as you said, in France. Then I challenged our group, and both of them are downstairs now. They're going to show us a live demo of what has been done in the lab to experimentally verify this. So I'm going to send you down to George, and hopefully everything will work. George.
Hello, everyone, and welcome to the Hydraulics Lab at SKUST. My name is George, and I'm a PhD student. Is that okay? Sorry, I don't have backup from the voice, but is that okay, Moez? Should I? Okay. So I'm George, and I'm a PhD student under the supervision of Professor Ghidaoui. And you've probably seen a few demonstrations of time reversal in video. but now we'll do a real demonstration, a live demonstration straight from the lab. And for that reason, we will do time reversal of pressure waves in water supply pipes. The setup is right in front of me. It comprises of 2 tanks at the ends filled with water, and they're connected with a set of different pipes. The length of the pipes is 6.5 meters. And we have an HDPE pipe, a copper pipe, another HDPE pipe with a junction, and a clear acrylic pipe. Now you see that in time reversal, we have a source and a receiver. For our example, our source and receiver are the same transducer. It's a hydrophone, pretty much like this one I'm holding right now, and it's mounted in the pipe using a magnetic base. Today, we'll use the clear acrylic pipe just to be able to visualize better the location of the source and the receiver. So this is the pipe we will use. And one transducer is here, and that will be our receiver for the forward test. And 2 meters away, there's another transducer over here that we will use to send our pressure signal. Now, we also have a pump to circulate the water, and currently there's flow in the pipe. The flow rate is about 3 liters per second. So, and the Reynolds number is about 40,000. So the flow is turbulent. So we'll try time reversal with viscous damping due to the fluid and the pipe wall. So let me go ahead to the computer, and I hope please change the screen to the computer so you can see what I'm seeing. So we have a software to define the pulse. So we will send a high frequency pulse, and by saying high frequency, we refer to signals with wavelengths comparable to the cross-sectional dimensions of the pipe, the pipe diameter, that is. So let me go ahead and do the forward test. Again, we will send a small pulse from the source that will travel along the pipe and will be recorded at the receiver. Now, if you can see my screen, you'll see 2 waveforms, one in red and one in white. The one in red is what we actually send, is our source. It's a Gaussian modulated sine pulse. And what you see in white is the response at the receiver. You see that it has nothing to do with what we send, but it's a dispersed signal that comprises of many wave packets. That's because the different modes that propagate out of the pipe and arrive at the receiver at different times. And according to the time reversal methodology, we will take this response of the pipe, flip it in time, and we will use this transducer here to send back our pulse and record it at the location of the original source and see what we get. According to the previous examples, the pulse must refocus. So let's do that. Let me just set up the equipment. And of course, I will have to change the transducers, so I have to change the cables as well. Just bear with me for a second. Also, I forgot to tell you, the pulse is quite short. It's 5 milliseconds in duration. So you see that wave propagation happened really, really fast. So now I'm ready, and I will do the time reversal stage. So the time reversal stage is complete. It's quite fast, as I said already. So what do we have here? If you can see the screen, you see again the 2 pulses, the one in red and the one in white. The one in red is our time reversal source, is what we send from this location right now. And you see that if you recall the forward propagation test, this is just a flipped waveform of the original response. So that's what we sent. And 2 meters away, we have the receiver that was the original source. And you see that the original pulse is not perfectly, but recreated. You'll see that we have also those side lobes. It's pretty much like the ripples in the tank that Professor Ghidaoui showed you earlier. You have some ripples. It's not perfect because we did not time reverse everything, but only like a point in the cross section of the pipe. So the time reversal is imperfect. However, I might tell you it's really important to say that it's not only feasible in the 6.5 meters range, but we also did the same test in a much larger scale, in a field setup of almost 40 meters. And Professor Ghidaoui will now show you the results we got from that setup. Thank you very much.
Okay, thank you, George. And I'll get this. Yeah, it's okay. So George showed you, because in the lab, we're in Hong Kong, we don't really have lots of space, but luckily we were able to get from water supply some space outside, and we managed to test this over 40 meters long. And so this is the blue is the wave source. Again, it's a wave packet. What we receive is a dispersed wave, like what George showed you in the lab there. We're gonna time reverse it and then send it back. And what you see, again, the wave refocus, albeit what George just mentioned, the two side lobes. So what you see here, the male lobe is exactly the analog of what you've seen in the tank where the stone was dropped. These ripples here are the same as these side lobes. To get rid of the side lobes, we either need to measure longer or measure at more points. Okay, so this is, then we went down to the field, and this is one of our early experiments in the field. So we 400 meters long, we put a burst. We mimicked a burst that sends two waves. The two waves are measured on either side, and that's what you see. And then we time reversed the signal, okay? We time reverse it and send it back from the two ends. And you will see that the wave refocus at the source again. So that means if this was a real burst, and if we happen to be measuring, we could in a fraction of a second reverse it and tell you where your burst is. Okay, that's what this, for example, an immediate, and we'll show you an example application of that. What's the theory behind this? So now imagine you send a pulse, a delta function at this location XS. Of course, if you solve the delta function, what you're measuring really is the Green's function, the GT at XS. What we do is we reverse what we measured. When we reverse it, and then we send it again. When you send it again, mathematically, we're doing the convolution. So you're reversing G minus T, and you're convolve it with the Green's function. If you do the math, this is the integral you get from it. If you know a bit about your inner product of function, this integral can only be maximum when T is equal to 0. What is T equal to 0? That's actually your source time. That's why the wave only refocuses at the location at the right time and at the right location of its source. So there is only constructive interference at T equal to 0 and XS. But what are the factors? Are you still wondering what are the factors that could destroy, that could maybe challenge? There are two main things, stability and damping. What is stability? Stability has to do with perturbing. And we know perturbation, in our case, there is a lot. We're measuring a signal, we're reversing it. Where we measure, we make errors. The model could have errors and so on. So we are perturbing those initial conditions when we send them again. And here on the left-hand side is a wave that was sent through a bundle of steel, random steel bars, randomly located steel bars, 2,000 of them, and then it's received on the right-hand side. Then it's reversed. And when you reverse again, you get the wave packet. So the perturbation did not seem to destroy the wave refocusing. In fact, theoretical work has shown that perturbation only grow as square root of time. But we are looking at waves. Waves are very fast. So the time, like George was telling you, 5 milliseconds. Square root of that is a very small error. Particles, why we don't see our milk coming back to, when we spill it, coming back to our bowl, is because it's made out of particle. Why the stone didn't come back? When here is an experiment that was done, there is again scatter. They send particles from this point, and then they measure their speed here, and then they reverse the speed. And what you see when they reverse the speed is there is only very few of the particles go back. All the other particles are everywhere. if time reversal of a particle worked, they should all collect here, but they don't. They are everywhere. So why is that? Why is that? Is chaos. Two particles close to one another, small perturbation, the errors grow between them exponentially. Waves, they only grow as square root of time. This is a nice video that I found that actually illustrates this. So here is the same video left to right. The only difference is the red particles has been displaced by 1 pixel. Okay, there is, and now you're going to watch the dynamics of particles. So with 1 pixel, notice the left and the right, the particle was only again 1 pixel displaced, but it's already now, if you look at the left video and the right video, the location of the red particles is nowhere close. Its trajectory becomes very, very different, okay, because of its high sensitivity to initial conditions. So in fact, now you can see, okay, they're going to show you actually the path of the particle. This is not my video. Okay, so now the two particles, they start together, okay, but with a small error. Initially, they are together, but very quickly, exponentially depart from one another. With waves, that error is only square root of time. Now, the other factor is, of course, damping. Here is the full wave equation. What we do here is we take the full Navier-Stokes equation. We don't neglect anything, and we write the wave equation for it. The only term when we reverse the time, the only term that's not reversible is the shear stresses, of course. Notice that the nonlinear terms are reversible because each velocity gets a minus v, but we have a v squared. V minus v, it restores it. So the nonlinear effects are reversible. So the only non-reversibility comes from the damping due to the viscous stress. And here, if we're looking at the pipe wall or any solid material, is due to the viscoelasticity. So now, whether damping acts or not, we need to look at the ratio of the damping term to the inertial term. And we call this the time reversal parameter. So the time reversal parameter due to friction, the time reversal parameter due to damping in the pipe wall. As long as those are much smaller than 1, reversibility is not going to be affected. So for all of the experiments that we've shown you, the time reversal, what George had showed you, actually the time reversal parameter is 10 to the minus 2, 0.01. In fact, for the range of parameters that we have on pipelines, the range with this time reversal could be anywhere from the tens to hundreds of kilometers. Okay, you could reverse these waves. This is not surprising for low frequency because we know that whales communicate over 6,000 kilometers. So these waves at low frequency do travel large distance. In fact, we did this for a pipeline. We did all the tests, testing the steady friction and steady friction, the viscoelastic damping. And you could see when you put viscoelastic damping at low frequency, we don't lose, we lose some of the amplitude, but we still get the correct refocusing. But friction, the viscous damping due to the fluid, does not do anything. Okay, in the time scale we're interested in. Okay, let me skip this. Now, of course, I just shown you everything ideal, but in reality, we have errors. We have measurement noise. So now imagine again, we have a source A, we have a media here, which is unknown. I'm talking media here because it could be a pipeline, it could be your ocean. And I'll show you an example. It could be in the atmosphere. There are applications of this in the atmosphere. There is medical applications of these. So there are unknown parameters. So you send your waves, there are unknown parameters, you measure the response, which is a pressure versus frequency. So theoretically, we know that your measured pressure should be your theoretical pressure plus noise. What we do is we can multiply by the phase conjugate. Why phase conjugate? Because time reversal, theoretically, time reversal in time domain, when you go to the frequency domain, it becomes phase conjugation. So what we show actually at the end of it is this expression here, which has the measured and the theoretical pressures. And this is the power, essentially, the maximum power of the signal, and it only peaks at your parameters. So we're looking for, this is where the wave will refocus. So at least we can show here that also noise does not destroy time reversal. Now, this became one of our early applications was to look at it for defect detection on pipeline. So again, I throw you back to Muaz in the lab, who will show us some examples of doing this in locating leaks in a pipeline. Okay, Muaz.
Okay, so welcome everyone. So now I'm gonna present to you the low frequency facility. So the system here consists of 145 meter long pipeline. It's a 3-inch diameter and it's made of HDPE. You can see the layout is coiled around the lab. That's because there is not much space, so we have to go around. At the upstream, we have a pump. It's a booster pump, so we can control the pressure. And at the downstream, we have a valve that is at this moment open. So we can have a simulated leak anywhere along the pipe, but today we decided to have it around here, which is around 98 meters away from the downstream boundary. So how this test is conducted, we will have 2 measurement points. One is at the downstream, one is at the upstream locations. And what we will do is basically generate the wave by closing suddenly this ball valve, and the wave will be generated and propagating along the pipe. As soon as it meets the leak, the wave will send a reflection that we can have it embedded in the signal that we will download, and then the algorithm will automatically run and give us the prediction of the leak locations. So now at this moment, you can see in the screen that there is a steady state and there is some pressure fluctuations. Some of these pressure fluctuations are due to the noise coming from the equipment or maybe coming from the flow. But at this moment, the pressure is steady. So here you follow me, I'm going to the downstream valve. Now here you can see this is the valve that we have now open. And what I'm going to do, I'm just going to close this valve suddenly so that the wave starts to generate along the pipe. So I'm counting to 3 and then I close the valve, and you possibly can hear the sound of water hammer. So 1, 2, 3. The valve is closed. The screen is probably showing you some pressure fluctuations. These are due to the wave bouncing back and forth from the pipe ends. And once it reaches, again, the steady state because of the damping and the friction that we have in the pipe, then we are ready to stop our measurements. It only takes a few seconds and we collect our data. Now the data is downloaded. We run the algorithm. The algorithms actually computes 3 different inverse methods. One is time reversal, area reconstruction, and MFP. That will give us the prediction. It takes only a few seconds to do the computations. And now the estimation will appear. We will see the layout of the pipe here in the other screen. And you can see that the prediction is given in pink. The correct location is in pink, about 98 meters. The other colors indicates the estimations. So you can see the estimations has an error about 1 to 3 meters, which is acceptable because the wavelength that we have generated is about 5 to 10 meters. Even if we repeat the test again, the error will change slightly, but will remain within the wavelength of the wave that we generated. So this is, we have already implemented this, and we have, of course, applied it in other locations in Hong Kong, but we have a fully implemented this smart urban water supply system here on the campus. So what we did, we modified some of the locations in the water supply system of the campus. In the screen, you are seeing some of these access points. You can see the box where we have the data acquisition system, the GPS locations, and the remote control for the valves. These are some other locations. We have about 4 locations. Some other locations around the campus have been implemented. Some of them are also implemented with a solar system because some of the water supply transmission lines have no electricity. So we have to get the full technology running with solar systems. Everything is run remotely through a web app. We just connect to a web app, and then we can control all the transducers and the electrovalves to generate the waves. We have a passive testing where we can detect some burst or abnormality that occurs in the system, as well as running some active tests where we can generate waves actively and collect the data and use which methods we want to use to determine the leak if there is a defect or if there is a leak or anything. So this is in general what we've been doing. Thank you for listening. I'll pass it back now to Mohamed if you would like to comment more about this. Thank you for listening.
Yeah.
Thank you.
Thanks, Moaz. Okay, let's. All right, we get. Are we on? Yeah, we're here. Okay. All right. So Moaz showed you what has been done in the lab. We're also doing this on campus. We actually tried this in the field in a number of places. Time is pressing. I cannot show you all, but we tested in Hong Kong. We tested in Italy. So I'll show you one test in Hong Kong here in the real water supply system where we applied time reversal. And the output of it is I'm going to show you. So this is actually an aerial picture of where we tested. So it's, again, not a leak detection. It actually tells you all kinds of whatever discontinuity you have in your pipeline. So we find, of course, things we already know. So there is a consumer connection that shows up in the time reversal. But also new things showed up, actually new things that were not even in the map. We knew from the time reversal something was happening here. After checking with water supplies, they said, oh yeah, there is a hydrant line, which they didn't tell us about. A simulated leak was found. Here is also PRV. An interesting thing is they told us the PRV was offline, but our time reversal was telling us something was dynamic, and we knew it was back on. So after a couple of phone calls, they in fact did confirm that the dynamic device was on. So it finds all of these changes that could happen to the system. Here is another test that we've done in Yulong in Hong Kong, and we reckon there are 2 leaks, and they are now preparing to confirm them. So we've done also in Italy and Milan, okay, successful. So I'll skip through those. I'll show you here. This is an interesting one. This is, let me run first. Sorry, what happened? So here again, what they had here was 2 measurements of those 2 sensors. So, okay, let me stop it here. So they were measuring at 2 sensors, and each day at 4 o'clock in the afternoon, they were seeing a drop in pressure, and they didn't know where that drop in pressure was coming from. So when we got these data, we ran the time reversal, and you could see, at least according to the time reversal, the wave peaks here. So whatever is happening must be there. And in fact, it turned out that's where it was. And what it was is actually at 4 o'clock each day, or around 4, there is a tanker that comes and actually fills up, and that's what they were seeing. So again, this is what I told you earlier. When you're doing this, you could actually bursts or whatever changes in the system. So as long as you keep measuring. Incidentally, there were a trial by other groups that failed to determine this. This is just showing you here, if you go to high frequency, remember I told you resolution equal higher frequency equal better resolution. This is now we're doing at the kilohertz. At the kilohertz, we could actually identify leaks, and we could identify also the presence of the support. You could also identify the presence of a junction. We also put a magnet inside the pipe, and you could find the magnet. We also put here, there is some bitumen lining that I actually took from the water supplies department. We tested, and you can actually localize it. Now, let me skip through a couple of these. Moaz just showed you this one. Maybe I'll show you this one. This is a recent one. This is sewer application. We have pumped sewage in Hong Kong, and we tested in it. In fact, there was a real leak. And here is in this project, a real leak that was actually found, okay, and detected, okay, just recently. Now I'll take you to a couple of other, these are some other applications that are starting to come out that are near the hydraulics field. A recent paper in Journal of Fluid Mechanics by Fink here, and others. Fink is one of the fathers of this area of time reversal. And what they want to do is understand rogue waves, what is also called the New Year wave in 1995 in the North Sea. That wave was close to 25 meters high. We want to try to understand it. So one of the ways they did it here was to actually then simulate the rogue wave, okay, using Froude number scaling, sending it in a channel, a gravitational wave. They measure then at a bunch of these locations. They take what they measured and they time reverse it. And when you time reverse it, you actually create the rogue wave. So if you are measuring, therefore, in the ocean, and you pick up this signal, you time reverse them, and you could actually tells you where these rogue waves are. But if you do them in the lab, they could actually highlight for you, and you understand better these rogue waves. And that's one of the aims for what is being done in these type of works. Here is there is a paper, not by us, again, by others, who looked at creating the tsunami source. Again, we usually have measurement of tsunami, but it's very difficult to understand what is the actual source when you try to simulate it. And time reversal allows you to walk your way back. So there is works that are doing time reversal like this one in the hydrodynamics. Okay, so because they were measuring at lots of these green points. And what they did is they time reversed it. And when they time reverse, it reconstructs back what the source should look like from a hydrodynamic perspective. Incidentally, people in geophysics have been doing this on ground motion. So they did also in Japan. They send back they did time reversal of the gravity of the elastic waves, and that tells them about how the Earth might have moved to create the tsunamis. These are tests that are, this is a paper again, I think it's recent, well, maybe 20 years ago, using time reversal to try to determine the parameter of a sediment, its thickness, its density, and the wave speed in it, okay? Here next to it is actually time reversal done in the atmosphere, because what people are doing now is they're saying, listen to the atmosphere. And one way, the wave speed, acoustic wave speed depends a lot on temperature. So by doing time reversal, you determine automatically the speed profiles. And by knowing the speed of the wave profiles, you actually can determine the temperature fields. So there is all kinds of environmental applications that are being done in this. So I'm started to race through this because I want to get to the end. I would like to mention that this area is actually open and fully open. I think there is a lot that we could exploit in the hydraulic fields. In fact, we're writing a vision paper on this, and hopefully will come out soon for all of you to read. But since I'm talking about two young professionals, we're talking about the prospects. Let me switch tactics at the end, maybe take 2 or 3 minutes, and tell you, at least from my perspective, what are the prospects. And I would say we have an hydraulic engineer, we have a proud past, but you have a bright future ahead of you. So let's first look at our past. We don't need to look very far. You look at water supply, you look at the drainage, flood protection, irrigation, hydropower, and so on. All of these are creation of the people before you, and you have been also contributing yourself. In fact, the medical journal, the British Medical Journal, sent a survey to medical people, not engineers, asking them what was the greatest health advancement in the past 150 years. And it was not any of the Nobel Prize winning, it was actually water supply and sanitation. Okay, water supply and sanitation also, which is part of our field, hydraulics, featured as the greatest, one of the top 20 greatest achievement of the last centuries. Of course, you also know about the iconic projects and structure like the Panama Canal, the Hoover Dam, the Three Gorges, and I think the video that David showed at the beginning has a lot more. Another interesting one that actually came across about a year ago is actually finite difference was created in the connection with hydraulics. This is when Richardson was asked to design a channel canal to drain a marsh. And what he ended up doing is writing a difference equation. But of course, with the different equation, you need a lots of calculation. So he needed to hire lots of boys, young boys, and each one of them had to do, they sit in a room and each one of them had to do a little node by node, and then they talk to one another. And he called them the computer. And this was before the computer age. So they were really doing parallel computing before the computer age. So now for you, you have huge challenges facing you, water security, global warming, floods, sustainability. All of these need advances in hydraulic engineering, but all of these also bring opportunities. And one of the opportunities that I think are very, very important is data. You hear about big data. Hydraulic engineering is actually based on data. It's a data-driven field. It's not new to us. Data might be new to computer scientists, but it should not be new to us. So we should not be scared of it. We should actually be leading these fields. What is new, though, is the availability, the ability with today's sensors to measure at different scales. But that's an opportunity. You can measure now at far, far more variability of different length and time scales. So we can understand things far better. You also have lots of these mathematical tools now that has been developed and that takes this data and extract information from it and throw away or squeeze out the noise from it. I'm receiving, though, I need to send a warning here. I'm start to receive some papers on AI on hydraulics, which, although I encourage, what puzzles me is that they seem to rely on data only. And rely in a field like ours, why would you throw away what we built over thousands of years in terms of physics and data? We should keep that. We should add the data to what we learn. We should not throw away the physics and rely on data. I'll give you an example of where you can go wrong with that. In fact, recently we're just playing with this for waves. So on the left-hand side, you see the exact of wave propagation. In the middle, we see data and physics, meaning we blend them together. In the right-hand side, we said, okay, let's do away with the physics. And when you do away with the physics, you get nonsense. So it is very dangerous and it is not advisable. Also, don't follow big data people blindly because they can collect big data. We don't have the luxury to collect big data. Maybe we can collect more, but we will never be able to collect big data. So to compensate for that, luckily we have physics. We have all the experimental equation that we derived over many years that we should keep with us. Now, just as a final, this is what I believe the way research progresses. So this is a progress in the vertical axis, investment on the right-hand side. It could be time investment, money investment, effort, etc. I believe that now in the hydraulics field, we are here in the red curve and we are plateauing. I believe, though, with all the problems, all the challenges we have, and with all the opportunities that we have in terms of big data, in terms of all the mathematical tools that has been developed, with all of our past knowledge, you can be the pioneers. But to be the pioneers, to enter big data, and to take advantage of it and be one of the pioneers, you need to go back and learn more, the fundamentals even more. The more data you have, I believe, the more fundamentals you need so that you could separate noise from real structures in fluids. So I wish you the best. I think you are in the right place. I think you could be in this curve, but you need to focus more as young persons in your fundamentals, your mathematics, and take advantage of what's available out there. Thank you very much.
Thank you very much, Professor Ghidaoui, for this very enlightening keynote lecture on time reversal of waves. It's very interesting not to get to know better the theory behind and also its applicability. Also, it's great to see this in this lab demonstration. So also thank you very much to Moez and George for that. Okay, we have maybe time for at least one or two questions.
Mhm.
I believe the first asking a question was Camille in the chat box, and we moved his question in the Q&A. So Camille Urbanovic asked on one of the early slides, probably the slide number 14, we've seen movement of 3 modes. My question is, what is the role of other modes? How many of them we have during our pipe flow?
Sorry, what's the role
of other modes? Because in this slide, you are showing 3 modes. And Camille is wondering if there are other modes and which is the role of these other modes.
Yeah, okay. With the frequency we send, I think this one, the frequency, the central frequency we send was about 20 kilohertz, I believe. And with that 20 kilohertz and the size of the pipe, we are able to excite 3 modes. Of course, when we go to higher and higher frequency, we tested, I think, up to about 100 kilohertz, and you could excite more. So you could have 4 or 5. So what happens, of course, with more and more modes or higher and higher frequency, you get better resolution. But with higher frequency, the damping becomes also larger. So you lose some of the range. So you can get higher modes, and which effectively you're getting better resolution, but you're losing the range. So you have to optimize when we do this in practice. And we believe that for us, it's sufficient around 50 kilohertz, at least for the pipeline applications. You could localize things to within 1 meter with about 50 kilohertz.
Okay, thank you very much. We've had several more questions. Unfortunately, we cannot go through them because time is pressing us. We need to move to the next session. I also have questions myself, no, because at the second slide, I believe you mentioned that one of the applications is in kidney stones, and I suffer myself from kidney stones. But yeah, I will keep my questions for the IAHR World Congress. So hopefully we can meet some of us there and continue with this discussion. So yeah, again, it's been a great pleasure, Professor Ghidaoui, to have this, to enjoy this lecture. And yeah, I hope it was the same for all the participants. And we need to close the session now, and in a couple of minutes, we continue with the first technical session on experimental methods and instrumentation. See you there.
Right.
Bye-bye.
Thank you very much. Thank you. So we need to...
David, good morning.
Hello, good morning, good afternoon, everyone, depending wherever you are connected. So it's my pleasure to welcome you to the first technical session of the second day of the Young Professionals Online Congress. So this technical session is on experimental methods and instrumentation. And I would like now to pass the floor to the chairs of this session, which is Rui Ferreira from Lisbon University and Sandra Suarez from Leuven University. But before that, let me remind the participants that if you have any question, any concern, you can use the Q&A. Okay, so with no further ado, Rui and Sandra, please, you can go ahead. The floor is yours. Thank you.
Hello, good morning. We have, I believe, very little to add. It's a pleasure to be here. This is a session about experimental methods, instrumentation. There are several applications of instruments and techniques to measure across all the spectrum of work in the IAHR. So it is a pleasure for us to listen to your novelties, and you are, of course, the future of IAHR. It's a pleasure for us to see the link between what we've been doing before and the envisaged new things that are to come. Sandra, perhaps you want to say some words as well? Or, yeah.
Okay, so hello to everybody. Hello to all the young professionals who are going to present. We are looking forward for a presentation, so I suggest we don't take much more time now when we start with the first presenter, who can, I think, share his screen with Joris Hahn from and co-author, but I guess this is Joris who is going to present.
As host, I'm the one sharing the screen, so the speaker, okay, in this case Joris, can go ahead with his presentation.
You have 6 minutes. These are posted sessions of about 6 minutes. This is general for all presentations then. Thank you.
Okay, thank you. Good afternoon, everybody. So I'm going to present an experimental setup and a computational model used to characterize the performance of large centrifugal pumps commonly used in waterways. So these are pumps able to deliver discharges of the order of 300 liters per second and reaching a power of the order of 300 kilowatts. Improving the selection and the operation of such large pumps offers opportunities for reducing greenhouse gas emissions due to waterways. So figure 1 illustrates the method used to carry out this study. The aim of the numerical model is to mimic the steady state operation of a pump for a given configuration, which constitutes the inputs of the model. So by this, I mean the power applied to the motor. So it is the voltage and the frequency, the head losses in the pipes, and the useful head difference. So this model has a number of coefficients that allow it to be adapted for a wide range of pumps. Thereby, it is necessary to identify for each pump individually those coefficients through a calibration phase that use optimization technique. In order to carry out this study, it was necessary to build an experimental test bench in order to test these pumps at several rotation speeds, for which the flow rates, the heads, and the electric powers were recorded. So figure 2 shows a computer-aided design of the pump test bench where the pumps were tested. So the test rig operates in a closed circuit. Water is pumped from the tank by the submersible pump or by a dry action pump. and the water flows through a flow meter and a regulating valve that generates the desired pressure drop. Then the water returns back to the tank. So the tank is remarkable by its size. Yes, so the tank is remarkable by its size. It is 3 meters in diameter and 4.5 meters in height. It was installed outside next to our hydraulic lab. So figure 3 shows the results of the calibration for an Amarex KRT pump, which operates on real-world waterways of the utility waterways island. So you can see the pump curves on figure 3A for several frequencies. So the stars corresponds to the measurement, while the triangles are the model outcomes for the same inputs. So figure B represents the total efficiency. And on the 51 measuring points, the root mean square error on the flow rate is calculated as 9% of the grate value, on the electric power as 3%, and on the total efficiency as 2%. For the detail of these errors, you can see the detail on the figure 3C for each frequency separately. So in the end, we get a mapping of the pump performance for a broad range of operation conditions in figure 3D. So the value of this combined experimental and numerical characterization of the pumps is to provide the pump operator a full characterization of the pump performance well beyond the nominal conditions, which are usually reported by manufacturer. It helps the pump operator assessing also the loss of pump efficiency when it operated in real world configuration differing from the nominal ones. And repeating periodically this characterization enables also assessing the effect of pump aging on the performance. So finally, we are working on a small software that allows pump users to obtain these operating values of their pump for different configuration by calculation. Thank you for your attention.
Thank you. Thank you for keeping in time as well. I believe we should move to the next presenter, which is probably Nime Maruf. Yeah, Nime Maruf from University of Aberdeen, speaking about their work on noise-free stereoscopic particle image flowsimetry. So please, floor is yours.
Hi, so my name is Nishme Maruf, and today I will be talking about noise-free stereoscopic particle image velocimetry, or PIV. As you know, PIV is a very widely used technique for measuring instantaneous velocity and turbulence statistics across a broad range of applications. However, measurement uncertainties still prevail, especially in highly complex three-dimensional flows. Our study aims to assess the use of redundant velocity estimates to significantly reduce error contribution to second-order velocity statistics by generating and analyzing synthetic PIV images. The theory of this approach is that when decomposing instantaneous displacement fluctuation estimates into the sum of actual displacement fluctuations and fluctuating error or noise, the displacement covariance of two redundant measurements may be decomposed as shown in equations 1 and 2, where the terms delta XA epsilon 1 and delta XA epsilon 2 tend to 0 if fluctuating error is not correlated with displacement fluctuations, as earlier tests by Cameron et al. 2013 suggest is likely the case in typical measurement conditions. This leaves the noise covariance epsilon1, epsilon2 as the sole remaining source of noise, for which a correlation coefficient C epsilon1, epsilon2 may be defined, such that C epsilon1, epsilon2 equals 0 indicates a near noise-free estimate, and C epsilon1, epsilon2 equals 1 indicates no noise reduction. Hence, in this study, a series of cases have been designed where the relationship between PIV image parameters and C epsilon1, epsilon2 may be investigated. This investigation has been carried out using synthetic PIV images generated from randomly distributed particles following prescribed motions. As such, the imposed displacement and measured displacement are both known, and the fluctuating error may be calculated as the difference between the two. In these synthetic images, image conditions are defined by the user, including displacement field, relative stereoscopic camera angle as defined in figure 1a, particle image diameter, light sheet thickness, particle image concentration, and the standard deviation of additive random image noise. We propose that the total measurement noise may be decomposed into 4 main contributions, including aliasing error associated with undersampling of PIV images, change of brightness error associated with out-of-plane displacements, camera noise error associated with the random component of pixel brightness due to camera thermal effects, and gradient error related to the uncertainty associated with each particle within a sample volume having a different displacement. We generated a set of simulations for the steady state condition to isolate each error and calculated C epsilon1, epsilon2 for each case. To demonstrate the concept, the error correlation coefficient as a function of relative stereoscopic camera angle for cases with a large out-of-plane displacement relative to light sheet thickness is shown. To isolate change of brightness errors, the other displacement components were kept as 0, as was additive random noise, and particle image concentration was kept constant. The results are shown in figure 1b, where at 0 relative camera angle, the images and therefore errors are identical, and C epsilon1, epsilon2 equals 1. As relative angle increases, differences in the projection of the 3D particle cluster seen by each camera become significant, and the errors decorrelate. C epsilon1, epsilon2 will cross 0 at a particular relative camera angle, indicating a potentially noise-free estimate of displacement variance. This optimal angle depends on particle image diameter and light sheet thickness, as shown in figure 1c, with higher relative angles being needed for thinner light sheets and larger particle images. Other simulations isolating aliasing and camera noise errors show near 0 error correlation for all practical relative camera angles, but gradient errors were shown to be strongly correlated for all imaging conditions. In conclusion, our study suggests that the noise-free PIV technique using 4 stereoscopic cameras rather than the conventional 2 has the potential to significantly reduce measurement noise contribution to second-order velocity statistics. It relies on measurement errors from one camera pair being uncorrelated with measurement errors from the second camera pair. And our simulations suggest that with careful control of the PIV setup, an order of magnitude reduction in error contribution to velocity variance is possible. And lastly, in the near future, we plan to further evaluate this method by comparing simulation results with those obtained from an open channel flume. Thank you very much for your time, and please feel free to ask any questions.
Thank you very much. So I remind the audience that if you have questions, you can ask them in the chat and we will handle them all together at the end. So thank you, Nejme, for this presentation. And I'm now introducing the next speaker, Andrea Paindelli, who will present his work on numerical modeling to estimate the hydraulic efficiency on continuous transverse grate. So we will have the screen. That's perfect. Thank you. And the floor is yours.
Thank you so much, Rui. Thank you, Sandra. I hope you can hear me loud and clear. We have a lot of background noise here. They are working just in the other apartment there, so I hope we have no disturb. Before starting, I would like to pinpoint a thing. Just pose a question to the wall person here. In which situation we have water in the street, so flood in the street. There are usually two situations when we have too much water into the drainage system, so that the water can out the drainage system, can leave the drainage system, or we have no water in the drainage system at all. So the water from the street is not able to enter into the drainage system. So this work is just focused on the second part. So evaluate how much water is able to get into the drainage system from the street. There are very few studies regarding the efficiency of the inlet, the grades in the street. We are just usually during the project we are just putting the grades all over the streets and then hope that the water get into the drainage system and we have a good protection. But it's not like this. The grades should be tested, should be, evaluate the efficiency of the grades. And what they are doing at the University Polytechnic of Catalonia, Professor Manuel Gomez and Professor Beniamino Russo has been a long time studying these efficiencies of the transverse grade. They have 1:1 scale platform reproducing the street of Barcelona. They saying that the quality of the poster are low, they're not readable. I think it's just an issue of the connection. And they have this 1:1 scale platform of the University Polytechnic of Catalonia, where they study all these different grades. They study the efficiency of the grades. And this work is focused on reproducing this platform that we have at the University Polytechnic of Catalonia using computational fluid dynamic software on 3Ds to speed up this laboratory test and to discover new types of tests that we can conduct to evaluate the efficiency of these grades. So getting into the explanation, what we have done is just to reproduce using Flow 3Ds, which is a computational fluid dynamic software of flow science, to reproduce this 1:1 scale located into the laboratory test, building all the part of the platform that have the hopper tank, the water source, the platform, and the location of the grades. Solving different simulation with a fully 3D model in a normal computer, which is a Intel Core Duo with 12 gigabytes of RAM, pretty standard computer, not the best one to make this type of solution. And what we've done, we made a lot of simulation and we compared the result from laboratory tests with the numerical results in order to validate our numerical model. And actually we have found a good correlation. We have found a very high correlation regarding the water depth and also regarding the velocity distribution. Obviously with the velocity we have a bit more oscillation, but just the solution could be just let the simulation run and then the simulation will stabilize. The duration of the simulation was quite long. We are talking about days, but this is justified by the use of the computer that is not the best one to make this type of simulation, and also because the model was not perfect. The idea was not to reach the best, the speediest model cell possible, but to have a usable model, the models that run, that can perform a simulation. So the idea was just to build a model and make it run, not to improve the speed of the model. And basically that's it. We have just simulated just one type of transverse grades. In the future, in the near future, and also in the coming years, we are planning to simulate also the other grades. We are quite happy about the result, because if you can see the relation between numerical results and experimental results is quite high. Is 0.98, and that's it. This is basically another way to make a laboratory test using a computer. Obviously, using a computer is much more cheaper than using a laboratory scale 1:1 platform. But you should also take into consideration the price of using this type of software that usually are quite high, quite expensive. but I'm pretty sure that in the next year, considering the evolution of the technology, the availability of a powerful computer in pretty any place in the world, it could be a good solution to take into consideration. That's it. Basically, was that for my side. I hope it was clear enough. I mean, I know that 6 minutes is not a lot, but I hope it was clear. Thank you. Thank you so much.
It was clear. Thank you very much, Andrea. Well, the size of the posters is what it is. We cannot really improve that. Well, I hope you can read it. But in any case, the presentations will be recorded and they will be available, and we can see it with more detail when the symposium is over. And I would like to call now Clement Delhaize.
Yes.
From University of Liège, I believe, about drag coefficient of body-like shapes. Please, floor is yours.
Yeah, thank you. So I will introduce to you my work on the drag coefficient of a body-like shape. I have to say that this work is to feed a numerical model in which we need the drag coefficient of a body-like shape to modelize the drift of these bodies. So we worked on the drag coefficient of a body-like shape in the specific case of a drowning accident. Indeed, nothing is known on the drag coefficient of a human body in the case of an unconscious victim, while many studies have been realized on swimmers and their suits and positions. So the goal of my study was to determine a reference position of the body in the case of a drowning, and then to study its drag as a function of various specific parameters to such situations. These parameters are the body morphology, the depth at which the body is, the yaw angle, the limbs position, and the way the body was dressed. So experiments have been realized in 2 experimental facilities, which are a 20-meter long laboratory flume in which we worked with 3 different dummies at scale 1/6. And I'm sorry you cannot see that, but there is a picture of a 100-meter towing tank in which we worked with one real scale model, and then forces parallel to the flow motion were measured and the drag coefficient has been calculated. So note that a second coefficient has been calculated too in order to be less dependent on the inaccuracies in the measurement of the frontal area. So the determination of the reference configuration has been made thanks to the forensic literature and exchanges with the stakeholders. Both agreed to say that the reference configuration is with a body close to the water surface, limbs hanging down, head downstream and face down. What has been added is the fact that in this case, the body has a normal morphology, is naked, and has a spine aligned with the main flow stream. In fact, his configuration is the reference one with only the specific parameter modified. So once each force was measured, we calculated each coefficient to have a drag coefficient equals to 1.6 in the reference configuration. Statistical tests of the p-values were applied on the results to determine if the modified parameter has an influence on the drag coefficient. If the p-value is higher than 0.1, that means that the parameter has no influence on the drag coefficient. So none of them is in this case except for the yaw angle of the drag coefficient itself, while it is not the case with the modified coefficient. So this is due to the fact that the frontal area varies a lot when the yaw angle is 90 degrees, because at this angle, limbs are perfectly aligned. And a small approximation in the positioning of the dummy during the experiments leads to a huge difference in the actual frontal area. So thanks to the area less dependent coefficient, results are that none of the tested parameters is negligible in the case of a drowning. So I have to say that finally, the histogram of each measured drag coefficient highlights that it is impossible to assign a clear-cut value to a body-like shape in the specific case of a drowning, as this coefficient can vary by a factor of 2 as a function of the different parameters. So the configuration has to be known in order to assess the right drag coefficient. Thank you.
Thank you very much, Clément, for this nice presentation. And also thank you for keeping it short. We are recovering the small delay we have, and I will now introduce the next speaker, who is Mariano Letizia, who will tell us about detection of point-wise impulsive contaminations in rivers by a moment-based inverse method. So
thanks.
Screen should soon appear.
Okay. I introduce the detection of a point-wise contamination in rivers by a moment-based inverse method. Free surface water may occasionally be polluted by harmful contaminants, which degrades its quality and changes its characteristics. This may render water resources useless for the purpose for which they were planned. In a modern perspective, the appropriate monitoring of water bodies may be a key tool to prevent and mitigate the subsequent pollution. For instance, wireless sensor networks represent a very promising technology to monitor the contaminant concentration. This research focuses on the detection of a point-wise source contamination in a monitored river. We propose an inverse method based on the evaluation of temporal moments of the concentration measured in a cross-section and on their relationship with the distance from the pollutant injection point and the contaminant mass. Previous approach for solution of this problem documented in the literature relies on computationally expensive methods, whereas we are interested in a lightweight and robust alternative. The description of a contamination process employs the analytic solution of advective-convective transport equation under point-wise injection of a finite mass provided by Sauty. This simple yet effective model allowed to compute the closed form expressions relating the distance x between the injection and the measuring point and the contaminant mass m to the first and the second temporal moment after the evaluation of a concentration in a cross-section downstream of the injection point. This method was tested on different types of rivers that have different form and flow to verify its reliability. In the absence of measuring errors and certain parameters, the method provides perfect results. To better represent practical conditions, we accounted also for the presence of the random errors and measurement of contaminant concentration, and for the uncertainty in the knowledge of velocity and diffusion coefficient. The result of the latter test are shown in the figures A, B, C, D of the poster. For brevity, we reported the results only for the Volturno River, but we found similar results for the other rivers. In these figures, we consider uncertainty of 10%, that it is a realistic one even for the fusion coefficient, but the velocity is generally measured with greater accuracy. It is possible to note that the error in the estimation of true contamination parameters decreases with the distance between contamination and the measuring point. The error on the distance becomes negligible at large distances. On the other hand, the error of mass remains comparable to uncertainty. Similar results have been found accounting the random noise in the measures that aren't shown for brevity. Additionally, we tested this method in a real case considering the experiment reported in Van Genuketen et al. Paper, where they studied the contamination of Siljan River with the use of rhodomine WT. Our method gave us an error of 3% in distance estimation and 6% in the mass estimation. The proposed approach has demonstrated to be really robust. Additionally, accurate prediction of this, the position of the entity of the contamination may be obtained with the very limited computational resource. Future research will be devoted to further benchmark and extend the applicability of the proposed approach. Thanks for your time.
Rui, we cannot hear you, but you are, of course, congratulating the speaker. I don't know.
I'm sorry.
Okay.
There was some glitch here. I was saying, yeah, thank you very much for your very good presentation. And I would call Patricio Ortega Lara, which is already there, which comes from University of Politécnica de Cartagena, is it in Spain?
Yeah.
So please share your screen, and you're talking about the analysis of performance of an air water flow conductivity probe in a calibration rig, please.
Okay. Good afternoon, everyone. My name is Patricio Ortega Lara. I will be talking about analysis of the performance of air water flows conductivity probe in a calibration rig. Most high velocity air water flows are characterized by large amounts of entraining air. In air water flows, the measurement devices may be affected by air bubbles and air water interface, for example, pitot tube or acoustic Doppler velocimeter. Phase detection probes are commonly used to measurement air water properties, for example, conductivity and optical fiber probes. Measurements were carried out in a calibration rig designed and built at the Universidad Politécnica de Cartagena in Spain. The structure has a transparent metacrylate tube, which allows the mixing of water and air, being the distance large enough to be mixed flow to be uniform. Two independent flow meters are used to measure the air and water flow rates. At the end of the main pipe, there is a constructions exit nodes. The setup allows to analyze jets with outlet velocity up to 18 meters per second and void fractions up to 0.85. In addition, a dual tip conductivity phase detection probe was designed and built at the UPCT. The probe tips were made of platinum weir and with a diameter is a 0.25 millimeters. Measurements were sampled at different frequencies, 20, 40, 80, and 100 kilohertz. During 90 seconds. The conductivity probe was used for measuring the local void fraction distribution in the center of the circular jet and the entire cross-section located at the distance of 20.4 millimeters from the outlet nozzle. We compare the void fractions measurement in the center line of the jet with the corresponding to the airflow meter recording. Whereas some difference may be homologeous, for instance, a mean cross-sectional concentration is more relevant. Deviation between both estimations may indicate either a change in the void fraction distribution, non-uniform, or limitations for the conductivity probe. The airflow meter is deemed more accurate and thus current accepted as ground truth. For void fractions below 0.20, the recorded points by the conductivity probe systematically depart from the linear trend relative to airflow meter. Therefore, obtain lower values of void fractions than those generated by the calibration device. This may affect to difficulties in detecting bubbles at low concentrations. The obtained result shows a similar behavior to this report for other authors, Matos and Friesel and Borges et al. As the void fraction increase 0.30, the points tend to behave linearly, but however, the data dispersion also tends to increase. This behavior in the void fraction detection seems to be independent on the sampling frequency as in the test carried out. No remarkable difference are observed when the recording frequency is changed between 20 and 100 kilohertz. In the another figure, they present the void fraction distribution with two different setting values. In the central part, the jet, the void fraction values tend a constant value, hence supporting the uniformity hypothesis on to the center extent. As the points move away from the center, the trend changes due to ambient air and water strong interactions. In summary, the used conductivity probe has difficulties detecting air bubbles at low air concentrations, which also supported by previous research. But what is the next step? What other factors may affect or influence the bubble detections? Well, it's an open question that needs further study. This has been all, and thank you very much for your attention.
Okay, thank you. Thank you very much for your presentation. I think for the next one, it is maybe better. Yes, so David could share the screen, so we avoid some special thing on the screen, but fortunately we could see what was important from your presentation. And we now welcome Ida Mashtan from the University of Manchester, who will present us the work about impact force on a floating wooden debris on a masonry arch bridge. So Ida, present? Yes, okay.
Yeah,
so
thank you very much.
The floor is yours.
Hi everyone, as introduced, I am Eda Maitan, a PhD student at the University of Manchester. I will present today part of my wider research on impact force of a floating woody debris on a masonry arch bridge. A significant number of bridge stocks in many parts of the world is masonry arch bridge. For example, around 45% of the bridge stock in Spain is masonry arch bridge. Similarly, 40% in the UK and 32% in Germany. A substantial proportion of this type of bridge has been damaged or destroyed due to flood-induced loads in many parts of the world, and this is figure 1 is showing just one of them, Tadcaster Bridge in Yorkshire in the UK after the 2015 flood. And as you see, like center of the masonry arch bridge, these 2 arch barrel and 1 pier was destroyed by the flood. And based on this gap, many researchers focus on scouring and substructure behavior of masonry arch bridge, but really limited study available in the literature on flood-induced loads on superstructure of masonry arch bridge and associated response of these to these loads. So based on this gap in the literature, we did experimental study, and as I mentioned, like this is part of wider research, including numerical part, but this is not scope of this presentation. In the experimental part, we aim to evaluate drag force exerted by the hydrodynamic and floating debris impact on a model bridge. And figure 2 is showing the experimental setup we use in the University of Manchester hydraulics lab recirculating flume, and with the dimension 4 meters. With the dimension already 4 meter, 88 meter in length, 1.22 meter in width, and 0.61 meter in height. The model arch bridge was 1 to 1/10 scale. But the prototype bridge dimensions we decide based on the existing masonry arch bridge. With the based on the existing masonry arch bridge, this ratio is important for this 0.25 rise to span ratio, and these are based on the model arch bridge 0.8 meter span and 0.4 meter width. And the important thing, we didn't know where the debris will impact on the bridge. That's why we suspended the bridge 5 millimeter, the gap between the bridge bottom and bottom of the flume, and by using elbow joiner and the below cell upstream, downstream of the bridge we located, And cylindrical wooden debris, specifically English oak with the diameter to length ratio of 0.059 we use based on the literature. Debris in initial orientation was parallel to the bridge span with its initial distance of 1.5 meter from the bridge, already you can see in the figure 2, and free surface velocity of 0.2 meter per second at 1.75 upstream of the bridge, with 0.208 meter flow depth we use. And we did for each case, we did 3 different tests as a repeatability analysis. And we, based on the result, as you can see in figure 3, drag force with just aerodynamic case and the combination hydrodynamic and debris impact case given. And this figure 3A is showing just the debris orientation when the debris impacted the bridge compared to initial position, initial orientation shown in the figure 2. And considering this result, drag mean of 12.33 Newton, we got the drag force in the hydrodynamic case with the standard deviation of 1.42 Newton, and the mean drag force, the peak force, 52.51 Newton with the standard deviation of 7.97 Newton in the case with the combination of the debris and hydrodynamic case. But here is important, like just not the high 4.3 times higher impact load. Another thing, the time, like impact duration, and also rise time of the impact duration. So to summarize the all findings, like flood-induced hydrodynamic and debris impact loads were obtained experimentally. The results show that debris impact result in significant higher loading on the bridge with shorter duration compared to the hydrodynamic loads, which can cause local failure, these like cracks in the structure, and this already with the crack propagation already it can be global failure. Thank you very much for your attendance, listening to me, and please don't hesitate to ask any question. End of the session.
Thank you, Eva, for your very nice presentation. I would now call Federico Romero, I believe from the Instituto Nacional del Agua, Argentina, speaking about the experimental study of cavitation in bottom outlets.
Hi, good afternoon. I am going to share with you the experimental study of cavitation in bottom outlets. It's important to refresh that cavitation can be due to 2 phenomena. The pressure fluctuation because of macroturbulent process, such as those occurring in hydraulic shems, which could affect the surfaces of steel basins, and because of high velocity flows in a structure with surface irregularities. We have analyzed the last of those causes by means of experimental study in 1 to 12 scale physical model, which allows the correct representation of the air incorporation phenomenon. The design of the structure under study is a channel discharge of a bottom outlet, which approximately 200 meters long of a rectangular section, which 4 aerator steps. In order to define where the highest risk of cavitation beginning could be developed, the cavitation index was estimated in different sections by recourse of pressures and velocity and using the equation 1. Then it was compared with the critical cavitation index for the maximum specific discharge of 32 square meters per second that has progressive decrease of the flow speed from 27 to 18 meters per second. To determine the critical cavitation index, the criteria developed by the US Bureau of Reclamation was adopted. As shown in table 1, the criteria define 3 different maximum surface offset irregularities to prevent damage of cavitation by linking the cavitation index and the presence or not of air in the flow, which can strongly reduce the exposure to the phenomena study. Therefore, The average air concentration in the flow close to the structure surface was incorporated in the recording parameters measured by a conductivity phase detection probe. In order to determine if air concentration was enough, the study of Janson was used. According to his research, value in order of 1 to 2%, although it does not completely protect the structure, reduce substantially the risk of erosion by cavitation. The results obtained determine the region susceptible to the beginning of cavitation by the joint evaluation of the mentioned parameters. Those are shown together in the double vertical axis graph, where are present the average air concentration in black curve and the cavitation index in the red curves all along the channel. The most exposed area to cavitation damage is where the air concentration is less than 2% and the cavitation index less than 0.4, as value measured in the section 1 and at the end of the section 2. In general terms, it also observed a progressive reduction of air from the aerator steps towards the end of the section, and an increase in cavitation index because of the decrease in velocity. In conclusion, as a design recommendation to prevent the beginning of cavitation, structural measures should be taken to increase the air concentration, or it is necessary to ensure in the constraint process offset surface less than 6 millimeters in the section 1 and the end of the section 2, and 25 millimeters in the rest of the structure. And finally, I would like to thank to the hydraulic structure program of the INA, especially to Daniel Bachiega, Claudio Fator, Santiago Arrigoni, and Constanza Fernandez for their help in this research, and thank you all for listening.
Thank you very much for your presentation. So we are already close to the end of this series of presentation, because we welcome now the last speaker of this session, who is Sinara Camelo from the University of Campina Grande in Brazil. Yes, okay, it was a collaboration with Portugal. So the floor is yours, please.
Hi, everyone. My name is Sinara. And before I start, I would like to apologize for the change in the theme of the work. The person responsible for building the experimental model tested positive for COVID-19, and that's why we weren't able to carry out the experiment in time. So the work I'm going to present today is numerical analysis of contaminant transport through porous media. The groundwater is a valuable resource which can be threatened by the discharge of various polluting sources. Therefore, the objective of this work was to evaluate computational fluid dynamics techniques to simulate a saturated porous media and its behavior against the release of polluting water. So a CFD model in ANSYS Fluent was built up to analyze a horizontal flume in which a section was filled with fine sand, treated so that it could be characterized by non-physical properties, namely porosity and permeability. The contained section of sand was crossed by a constant flow of water to become saturated. And the flow discharge of the dye solution representing the soluble pollutant from the top into the soil was constant, like shown in figure 1. The numerical technique, which is used within ANSYS Fluent, considers a porous medium model to define the sand region, which is represented by an empirically determined flow resistance, translated as an added momentum sink in the governing momentum equations. So the boundary and initial conditions were the inlet, water head at the left, the inlet with a constant concentration at the top, the outlet with water pressure at the right, and the wall no slip at the bottom. A structured rectangular quadrilateral mesh was considered To be sure that the mesh was not affecting the study, 3 different meshes were tested. The simulations allow the analysis of the velocity distribution of dye and its transportation along through the porous media. For velocity of water equal to 0.002 meters per second, and velocity of dye equal to 0.02 meters per second of discharge of polluted water from the top, like are shown in figure 2. It can be seen that the dye enters the porous medium, but is dragged by the flow of water. The mesh is M1 with 0.005 meters by 0.005 meters with 5,000 cells. Mesh 2 with 0.0035 meters by 0.0035 meters with 10,153 cells, and mesh 3 with 0.0025 meters by 0.0025 meters with 20,000 cells were tested. Figure 3 shows the results for the velocity field in a cross section in the dye discharge for each tested mesh. The results obtained for the velocity profile show the reliability on mesh 2. So this mesh was used at all results obtained in this work. So to analyze the impact of the discharge of pollutants, 4 different velocities of pollutants were simulated, like velocity 1 equal to 0.001 meters per second, velocity 2 equal to 0.004 meters per second, velocity 3 equal to 0.008 meters per second, and velocity 4 equal to 0.016 meters per second, shown in figure 4. The examination of flow patterns showed that the extent and the form of contamination depends considerably on the rate of leakage and the rate of entry of water, representing the natural infiltration. So, CFD-based is a valid methodology to understand the process of transporting contaminants through subsurface porous media with an appropriate computational mesh. As the dye discharge velocity increases, the reach of the contamination range expands in the y direction. And for future work, we will focus on analyzing an analogous physical model to corroborate the numerical results through qualitative comparison and performing new simulations by varying the porosity values. And that's all. Thank you for listening.
Thank you. Thank you, Sinara. Sandra, I have an issue here. Can you start the debate? I'm sorry.
Okay, well, first of all, thank you to all the presenters. Thank you for keeping the time. We are now entering, well, it's called the coffee break, but it's unfortunate that we cannot have a real coffee. So in this virtual coffee break, we are going through the questions that were raised in the questions and answer sessions. There were, so not going to take them all in the right order because some were maybe already answered, but I see that there were several questions for Ida. So maybe we can start with those. So we'll read the question. There is first question, could you please explain the prototype scale which is used in your model? And then related to that, do you use the dimensional analysis to determine all the parameters that affect the impact force on the bridge? So this is for the first series of questions. Can you briefly answer this?
Yeah, can you hear me? Can you hear me? Yeah, okay, perfect. We use, we collect the data from the bridge dimensions, and this is like damaged one single span, representative one single span, the bridge dimensions, and its rise to span ratio is important to define this 0.25 as I mentioned, and it is the width is 4 meters, it is representing single lane, vehicular, car, the width, and the span is 8 meters, again representing the typical bridge dimensions. We mentioned these are more detailed in our published paper. I gave already end of the abstract, extended abstract. You can have a look if you are interested.
Okay. And then in addition to this, we had also a question about the orientation of the debris that will
yeah, I can read that. Like okay, the influence of debris orientation at impact is significant. It's significant. Yes, it is significant. As like 90 degree and 0 degree we consider, but for this case we are just using where the abutment, we have abutment, arch barrel, and spandrel wall as a superstructure of masonry and arch, which this case just abutment is fully submerged. That's why I cannot consider here 90 degree debris orientation the impact because it is passing through the bridge. It is not impacting the bridge. But if I am considering different submerge ratio like spandrel wall or arch barrel, yes, we can consider this 90 degree debris orientation. And as I mentioned in our paper, we mentioned already this one. If you are, but if you want to ask any question, please ask by email. I'm happy to discuss.
Okay, thank you very much. I think Rui, you want to discuss the PIV results, maybe.
Yeah, okay. There's a few questions more by Mark Keating, for instance, about the PIV results. I'm not fully understanding the question. Will the PIV results be correlated against CFD results? I suppose that you mean that if these results are going to be validated with CFD and not only with open channel results or open channel flows, actual flows. Is Mark here? Can Mark speak? No. This is only questions and answers written, and then Nime can reply. So please, Nime.
Yeah, so as I typed in my answer, at the moment, it's not part of the plan. We're just planning to validate the simulation results using open channel flow experimental results. But depending on how well the experimental validation supports our simulation work, we may add CFD work to support it further.
Okay, thank you. I had maybe, so if you have questions, don't hesitate to write them in the chat. And in the meantime, I had a question for the first presenter. So you discussed about pumps and you showed comparisons between numerical modeling and experimental measurements, high quality results. But I was wondering, what are the calibration parameters of your model? Can the calibration be done without having access to measurements on a real pump? So this was for Joris Hardy, the first presenter.
So yes, no, it has nonsense to make a calibration without any data about the pump. But yes, we can also do a calibration based on the manufacturer data, but it will not be as accurate as it will be with the test done for the pump, because in most manufacturer datasheets, you don't have access to the pump curve for different rotation speed. They are usually given for several impeller size, for example, but not always for different rotation speeds.
Okay, thank you. But indeed, I think it's interesting to be able to assess the quality of the results that you can expect without doing measurements on the pump, but just based on the manufacturer's data and geometrical data of the pump. It would be interesting to compare this.
Okay.
So I don't know if we have other questions.
I have a general reflection on this session. This is a session about experimental methods instrumentation, and it's one of the usage of experimental methods and instrumentation, of course, is to provide data for model calibration or for the estimation of the parameters that then will be used in models used for solving actual problems. So it's quite interesting to note that most of the presentations here were exactly on this streak. I mean, they were not standalone problems or problems that could be used with experimentation itself, but mostly determining validation or determining methodologies to validate or to understand how computational models would work then. I suppose that in the case of EDA, there will be a study on with dual-S physics at some point, maybe not by EDA, but by some colleagues.
Yeah, I'm using dual-S physics, and I'm validating my SPH model with this experiment. Yeah.
At some point, I understand this is valuable to make this dual with experimentation and with numerical tools as well. And is this a trend? Is this something that we can think of as a trend? I mean, experimentation by itself is not solving problems. It's not enough now to capture the fundamentals of the physics and or chemistry or whatever, or fundamental, disciplines. Do we need to go on to a modeling stage afterwards? I mean, beyond these concrete questions that we still have time to pose to our panelists, I would like to go a little bit on this, because it's something that we are working quite a lot in IAHR on the experimental methods and instrumentation. What are the links to other ways to understand the world, namely with numerical computational tools? But is this losing track, this idea that we can do experiments, know the world, and this will be enough? Do we still need, or do we feel that we need one next step, which is putting this into a model, and it is the model that is going to solve the problems, and our experiments are going only to calibrate these models? I would like to hear the views of the next generation on this. Eda, you were talking. You were going to use and probably you have this.
I'm both using numerical part and numerical method and experimental method. It is both are necessary at the point. Like, of course, it's easy to do. Not easy, but if you have enough GPU, CPU, you can do simulation. CFD, I'm using GPU, for example. But for the experiment, of course, cost. But why we need experiment? This is important. Why we need experiment? For example, for my case, SPH I'm using quite new method compared to mesh-based methods. That's why I need to validate my numerical model, or I need to examine how the accuracy of the method. That's why I am doing experimental study, like I'm conducting the experiment to examine my numerical model. So I will, after finding out the capability of the SPH model, then we will, of course, continue with the numerical model. And this is already, as an engineer, we are thinking, we need to optimize everything, money, time, everything. So why we need experiment? Of course, experiment giving the real results, but we need to find out how we can use this numerical model and what is the exact accuracy of the method we are using.
Okay. Sinara, yes, you were on the same track, I suppose. Sorry, Sandra. Let me just do this question to Sinara. You had this work on experiments and then numerics, and then the experiments fell through because of COVID, and so you were left off with the numerics. What was lost, given that the ability to conduct experiments was well, not there? You could not do it. So what do you think was lost that since you could not conduct these previous experiments? Is this something that is going to affect the research, or is something that you think that the numerics are going to show the way in any case? If you do many simulations, if you fill with parameters, would you still feel the need for experiments?
I'm not sure that Sinara
I'm not sure
is
that.
there, or okay, but
Rita is there. Rita, do you want to? Maybe she's not anymore.
no, I don't think so.
Can you repeat, please?
Yeah, this is just a teaser. It's just devil's advocate. So you could not do experiments. COVID didn't allow for that. In many labs that happened. So what is the role of numerics then? Do you feel that you can actually, improve knowledge with numerics only by fiddling with parameters, by tuning, by conducting runs with many diverse scenarios? Or would you still have this feeling that to properly ground knowledge, you still at some point need experiments and actual data?
I think that the experiment is important because of the parameters that we have to input in the model, in the ANSYS. So we did several analyses with the soil, like density, porosity, permeability, to use these values in the model, and we still are going to do the experiment till the end of December to compare the results. But until now, we think that just with the model with a good characterized of the sand, the region, the properties of the soil, of the porous medium, we can have a good results with the ANSYS, with the model in CFD.
Very well.
Okay, I think that there is something really interesting in all what you are doing when you combine experimental research with numerical simulations. You are all aware that the reality is on the side of the experiments, and that's important. And numerical models, you need always to make sure that they reproduce the reality. And once they are well calibrated, or once you are convinced that they can reproduce in a reliable way the reality, you can use them to test many scenarios. That's really interesting. And I think that you all in a way show that it's important to be sure of what your numerical model is doing by having good quality experiments. And again, we have a question that is going also in that direction, a question by Maël Lemar for Joris, for the first presenter, asking if there is a strong difference between the manufacturer's curve and your experimental curve at 50 Hertz. And again, it's in this sense, how good are the predictions, how reliable are they compared to what the manufacturer produced, often based on experimental measurements. So I don't know if you can answer this question, Joris, maybe? You need to reactivate your microphone.
This question is for me?
It was for Joris, but apparently he has some difficulty. Okay, now he's back.
So, okay. So I'm just reading the question. So I see the question, but I don't understand the question. For me, there is no question. It's a yes or no.
The question is, if you construct so you have done measurements also apparently, and you have obtained a new curve at 50 Hertz.
Yes, yes.
How does this compare to the manufacturer's curve?
This is maybe due to the fact also that the pump was stored several years outside, and also maybe due to the fact in terms of efficiency, due to the fact that we use a variable speed drive that has an efficiency too. And for variable speed drive, the efficiency is nearly a constant around 90%, which is quite negligible, but you can see the difference on the graph for the total efficiency. And so if you took the efficiency given by the manufacturer and then multiply it by 90%, you can retrieve a curve that is nearly the same as observed in the test bench for the frequency 50 Hertz.
Okay, thank you. We have here, it's not really a question, but it's an interesting comment by Mark Keating. You can probably read it. He's discussing the question of artificial intelligence, and this was also interestingly pointed out in the keynote lecture by Mohamed just before the session, showing that if you use only artificial intelligence, you can come up with results that are completely wrong compared to models that are based on the physics and that are complemented with artificial intelligence. So Mark is saying that experimental and numerical methods will work hand in hand, but also including some assets from artificial intelligence. And maybe some of you, of the young researchers, did you use some artificial intelligence, or are you going towards such methods? Do you intend to go towards such methods? Maybe it would be interesting to hear your opinion about that.
And perhaps to focus on or even focus a little bit more on this session, experimentation again, or sensing, more than experimentation, sensing, is going to play a huge role. And I agree with Mark here, it's going to play a huge role in the near future. It's not just combining with artificial intelligence, it's all this idea that critical infrastructure should have a digital twin. Everything will have a digital twin. Full cities may have a digital twin. And you need to know how to combine information, and you need to know how to sense information, how to believe in your sensors. So there's a huge role for instrumentation still here. And then all the rest, combining all of this, is going to be informing models that will be running full-time, let's say, with many components, and that will allow us to plan better, to change in the digital twin or in the virtual twin or the virtual part before actually putting that in the field. So yeah, we have to agree that in the future there will be a major interplay between what we sense and what we model for the well, for this idea of everything will have its, or everything critical will have its own digital counterpart on which we can fiddle and we can change and we can. But there is for the old timers, there is also this idea that real knowledge, as Sandra was saying, real, fresh knowledge, some, introducing novelty, probably cannot come from modeling, or at this stage even from artificial intelligence. We have to be able to measure things and to interpret what we're doing and build actual knowledge on that. Models, interesting as they may be, or flexible as they may be, cannot create what was not already coded, unless they're very, very, very fundamental. I'm thinking DNS, for instance. But anything that will introduce a parameter will have relied on production of truth on the empirical phase. And we had some presentations on that from Patricio, from Federico, and from Nime, which I'm constantly pronouncing her name wrong. I'm sorry, but Patricio and Federico we haven't discussed yet, and I would like to hear the motivation of Patricio again on how to calibrate the probes, which are a sensing instrument quite interesting for multi-phase flows. And how do you handle that instrumentation? How do you handle that facility? How do you know what are you injecting? How do you know the size of the bubbles? How do you know that you are calibrating the probes correctly?
The motivation this study is understanding the mechanisms that are training flow. For example, air water flows are characterized for amounts of air entrainment. And the motivation was we experimented in rectangular free-falling jets, and we can see that the air entrainment affects the rectangular free-falling jets. For this mode, we analyze air concentrations, bubble frequency, etc. And we compare the efficiency of phase detection probes and optical fiber probes. And no visually difference, but in other experiments, we can see for low concentrations, the detecting bubbles is lower than air flow meter, and that is the motivation. For example, we understand exceeds other force. For example, velocity bias is strong in laboratory scale investigations. It may affect the extrapolation of results the full scale, for example. What factors may affect the bubble detections?
Okay, very well. I'm being unfair. There are other, there are other, at least one other presentation that was really on the side of collecting information on an empirical basis, which was from Mariano Leticia. I don't know, do you want to go back to this? Mariano, you had this problem and you came out with an answer which was, if I understood, is you cannot really give a definite, you cannot attribute a drag coefficient to a model of a person, if I understand. It's much more complicated from the experimental point of view. You cannot really just pin down one value or pin down one way of doing this, if I understand. It was a bit more complicated than that. Would you feel that with the advent of computational methods and believing in computational methods and all of the flexibility of variations that you can get, you could go further if you step out of the channel and went into more virtual kind of simulations?
If it is possible, I want listen on the question, sorry.
If it's possible, I'm sorry.
I don't understand the question. If you can repeat that.
Yeah. Again, I was under the impression that you. I'm sorry, Marianne. This was for Clement Delhaize. I'm sorry. It was the drag coefficient on a body-like shape. I'm sorry.
Oh, okay.
I'm sorry. There's another question for you, but I mixed. It was for Clement. It was, if I understood, it was you mentioned that it was not totally possible to specify a drag coefficient, to put it in a simple way.
Yes, exactly, because it depends on so various parameters that you can't assign a clear-cut value to the coefficient. And so you have to know more parameters in order to assign the right drag coefficient to the shape.
Okay, and now that we're speaking about this, empirical view and using sediment modeling, would modeling be helpful here, given that you have more flexibility in setting up experiments and putting gradients in your models? And would you feel that you'd learn something that in the lab you might not be able to learn?
Sorry, could you repeat, please?
One of the problems, I believe, is that your flows in a 1D flume, let's say, would be very simple. Would you feel that it would be useful to use numerical models with some detail, large eddy simulations, for instance, in which your variability of flows would help you learn more than you can learn in a channel in those conditions that you studied?
Yes, we do both. We use the experimental and the numerical to learn the more that we can do.
Okay. And for Mariano, in fact, I had also a question here, because it's something with a mix of analytical methods and experiments. And for the analytical methods, I believe you would need a lot of information coming not only from estimations, but also the uncertainty of these experiments, of this empirical information. I believe that your normally inverse methods will be very much depending on noise, on non-true components. How do you tackle that? How do you key in the issue of uncertainty?
Okay. Okay. We
yeah.
Yeah. I'm so excited. Allora, we have considering some type of uncertainty parameters. In fact, we consider the diffusion parameter and velocity parameter. The diffusion parameter is a parameter that is not simple to evaluate. In fact, we consider 10% of the uncertainty, by our experiment on the different types of rivers, we have seen that random noise of concentration, because it's the important it is the important error that we can find in our experiment. In fact, if we use a random noise of evaluation of the concentration, we find the same values of error, or we verified our methods that not amplifies the uncertainty of the parameters with the random noise and measured concentration. In fact, we performed several numerical tests on different sides of rivers. We consider the Missouri, and we consider the Wind Bighorn, that is a really little river.
Okay, thank you. Sandra, would you like to start closing this?
Yes, indeed, that's what I was going to say. So we are coming slowly to the end of this session, and we had many interesting presentations. We had also some discussions. Of course, it's difficult if not everybody can ask questions, but thank you for those who did. Thank you for asking questions in the chat. Thank you also to all the presenters for participating in this very nice initiative from IAHR. And I let now Rui close this session.
No, I've just the same remarks that you have. Appreciate the contributions of all. We wanted this to be a lively debate, of course, and sometimes there are some participants with more questions and more, that get a little bit more attention. I hope that everybody was satisfied with the discussions. I hope that this initiative is to continue in the future. It's very important that young researchers have a forum and contact with other younger researchers and understand start making the map of what was there before them and what is the potential to evolution of their own research. And I think this initiative is really very important. I'm looking forward for the next days of this second Congress of the Young Professional Network. So thank you very much, and I think that we should end the session now. Thank you very much.
Thank you very much.
Welcome everybody. We are going to start our second session in today with the support of two incredible chairs, Claudia Addus from the University Rome 3 from Italy, and Damien Biolot from the EDF in France. As Manis, Pandlik, and me, we are going to support you during the presentation. Manis is going to share his screen with the different poster. So please, Claudia and Damien, start when you want, and the floor is yours.
Just the screen is visible.
Hi, thank you for the introduction. And
I would like just to introduce this session of fluid mechanics within the second YPN Congress. And we have 9 pastors, and the pastors will be presented with a duration of each presentation of 6 minutes, and the questions will be given at the end of the presentations during the coffee break. Can you hear me?
Yeah, we can hear you.
Okay.
Yes.
We do. Okay. And Damian, would we share the presentation introduction of the several contributions?
Excuse me?
Could we share the presentations of the different pastors? I can introduce one pastor and you can introduce another one.
As you like, Claudia.
Yeah, if you preserve, I think that. And if you could you introduce this one, because I am one of the author, and then
okay.
it's better if you introduce it.
I'm discovering the program, in fact. So we will welcome first Maria Rita Maggi, presenting a poster on lock exchange gravity currents propagating over roughness elements. So is the speaker here, Maria?
Yeah. Yes, I'm here.
So you may start now.
So, okay, thank you. Good evening, everyone. Thank you, Professor, for the introduction. I'm Maria Rita Maggi, a third-year PhD student from Roma Tre University. It's a pleasure today to be a part of this Congress and speak about my study concerning gravity currents. So, and moreover, it's a pleasure to be here and to share opinion with other young colleagues. This study was performed under the supervision of Professor Claudia Duce in collaboration with the Legge Institute in Grenoble. Let's start with a brief introduction about gravity currents. Gravity currents are buoyancy-driven flow generated by a density gradient. Usually, those flows widely occur in nature, spontaneously, or are made by human activities. Examples of gravity currents are oceanic currents, river plume, or sandstorm. So usually this kind of flow develop over a complex topography. And the aim of my study indeed is to show how the topographic features can affect the dynamic of the gravity current. To reach my goal, we performed several lock exchange laboratory experiments. Precisely here in figure 1, we can see the sketch of the experimental setup adopting to realize the study. Thanks to a sliding gate, it was possible to divide a perplex tank in 2 regions. The first volume of the tank was filled with a salty water, while the rest of the tank was filled with an ambient fluid. The density gradient was kept constant. So the bottom roughness were made by Lego bricks. The distance between the elements has been kept constant, while the height of the elements has been varied. So we performed several experiments with uniform height distribution of the bottom roughness, several experiments with a random distribution, and moreover, a set of smooth experiments were performed. So the flow velocity were determined using a optical, non-intrusive experimental technique known as PIV. In particular, we focus on 2 different fields of view. One very close to the sliding gate and one 50 centimeters from the sliding gate. Thanks to the PIV, it was possible to obtain the instantaneous velocity maps. In figure 2, we show the streamwise velocity field after the current reached almost the limit of the visualization window. We have in the first panel a smooth run, while in the second panel we can see a gravity current develop over roughness bottom with a uniform height. Focus on the time evolution of the dense current, we define how the presence of the bottom elements leads to a reduction in the velocity of the current propagation. Moreover, we determine the interface between the current, the dense current, and the ambient fluid, considering the condition where the streamwise velocity is equal to 0. In this manner, we can study how the typical structure of the gravity current is modified by the presence of the elements on the bottom. Moreover, the analysis of the instantaneous map of the velocity field in the presence of the recirculation area on the bottom, in the case in which we have the elements, and this recirculation area are constant over time with a longitudinal development and an height depending on the height of the bricks. So with simple analysis, in conclusion, we show how the additional drag force induce more complexity in the flow dynamics. Thank you. If you have any question after.
Thank you. Well, the question can be written also in the chat, and then we can read all the questions later during the coffee break.
Okay, thank you.
And thank you, Maria Rita. And we can move to the second poster, second presentation. Is Stefano Miliani here? Stefano Miliani, are you here?
Currently, he's not.
He's not.
So what shall we do? Come to the next.
Let's go ahead. Yeah. Let's move to the next presentation. If Stefano will join us later, he can show his poster later. And then we can move to the third presentation. And the authors.
Sorry if I interrupt you.
Stefano is here. Stefano, I can see you. We can't hear you.
We can't hear, so maybe you can try to log out and log in again. Maybe a problem with your mic.
Yeah, Stefano, we go ahead with the next presentation. Try to go out, log out and log in as Damian suggested, and then you will present at the end. Okay, try to solve the problems with your voice. That's not possible to be here. And okay. Now we go to the head with the next presentation, the third presentation. Pablo Solan-Fustero is here.
Yeah, can you hear me?
Yes, and we can hear you. Okay. And we have this presentation, a priori estimation of the performance of Rhino and UWC schemes as ILES methods, and the authors are Pablo Solan-Fustero, Adrián Navas Montilla, Esteban Ferrer, Juan Manzanero, and Pilar Garcia Navarro. Please.
Yes, thank you very much for your presentation. Well, I'm Pablo Solan-Fustero. I'm a PhD student in the Computational Hydraulics group at the University of Zaragoza. And the main goal of this work is to find a priori guidelines for the computation of under-resolved turbulent flows. In this way, we have carried out an approximate dispersion diffusion analysis of higher-order schemes to solve problems with turbulent fluctuations. Since turbulence lacks an analytical model, implicit large simulation methods are used to resolve the large scales of turbulent flows, while the small scales are filtered out by the numerical error of the discretization scheme. And while high order schemes. Well, turbulent flows are multi-scale problems, so high order schemes can be used for this purpose because they provide high accuracy at all scales. In this work, we try to estimate the performance of the several high order numerical schemes as implicit LES methods. To do so, first, we implemented an approximate von Neumann spectral analysis of this above mentioned high order schemes applied to the 1D linear advection equation. With this, we have obtained a priori guidelines that are the cutoff wave numbers based on the 1% rule. These guys here, KDs and KDIF. Second, we solved the 1D Burger's turbulence problem, which acts as a 1D version of the turbulent behavior. And we plot the energy cascade of these results to represent the energy spectrum along the wave numbers. And finally, to test the validity of the a priori guidelines obtained in the first part, we plot the cutoff wave numbers together with the energy cascades in this figure 1, in these plots of figure 1. Here, the black line represents the energy cascade, and the dashed lines at the end of the cascades are the cutoff wave numbers. The 7th order central upwind scheme with C field number 0.1, which is the upper left plot, is characterized by an energy pileup at the end, just at high wave numbers. There, the energy increases before it is entirely dissipated, and this is not a desirable performance. But as we can see, if we raise the C field number to 0.9, this energy pileup decreases. And we can also see that the cutoff wave numbers predict the location of the maximum of the energy pileup and the start of the dissipation region. And what about the nonlinear schemes that are the winner schemes here in the red? Well, the main difference between central upwind schemes and winner schemes is the absence of the energy pileup. The energy because they provide high dissipation, and winner schemes don't depend on the C field number, as you can see here, and they are highly robust for implicit LES methods because they provide high accuracy at high wave numbers. And finally, one more application is the one that you can see here in the right plots. The cutoff wave numbers, based on the 1% rule, can be used as a criterion for scheme selection according to the efficiency. Here we plot the cutoff wave numbers in diffusion, KDIF, against the CPU times used to solve several problems with the different schemes considered. For example, the 7th order central upwind 4th order Ronjecuta method is more efficient than the other two that are highlighted in the left figure. And to sum up, the main conclusions are that the cutoff wave numbers predict the start of the dissipation region, so the 1% rule is a useful tool, and that the winner schemes are more diffusive than the central upwind schemes. But both may be suitable choices for implicit LES turbulence modeling. And as future work, we will try these estimation tools on 2D and 3D problems, and we will look for ways to find out whether there is an energy pileup or not, because at the moment we only know the location of it, if any. Thank you very much for your attention.
Thank you for your presentation.
So shall we proceed back to the second? Yes. So what about the author of the second presentation, the second poster? Stefano, are you back with us, and can you try to speak?
Yeah, I solved the problem. Sorry for.
Right. So please go on. Well, actually, Claudia already introduced the title and your co-authors, so I believe you can start.
Okay. I cannot see the presentation.
Is it up to me to do that, Claudia? Okay, let's see. It appears now. You can go.
No, no, it's.
Oh, it's
I think it's the one of the next one.
Yeah, it was.
Yeah.
I can show mine from my computer if there's a problem.
Claudia, who is managing that?
I'm not managing this.
Yes, I think it's not none of us, in fact.
Yeah.
It's done by the IAHR host.
Jose?
Just give me 1 minute. I'm answering.
Yeah, it's the second presentation, poster number 27.
I think that one now.
Yeah, this one. Thank you.
Thank you.
Okay, sorry again for the problem. Thank you for the introduction. I'm Stefano Miliani, and as you can see, the argument of my presentation is the numerical simulation of droplet arrangement inside a pore using LBM. We chose this argument because emulsion play a pivotal role in many engineering fields. In particular, it has been demonstrated that the emulsification of dispersed oil mass inside the soil created by the injection of chemicals, in particular surfactant, increase the efficiencies of process like oil extraction and soil remediation. However, the study of these processes using physical model can be unfeasible in some cases. They resort to numerical modeling. Among the many numerical models available, the LBM, the lattice-Boltzmann method, is a mesoscopic approach which can be seen as a discretization of Boltzmann equation. In LBM, fluids are described in terms of propagation and collision of particles by a distribution function, which represent the probability of finding a particle in a position x with a velocity e at the time t. The model we use is governed by the equation that is shown in the method section of the poster. In this equation, f is the distribution function, while omega is a quantity which take into account the fluid viscosity, the effect of the surface tension, and the meter diffusion of the component. In fact, we are trying to simulate the emulsion flows. Therefore, we have two different fluids and so also two different sets of equations. In order to take into account the effect of surfactant, to the equation is added an additional short-range repulsive force which act only on the fluid interface. The model is was already validated in other case scenario. However, we decided to perform a further validation using the work of Joseph Kubaut as benchmark. In figure 1, you can see a sketch of the physical model and of the computational domain, of course. Joseph Kubaut found out that with different combination of the capillary number and the ratio between the distance between two droplets and their diameters inside the inner channel, the droplet assume a particular arrangement inside the pore. So we try with our model to reproduce such patterns. In particular, in figure 2 panel A, you can see all the simulation of performed with the LBM model, which are represented by the black crosses, while the results of our model are displayed in the panel B. As you can see, the model can reproduce this geometrical pattern with ease. In particular, the first two cases, the one order layer and the two order layer, are reproduced almost perfectly. While for more complex cases with, let's say, more than 3 layers, the model is able to reproduce the shape and the dimension of the arrangement quite satisfactory. So we can see in conclusion that the model is able, proves to be able to simulate such phenomena, and so it can be used to explore parameter space relevant to technical scenario. I want to conclude with, let's say, a future application of the model. In particular, now we are trying to understand how the presence of surfactant influence the mobilization of slow dispersed mass inside an idealized porous matrix. In figure 3, you can see like one example of this of our simulation. For example, we vary in the wettability, so we pull wettable solid walls. They generate, there is, let's say, a formation of a thick layer of adherent mass, which promotes the breakup of the dispersed mass in this porous matrix. Thank you for your attention.
Thank you, Stefano. Let's go ahead with the fourth presentation. Juan Mayral.
Yes. Can you hear me all right?
Yeah. Now, the title of presentation is a cross-validation study of computational methods for droplet spreading, and the authors are Juan Mayral and Lennon O'Naraik.
Okay. Well, hello everyone, and welcome to this presentation on the work that we've been doing. So I'm Juan, and I'm currently a PhD. I'm starting my PhD at the University of Zaragoza with a group of computational hydrodynamics. But before that, I was doing my master's research project with Professor O'Nara at UCD, the University College of Dublin. So the idea for this project came from the fact that droplet spreading is quite a popular problem because it has many applications in industry, for example, and also in other fields like forensic research and the natural sciences, climatology, soil science. So what happens is that many different scientists from many different backgrounds and who don't necessarily have the tools of computational fluid dynamics come together to the need for good results on droplet spreading. So it would be good, it would be ideal to have a tool that could carry out simulations easily without the need to produce their own homemade code, which is extremely costly. For that, we propose to use OpenFOAM, which is very popular as a C++ library for computational fluid dynamics. And well, the problem is that simulations of droplet spreading have a contact line, which is the point in which the surface of the droplet meets the substrate. And so it's been known for many years now that if you impose a no-slip condition, which is the most useful thing to do in this kind of simulations, on the contact line, it develops a stress singularity, and you cannot calculate that. So new methods are needed new formulations are needed to solve this singularity. And so we propose here two of the most used ones, which is the diffuse interface method, which introduce the physical characteristics to the interface that it allows diffusion, so natural diffusion. And the contact line moves physically without need of imposing outside laws, like we do in the second method, which uses an outside law for the contact angle. So basically you use parameters to say the contact angle at that time should be this, and you give a law. And in OpenFOAM, there are two laws implemented, which allow for a constant contact angle. So the contact angle is set to be the equilibrium contact angle, which can be found using well, the classical Young law of surface tension. But then there is the possibility of having dynamic contact angle, of which only one equation is implemented, and it is the second function that you see in the blue box. And it's given in terms of the equilibrium contact angle, the two special angles, which are the advancing contact angle and the receding contact angles, which can be measured and have been measured in the past, and also a parameter u theta, which is not necessarily very physical. It has units of velocity, and it gives an idea of how, let's say, modulated is that change. So this work has consisted on many tests and simulations comparing the two methods, of which I give a few snapshots in the poster. And the conclusions are that the closest the equilibrium contact angle is to 90 degrees, the results seem to be more consistent. So for the highly hydrophilic case, that would be around 60 degrees of an equilibrium contact angle, the open foam simulations tend to overestimate the contact angle. And to fix that, we propose a few new laws in open foam that should be more physical rather than this mathematical construct that is the dynamic contact angle law, which we leave as new research. But in the case of right angle contact angle, the convergence of the mesh has been proven and the convergence of the different parameters have been shown to be good. And so that result could be transported to 3D simulations, which are more difficult, but that is where the interest lies. So that would be a summary of the work. Thank you.
Thank you very much. So now we'll move to the paper or poster number 5. So I'm calling Ghidaoui. I hope I did not mispronounce your name. Can you set up your mic on, please?
Hi. Hi, everyone. Can you hear me?
Okay, we can hear you. Good.
Great.
Let's start. Well, let me just present the title. So you're talking about settling and rising patterns of microplastics in aquatic system, and it's a numerical study. Your co-author is Shuka Karimpur. We're listening to you.
Okay, great. Thank you. Thank you for your introduction. My name is Ghidaoui, a civil engineering PhD student at York University, Canada. My research focus is hydrodynamics that have a strong relevance to our living environment. It is my pleasure to be here and share our research to you all. Today, I would like to introduce our numerical work on the settling and rising dynamics of microplastic in aquatic systems. As a background to my research, plastic pollution has been increasing exponentially ever since they have been introduced into the industry in the 1950s. This huge increase in the production and usage of plastic leads to their growing pollution in aquatic environments. Microplastic, which is defined as plastic particles smaller than 5 millimeters in size, is resulted from breakdown of larger particles. This microplastic can be transported far and wide by water currents, endangering the organism of many aquatic environments. To predict the transport trajectory of microplastic and mitigate their pollution, it is essential to investigate their settling and rising patterns, as these patterns reveal microplastic's depositional tendency. Because microplastic particles that have been found in nature have a wide variety of densities, sizes, and shapes, they are very difficult to characterize. So far, numerical models on the settling of microplastics are very limited, and they all fall short in accounting for microplastics' complex shapes. Now I'd like to talk about our methods. Our study employs a three-dimensional numerical scheme to simulate the settling dynamics of a single microplastic size particle. The particle is represented in the model as a cavity with a predefined shape, density, and moment of inertia. An overset mobile mesh method is employed to capture the particle shape and the fluid motion surrounding the microplastic sized particle. As shown in Figure 1, the computational domain consists of one set of coarser background mesh with uniform mesh size, shown as the yellow zone in Figure 1a, and a finer refinement mesh surrounding the particle, shown as the red zone in Figure 1a. The flow evolution within the refinement zone is calculated according to the refinement mesh, whereas the flow evolution outside the refinement zone is computed through the background mesh. The particle is settling in the downward Z direction. Figure 1b shows the setup of the refinement mesh zone, which always move with the same speed as the particle. In the refinement mesh zone, the mesh refines progressively towards the particle, which is marked in the zoom-in view of Figure 1b. With this setup, the mesh adjacent to the particle is finest, so that the intricate flow patterns around the particle can be captured. The model numerically solves the flow velocity and particle position during the settling of a predefined microplastic particle. Preliminary results suggest that drag coefficient associated with the settling velocity of negatively buoyant microplastic of spherical and cylindrical particles are dependent on the particle's Reynolds number. Figure 2 shows that preliminary results from our study for perfectly spherical particles, which are shown as red dots, are consistent with the experimental data for sediments, which is shown as the black line. The present model is also applied to microplastic particles with complex shapes, like thin cylinder. The top right figure of figure 2, which is the velocity magnitude of a settling thin cylinder in XZ plane, demonstrates how the flow dynamics of complex shaped microplastic is simulated through our model. Our model is shown to be capable of simulating the settling dynamics of microplastic sized particle near their upper size limit, that is 4 millimeter. Our research will be extended to parameterize microplastic particles with various irregular shapes. This will be essential to create an accurate large-scale model for the prediction of the fate and transport history of microplastic in natural aquatic environments. Thanks all. That's all. Thank you for your attention.
Thank you very much.
Thank you. Now let's start with the sixth presentation. Felipe Rezende is here.
Hello.
Hello. Are you here? And this presentation is about hydrodynamics of floating vegetation in lateral cavities, and the authors are Felipe Rezende da Costa, Luis Eduardo Domingos de Oliveira, and Johannes Gerson Hansen.
Hello. Can I start? Hello, my name
is
Felipe.
Please.
My name is Felipe Rezende. I'm a graduate student in the Universidade Federal do Mato Grosso do Sul, and I will present the research effects of floating vegetation in lateral cavities. This project focuses on studying the reservoir zones, more specifically through lateral cavities that can be formed naturally. From the environmental point of view, the reservoir zones play the role of fauna because they absorb part of the energy from the flow. And with that, they provide the rotation of sediments, the protection of the riverbank, and refuge for organisms that develop in calmer water. In the field of study of vegetated flow, we want to understand the hydrodynamics interaction between the flow and the vegetation. But when we study cavities vegetated, it's a recent topic. But when there is vegetation inside of the cavity, the vegetation provides an additional rotation from the resistance to the flow. So this impacts the distribution of velocities inside of this reservoir zone. So we want to understand the effects of the floating vegetation's depth on a reservoir zone to benefit the surrounding ecosystems. To do so, we use CFD. So the first step was to set geometry. The geometry consists in a main channel with a lateral cavity, and it was based on an article of Xiang et al. From 2019. After that, we set the mesh values that were calculated previously. The next step is to set the boundary conditions from the free surface domain and the longitudinal XZ plane located at y equals to 0, we define as a free slip surface. The plane that cut the left portion of the channel and the bottom was set a zero velocity wall. The inlet received a velocity profile previously developed, and the outlet received a zero gradient condition. To simulate the vegetation, we used a porous media model because it's a simple way, but very effective to represent the vegetation resistance. To calculate the values from this to the poral zones, we use the Darcy-Forchheimer model, in which the vegetation density remained constant, and on the depth of the vegetation varied. We use the same density data from the second case of the same article of Xiang from the geometry, where the density is equal to 0.1332%. The simulation was run in the open phone, and we need to set a table with the list of the case and the values from the viscosity drag and coefficient and initial coefficient, because we need different values to have the same density, because there are difference in the depth on each case. So even with the different values, they have the same density. After that, we need to validate the simulation, and to validate, we use a full vegetated cavity that is the case 1 from our research, and it's the same case from the article of Xiang. The results, we note that the floating vegetation reduced the velocity magnitude inside of the cavity, but in the cases where the ratio between vegetation height and the channel depth was less than 0.6, there was an increase in the velocity in the region close to the cavity entrance. However, we noticed that the cases with deeper vegetation, the values from the velocity were slower inside the vegetated area, but in the non-vegetated area, there was no effect. They are almost the same. And as expected, the flow inside of cavity becomes lower compared to the main channel. But when we analyze the contours, we see that there will form an anti-clockwise vortex inside of the cavity. This happens because the entrance of cavity creates a shear layer, which leads to formation of vortex, and they are carried to the inside of the cavity. Furthermore, in the vegetated region, in all the cases, the center of the vortex was more to the right in the x-axis, which is the direction of the flow, and closer in the y-axis, closer to the cavity entrance when compared to the non-vegetated area in the same case. So in conclusion, it was possible to verify variations in the hydrodynamics characteristics inside of the cavity depending on the depth of the floating vegetation. And with this knowledge of patterns and behaviors, the implementation of floating vegetation inside the cavity can be better implemented, as in projects that envisage the use of floating vegetation in narrower zones, such as protection of the riverbank or transversal heterogeneity on the channel. And that's all. Thanks for your attention.
Thank you very much. So now it's time to call Stefania Sansone.
Hi, can you hear me?
Yes, we hear you fine.
Okay.
So your poster is titled The Numerical Modeling of Rock Ice Avalanches in the Hyperbolic Range. And you have no co-authors, so we are listening to you. You can start.
Thank you so much for the introduction, and hello everyone. I'm Stefania Sansone, a PhD candidate at the University of Trento. In this poster, I will show you part of the research conducted under the supervision of my supervisors, Professor Giorgio Rosati and the researcher Daniel Zugliani. And this poster focuses on some numerical results conducted for a rock ice avalanche model that we proposed in a paper published recently. Rock ice avalanches are three-phase free surface flows characterized by three phases: rock ice and a liquid, and whose flow dynamics is affected by the ice melting process, which continuously supplies water to the mixture. The mathematical model that we considered corresponds to the one-dimensional depth-integrated partially isokinetic rock ice avalanche model, and treats the mixture as composed of three phases, rock, ice, and the liquid, that move with two distinct velocities, one referred to the overall solid phase and the other to the liquid phase. For this reason, in this way, the mathematical model in the one-dimensional case is composed of 5 partial differential equations, and more precisely of 3 mass balance principles and 2 momentum balance principles, one referred to the overall solid phase and the other to the liquid phase. An important step for the computation of numerical solutions corresponds to the computation, to the detection of the mathematical nature of the equation system. This was achieved by computing the characteristic polynomial of the equation system, and which is very, very complex, and is composed of 2 parts. The first part is lambda minus US, and the other part is a 4th-degree polynomial in lambda that I put in the poster a plot in figure 1b. By computing the solutions of this characteristic polynomial, it is possible to detect the eigenvalues whose trends as functions of the liquid free number are reported in figure 1a. It is important to observe that in a specific range of the liquid free number, we can notice a region where 2 lines do not appear inside the plot, and this means that we have a loss of hyperbolicity, which is induced by the fact that the local maximum of the 3rd-degree polynomial in lambda that appears inside our characteristic polynomial tends to have negative values. That is to say that it tends to move under the abscissa axis. For numerical and analytical purposes, it is important to try to investigate, to try to define the values of the liquid free number at which corresponds a change in the nature of the equation system. That is to say, where we observe the limit of the region where we lose the hyperbolicity. And these can be performed by considering the characteristic, by considering the plot 1b. In particular, the mathematical expressions cannot be derived analytically because of the complexity of the characteristic polynomial, but it is possible to derive approximated mathematical expressions by approximating the local maximum of the 3rd-degree polynomial in lambda with a value of lambda equal to the mean value between the liquid and solid free number. In this way, we derived the mathematical expressions for the liquid free number that delimits the region of the non-hyperbolic region, and these mathematical expressions are reported in the central part of this poster. And we tried, in order to understand if these mathematical expressions are able to represent effectively the realistic limits of the non-hyperbolic region, we compared the mathematical expressions with the exact ones derived starting from figure 1a. In figure 2, there is this comparison. It is possible to notice that there is a good agreement between the different limits, between the approximated and the exact limits of the non-hyperbolic region. Considering these mathematical expressions for the limits of the non-hyperbolic region, we computed then analytical and numerical solutions. With regard to the analytical solutions, we considered the uniformly accelerated flow, which was derived starting from our mathematical model and by neglecting the terms associated with the ice melting process, that is to say, the terms that are denoted by the symbol epsilon I. And we consider as drag stresses the closure relation proposed by Pittman and Lee. This analytical solution is characterized by phase concentrations that are constant over time and space, and by phase velocities that change exponentially over time and reach a constant value at a dimensionless time equal more or less to 4. With regard to the numerical solution, we implemented the numerical scheme proposed by Zuliani and Rosati. This numerical scheme is a finite volume method with Godunov fluxes and is a modified version of the Osher-Riemann solver proposed by Toro and Lumser. This is a second order of accuracy in time and space numerical scheme. And in figure 3, we can notice a comparison between the numerical solutions identified by dots and with the analytical solutions which are denoted by solid lines. By computing the relative errors, we can notice essentially that the numerical scheme chosen is able to detect the analytical solutions, and essentially we can also observe that the numerical scheme can solve accurately with small relative errors also the equation system. So in conclusion, we derived mathematical expressions for the limit where the hyperbolicity is lost. And thanks to these mathematical expressions, we were able to be sure that our numerical solutions and also the analytical solution stay in the hyperbolic range. Thank you so much.
Thank you. Is Claudio Iuppa here?
Yes.
Yes, okay. Let's go ahead with the next presentation. The authors are Claudio Iuppa, Lilia Carlo, Enrico Foti, and Carla Faraci. And Claudio Iuppa is presenting optimization of CFD numerical model for the analysis of a combined caisson. The floor is yours.
Good afternoon, everyone. Today I want to talk about the experimental numerical campaign that we have done in order to study the behavior of a composite caisson. The aim of this project, of this work, is to provide a tool in order to estimate the wave attenuation due to this type of structure. As can be seen from figure 1, this structure is composed by a caisson and is filled by a rubber mount. In order to simulate this structure, we used the software OpenForm. In particular, we used in order to simulate the interaction between the wave and the rubber mount, we used the toolbox Olaflow. This toolbox is based on the volume average, Reynolds average Navier-Stokes equation, which, however, required the calibration of some coefficient. In this case, referred to the question 1, are the coefficient alpha and beta. As regards the coefficient C, a constant value can be considered. The calibration of these two coefficients was performed on the basis of the data obtained in the experimental campaign that we have done at the hydraulic laboratory of the University of Messina. Here, the model was reproduced in a scale 1 to 14, and several wave conditions were simulated. The elevation of the free surface was measured in 3x3 wave gauge, and then the output data was processed using the method proposed by Mansard and Fug. And for each test, we estimate the reflection coefficient. This setup was reproduced partial identical in the numerical model, and in this case, we try to test different value of the coefficient alpha and beta. And also in this case, for each case, we estimate the reflection coefficient. In the figure 2 is shown the comparison between the results of the numerical model and the experimental campaign, but also the results estimated using the method proposed by Faraci was used, which is the unique relationship to predict the reflection coefficient for composite caisson. As can be seen from this graphic, the method for in the x-axis is show the dimensionless wave number, and for value that are smaller than 1, the different source provide the same or similar trend. While for the value greater than 1, it's possible to observe a different underestimation of the predicted method proposed by Farage. In particular, we estimate a root mean square equal to 0.14 for the empirical relationship, while for the numerical model, we estimate root mean square for the best configuration of alpha beta equal to 0.04. So in conclusion, the variance equation may be used for the prediction of the reflection coefficient for this type of structure, and it provides reliable results also for the case for which the viable empirical relationship provide an estimation. Thank you for your attention.
Right, thank you very much. And now we have a last poster before the coffee break and discussion, and it is Surrender Bandy. Are you with us? And can you speak?
I'm audible, sir.
All right. So you're going to talk about numerical analysis of erosion rate around a cylinder surface. And you did this work with Anuj Kumar and Anant Kumar Rai. So we're listening to you if you're ready.
Okay, thank you for the introduction, sir. My name is Surrender. Presently, I'm pursuing my MTech from Native Warangal. Title of my project is Numerical Analysis of Erosion Rate around a cylinder surface. The aim of this project is to study numerical flows of air and water around a vertical cylinder to understand the flow behavior around bridge pair. Bridge pair are a type of substructure that support the main structure of a bridge. One of the main reasons for bridge failure is bridge soak, which means removal of sand around the pairs. As shown in figure 1a, geometry with cylinder wall, which act as an obstruction to the flow in a dirt is modeled, and the simulation study is carried out using ANSYS Sphere 19.2. The methodology we followed are water is taken as a continuous wave with inlet velocity, pressure outlet, and mostly boundary wall condition is applied to duct walls and cylinder surface. Discrete phase model DPM is used to model solid particles suspended in the fluid. To solve the Newton equation, a structured mesh with 2.08 million elements has been developed. Moreover, inflation layers are also added around the cylinder surface to study the boundary wall effect, which is shown in the figure 1b. Result part, as shown in figure 1d, the magnitude of erosion rate on the cylinder surface is more on the inlet facing surface compared to the outlet facing surface. This is mainly because of the swirl flow and velocity reduction at the rear side of the cylinder. As can be seen in the figure 1c, the solid particle behavior on the cylinder is shown in figure 1e. This also confirms the high erosion rate in the front side of the cylinder. Now, I want to conclude that erosion study has been carried out around the cylinder surface. The initial result of the study has been presented here and found that the surface susceptible to be eroded the most has been the surface facing the inlet side. These are the initial results, and we are planning to explore the study further to optimize the shape of the geometry to reduce the erosion around the bridge pairs. Thank you everyone.
Thank you. So now it's time for a coffee break. Claudia, would you like to introduce this part, or would you like me to do it?
So you prefer? Well, I introduce this part. Yeah, during this coffee break, we can ask questions to the presenting authors. You can use the question and answer box. This is for the people attending this session, or also the presenting authors can ask questions. Is there any question for the posters that were presented from the speakers or from the participants to the session?
I do have questions, by the way, but
yes, please.
I don't want to. Well, I can speak first if you like.
Yeah, yes, please.
Okay, let me ask a question to. Let me find again the title of this poster. It was the one on floating vegetation. So it's a question to Felipe Resenta da Costa, right? And I would like to ask you a question about the model you have chosen for the porous behavior of the vegetation. You're talking about Darcy-Forchheimer model. And my experience is that it is necessary to go up to this model to properly represent the flow within densely packaged vegetation. So I'm not surprised that you needed Darcy-Forchheimer model, but can you say a few words about the values of the parameters that you found and how you found them? By calibration against measurements? I'm talking about the two coefficients in the model. You have one coefficient, which is the Darcy coefficient or hydraulic conductivity, and you have a similar coefficient in front of the second term, which is the so-called Forchheimer term.
The first step was to set these values to match the real case from Xiang. So we made the calculation that we have to use the volume of vegetation, the number of hots, of steams. So we use the case number 2 from his article, and in this case there is a full vegetated cavity, and it was the same conditions from the case number 1. And we validated this case using our numerical case in cooperation with the real experiments of Xiang, and we needed to change the depth of the vegetation, and this value influenced the parameters from the Darcy-Forchheimer, because we need to set the volume of vegetation and the volume of the cavity. So the volume of the cavity is the same from all the cases, but the volume of vegetation is different. So the values need to be different to have the same density of the real case, but we set a case that is equal to the real one, just the partial, the cavities that are not fully vegetated are truly simulations.
Can you, I guess you did not give the values of these two coefficients in your paper, did you?
I did.
All right. And the paper you're talking about as a reference is also referred to in your paper?
Yes.
It is Jackson?
The value that has the density and the real case is the Xiang's one.
All right. And so if I want to learn about the test cases that you mentioned, I should read Xiang's paper, right?
To know the case and to know more about the porous zone and the Darcy-Forchheimer is the Oldham and Sturman, and there's
all right, thank you.
Both of them are in my article as reference.
Thank you.
You're welcome.
So please ask any question.
Yeah, there is a question. There is a question. I read the question. You can check the question an answer box. It's from Michael Nones to poster 40, the 5th presentation, to Zhao. And the question is, you suggested that your approach can be used for large-scale transport model. Can you explain a bit more? What is the computational load for this 3D model, and how can you extend to simulate larger regions? So,
okay, I'm here.
Okay. You can.
I saw the question.
Yeah,
I saw the question. I saw the question. It's a very good question. I mean, by the way, what I mean by extending my small scale model to large scale model is is by parameterizing is from the small scale model, which resolve the actual shape of the small microplastic particle, and I get a parameter, and I use this parameter to build large scale model, which this small scale is a small scale model because it has to resolve the complex shape of the actual microplastic. It's very, very time consuming. And for large scale model, if I have the parameter available, I could assume that the particle I could ignore the shape of the particle and just use the parameter I obtained from this model, from our model. And the reason the good thing about our model is that microplastic has been shown to have very different parameters than natural sediment, which has already been studied and already been parameterized, and these parameters have been used for sediment transport model, and that model is pretty, it can even be two-dimensional. It's pretty straightforward. It runs relatively fast. It has been well established, but this establishment is not true for microplastic, and that is the purpose of our model. For the actual runtime is, as I said, it's very time consuming for a single run, for the run of a single microplastic particle until I can get the terminal saline velocity, which means that the force reaches a balance. It takes around like 4 days to simulate. Okay, that's my answer.
Well, thank you for your answer. And by the way, I can see that most of you have set up their cameras on, which is a good idea for discussion. So if the others can do the same, that would be great, if you can. Is there any other question? I can't see any new question in the panel, in the window. That you can also ask by raising your hand. If there is not, I can also ask a question to Stefania, if you like. And it was interesting to see your work, but it was not clear to me what are the origins of your equations, and why do you have 5 equations? I can remember that it looks like the shallow water equations, or depth average equations, where h looks like the depth of the avalanche, the local depth. But there are other notations that I could not read, actually. Can you elaborate?
Okay, we have 5 equations, essentially because we have, so the system of equation is composed of 5 equations. 3 of them are related to the 3 mass balances, related to the 3 phases, that is to say,
which are rock,
ice,
water.
And the water, a liquid phase. It's much better to talk about liquid. And then we have the momentum balance principles related to the phases. But we introduced in the reality, we should have 3 momentum balance principles. But we introduced an assumption that is the isokinetic condition between rock and ice. So we assume that the 2 solid phases move with the same velocity. And with this assumption, we reduce the number of unknown variables from 3 to 2 in the one-dimensional case. And in this way, we can only have 2 momentum balance principles inside our equation system. Obviously, the isokinetic condition is a strong assumption, but we are trying to work on a full model that contains all the momentum balance principles for the 3 phases. But we are far away from deriving it at the moment.
And about the mathematical properties of your system, if I understand well, you would like a model that ensures hyperbolicity everywhere.
Yeah, we are working also on this problem. we are trying to investigate mathematically the problem of the loss of hyperbolicity. We obtained a solution in we relaxed some of the hypotheses contained in the model, and this hypothesis is associated with the depth integration. And we noticed that in this way we were able to extend the region where we have the loss of where we observe the hyperbolicity. So we have a loss of hyperbolicity for very, very small differences in the phase velocities now. We are still far away from solving the problem of the loss of hyperbolicity in the whole range of the liquid frame number and for the whole ranges of the flow variables. But we are working on it, and we are quite sure that in the future more research could be solved this problem.
And can you tell us the name of your supervisor? It's a pity that you did not mention her name.
My supervisor is Professor Giorgio Rosatti at the University of Trento.
All right, thank you.
You're welcome.
There is a question in the chat. I read the question. Is for the last presentation. Numerical model, yeah. What entrainment coefficient and bed load coefficient were used in the calibrated model, and what is the range used in investigation?
It's a question to the last speaker.
The last presenting author, Bandi.
Bandi Surrender.
Yeah, it's a question for you.
Yes.
Should I repeat the question? Did you hear?
You can read it in the chat if you
want.
The solid particles using the diameter of 50 micrometers. It is a deep field model. We are not using any multi-phase model.
I can hear you. Can you repeat?
My voice audible?
We can hardly hear you.
Yeah.
Are you sure your mic is okay? Otherwise, you can try to answer the question in the chat.
Yeah, probably it's better if you write your answer in a chat because you're not able to hear you properly.
You know, I have questions to everyone, actually. So if there are no more questions, don't worry, Claudia. I can.
Yeah, I can ask a question to the presentation, poster 38. That is the fourth poster about cross-validation study of computational methods for droplet spreading. I was wondering if you are planning to compare your numerical simulations with experiments.
No, not at the moment. So what we're doing is comparing the two methods together, but there are no plans for the moment to run any experiments. And well, not to run any experiments on our part. And I think the comparisons that we could do are with some previous results that measure the advancing and receding angles. The problem with that is that we know that our methods and the method that OpenFOAM uses is not very good. It's just mathematical construct. So before that, we would like to do our homemade implementation of a different dynamic contact angle condition that would probably include things like viscosity. We were thinking we should try to do one based on the capillary number, which I think would be much better. That's what is currently implemented. Of course, that we could only do those modifications ourselves due to how the licenses with OpenFOAM work.
Thank you.
By the way, let me see Claudio. Claudio, yeah, I guess there's a small typo in your poster. Instead of delta P in your equation, looking at the units, I guess it should be more like dP over dx. I mean the pressure gradient, not the pressure difference, you see?
Pressure gradient, yeah.
Okay, well, it's just a small comment. Okay, I would like to ask a question to the third speaker. Who was the first speaker? Let me see.
It's me, Maria Rita.
It's you. What is it, the third speaker? Ah.
The third or the first? Excuse me.
No, the third, number 3.
Ah, I'm so sorry. I hear the first.
Number 3 is Pablo.
Yeah.
Yes. So you presented your what? Let me see. I'm not sure. Was it the right paper? Yes. So you did one-dimensional simulations to study LES, in fact. Mm-hmm. And LES to me is more like a 3-dimensional process or model. Can you comment on that?
Well, yeah. Obviously, we are very limited by. Well, we have tested a toy model to try to.
Yes, I understand that. It's nice, yeah, and a good idea to test a toy model, but I was more thinking about not about the relevance of using such a model to start, but you compared your spectra with 2-dimensional turbulence spectra. You know, we have double cascade.
Yeah.
Is there any theoretical results, assuming that, ensuring that this double cascade occurs even in 1D?
Well, it was not a double cascade, it was a single cascade, but it was plotted twice.
Yes, but I mean, you have two ranges with one
okay,
5/3
right.
power
Yeah.
law and one -2 power law. Right?
This is because it was divided by the forcing term of the Burgers turbulence equation.
Okay.
Yeah. So the left part is where the forcing term is applied, and the right part is where it is not active.
Okay, I see.
Yeah, and yeah, there is a theoretical energy cascade for 1D problems, and another 2D problems, and another one different for 3D problems. And this one is not related to the one with 2D problems, because I think in 2D problems there are 2 ranges. One to injecting by injecting energy, and
that's why that's what I call double cascade. So here it's not double cascade.
No. This one is not related to.
But it was expected to have the tail in k to the -2, was it?
Yeah.
Okay.
Mm-hmm.
Thank you.
I have a question for the 6th presentation about hydrodynamics of fluid vegetation and lateral cavities. Can you comment a bit more? How did you model this? Because in a presentation you mentioned that the vegetation was modeled by a porosity. I don't know if you can give some more details about how did you model this vegetation?
More details. Well, when we set up, it's a method that's used. It's a method to use the pore zone because we need to simulate the resistance caused by this vegetation, and to do so, we can, for example, put set small objects inside of inside of the domain, but we need to have a mesh that is too heavy to be processed. So we set a condition of pore zone. So where we have different depth of vegetation. So from each case, we have pore zones only on the vegetated zone, because the porous zones simulate this resistance and the effect in the flow without the necessity of power computational process. But we need to set the conditions based in the real resistance from the vegetation. And I don't know if I'm explaining it very well. I mean,
yeah, it's just to understand, but I imagine in the lab how we model vegetation and we vary the distance between the stems and the size of a stem. And I was just figuring out how the porosity can be connected to this real vegetation as it occurs in a real case.
Yeah,
in terms of spacing, density, no? That's it.
Yeah, to set these values, we need to calculate using, for example, cylinders, but it's only in the process of calculation the Darcy-Fortheimer parameters. But so we set, for example, a number of steams and the value of the cavity that will be vegetation and not vegetation. Like inside of the vegetated region, we have small parts that have vegetation and other ones that don't have. So when we use the pore zones, we set these values that we calculate, assuming the density that we want. So these values will set in rotation of the energy from the flow.
And also with your presentation, I'd like to know if you are you planning any experimental validation of you, or if you you don't have to run experience, but you have any experiment already performed that can be used for validation of your.
The validation was made using the Xiang case and in the Xiang articles. This case was experimental. It was set an experimental example. So we used the real case to validate our computational case using the case from Xiang and all from 2019. So it was validated using an real case and experimental case, but the experiment wasn't set by me.
And you already validated this.
Yes.
These experiments, but didn't you show it in the poster, right? Because in the poster,
yeah, in the poster,
you have only cases with or without, but only numerical comparisons of two different numerical cases.
Yeah.
Okay. Okay, thank you.
You're welcome.
Yes, Jose told me that we have someone who raised his hand or her hand in the chat, but I can't see it. Jose,
yeah.
can you?
We can allow him or her to speak. please just open your micro and ask your question.
Who was it?
It is in Chinese or in...
Ah, okay, I see. Well, there's a Chinese person on board who raised his hand or her hand. So can you, if you're here, can you switch on your camera and mic, please, and ask your question? Okay, sleeping apparently. So let's go on and ask your question if you like. Or if you don't, I can continue asking questions. I would like to ask to the author of the second paper, second poster, who was the second? Wasn't it Stefano?
I think it was me, yes.
Yeah. You presented a model which seems to give quite good results, but what is your, what did you develop? If you developed something, or did you in-house code or commercial code?
Okay, is an in-house implementation of LBM model. The model was developed by Andrea Montessori, is one of the reference of the paper. And I only, let's say, tune the model in order to be able to simulate what I needed. So, for example, I changed something on the boundary condition, and I tuned it like the short range repulsive force. But yeah, was in in-out implementation. So we wrote the code. We wrote the code in Fortran.
Okay. It was not clear in your poster. That's why I'm asking. Also, I have a question for the speaker number 4. And I guess it was Juan.
Yep.
Are you with us? Yes. Can you tell me whether you, well, did you think about using particle methods to do what you did? Because I know it's commonly used in droplet spreading.
Or, by particle methods, you mean
Lagrangian method.
Track the interface?
Not necessarily. I mean, numerical models based on a set of material points or particle moving all together. Like
yeah,
SPH.
Yes, we thought about that, but we did a balance between. We thought that would be less costly, computationally speaking, but we thought that it would be more inaccurate as well. So at the end, we used the diffuse interface method and the volume of fluid method with the angle law, which are interface tracking methods.
I can understand the question of time. I mean, the CPU time. You're right that particle methods are significantly more costly, but the accuracy now is the same order of magnitude as finite volumes, even for that kind of applications. But you're right, it's longer. So,
okay.
And you used OpenFlow, is that right? Yeah. Okay.
All right, but well, anyway, thanks for the suggestion, and perhaps we'll look at that in the future. But we have a long list of things to look at.
I also have a question for the speaker number 5. And this was Gie.
Yes.
Did I pronounce your first name correctly?
Yes,
right.
Correct.
And yes, you were talking about settling of small pieces of plastic.
Yes, settling of microplastic shaped particle.
Settling is a nice thing, but if you refer, for example, to sediment transport processes, you know that the motion and behavior of those particles of matter in water is driven by settling due to gravity, but also to diffusion due to turbulence. Do you have any idea about the response of such small plastic pieces due to turbulent motion?
Yeah, I know there's some research about, the setting of a microplastic shaped particle in eddy waves, but my research is mainly the setting of particle in transient fluid. Well, as the same with the last speaker, the model is already sufficiently complex. And the reason of this model is just to set up some parameters, in particular drag coefficient for large scale models to predict the transport of microplastic. Yeah, in terms of eddies, in terms of the settling in turbulent fluid, I can imagine it could be more the weight of the microplastic, which varies a lot, could be more influenced by fluid turbulence than natural particle with larger size and denser and greater density. That's as far as I know.
Okay.
I think we should close this session because
it is yes, we are a little bit late. Excuse me. And maybe Claudia, would you like to say a last word to acknowledge everyone, or would you like me to do it?
Yeah, I can say a few words, and you can do the
Okay,
same.
please go on. Please go on.
Yeah, and I would like first to thank you all, the author representing author, for their contribution, and all the posters were very interesting. We analyzed several problems spanning between droplets, microplastics, recurrence, and rock ice avalanches, and presentation we're dealing with different methods, numerical simulations, and laboratory experience. And yeah, I wish to thank you all for your interesting presentation. I don't know if you like to add further words, Damien.
Well, I have nothing to add, except thank you again to everyone, and enjoy the rest of the Congress.
Yeah.
Thank you, Claudia.
Thank you, Damien. Thank you all.
Thank you very much for this interesting session. A pleasure.
Right. So we say bye-bye, and you're supposed to manage the transition to the next session, I suppose.
Yeah.
Okay.
Yeah, thank you.
Thank you very much,
Claudia.
Thank you, Jose. Bye.
Thank you.
Thank you.
Okay, hello everybody. We are going to start with the session number 3, and that in where we are going to count with Silke Witter from the University of Stuttgart, and also with Neil Ruther from the Norwegian University of Science and Technology. And they are going to be the chairs in this interesting session. Silke, Niels, the floor is yours. If you want to make a short introduction of the session, please.
Okay, so hello to everybody. Thank you very much, Jose, for the introduction. And yeah, it's nice to see you all here on the second Young Professional Congress. And we are opening a session on fluvial hydraulics and reservoir sedimentation. And it's my pleasure to be the one sharing with you together the presentations and also leading the discussion. And I'm happy to have a co-host, which is Niels Ruther from NTNU in Trondheim. And Niels, maybe you want to say some words in the beginning, and then I start for the introduction.
Yes, no, nothing more to add from me. I'm just happy to be a co-chair here and to join this session and to listen to all these nice contributions. Thank you.
Okay, so then I would suggest that we just start with the interesting posters and discussions. I went through all the presentations and the abstracts that I could read, and I see that we do have a wide variety. On the one hand, in terms of different areas. So we have the first presentation starts in Poland, and we also have presentations about topics in Uruguay and in Peru, but we also have a wide variety of different topics. So on the one hand, like a bit interesting topics about hydraulic structures, like the piano key weirs, dam constructions, pier constructions, veins, and also about sediment transport. And it's about using different approaches in hydraulics and in morphology, like hydromorphological dynamics and its modeling, as well as experimental modelings and field and data analysis. So I'm very much looking forward to the presentations. And the first presenter will be Camila Cavallo, if I got this right. So I realized that Camila will give the presentation, and you already see it on the screen. It's about Sentinel-2 derived hydromorphological dynamics of reach of the Vistula River in Poland. So Camila, the floor is yours.
Thank you. Good afternoon. Thank you very much for your introduction. I'm Carmela Cavallo, PhD student of Salerno University. This work is in collaboration with Professor Michael Nones of Institute of Geophysics, Polish Academy of Science. In this work, we used the Sentinel-2 multispectral satellite images to observe water, sediment, and vegetation dynamics of a reach of the Vistula River in Poland. In particular, we developed a Google Earth engine script to evaluate changes in vegetation, presence of water, and turbidity using NDVI, NDWI, and NTDI multispectral indexes. The preliminary results show that one can expect, normalized different vegetation index is minimal during the winter months and reaches the maximum values during the summer. On the contrary, the presence of water and turbidity increase when the influence of vegetation is lower. Comparing the indexes with the monthly discharge measurement at the upstream of the studied reach, we can see a time lag between high flow condition and peak in turbidity and water content. So we can conclude that multispectral satellite images and Google Earth engine has a great potential to monitoring river dynamic at a high space-temporal resolution. As future developments, we plan to implement further multispectral indexes and hydraulic analysis with the aim of providing water managers with useful information of past trend and future evolutionary potential. We also analyze the hydrology at the daily scale to see if more variation of the indexes are visible. Thank you very much for your attention.
Yeah, thank you very much, Camila, for your presentation. Very interesting.
Thank you.
Yeah, I think we have some discussion time. No, we just proceed with the next presentation.
We proceed.
Yes.
Exactly. That's what I wanted to add. Maybe please write your questions in the question and answer field here. Maybe not in the chat, but use the question and answer field, and then we will discuss all your questions after the presentations. Thank you.
Okay. Yeah, I was just a bit irritated because there were some minutes left for Camila to talk, and therefore
No, I think we have time. Yeah.
Yeah, exactly.
That's good.
Mm-hmm. Good. So then we proceed to the next presentation, and I think it's Mohamed who will present. At least I saw him in the attendees list, and he will talk about the topic here, or his topic. His presentation is titled "A Review for the Piano Key Weirs hydraulic characteristics between modeling and modified based main and auxiliary geometric parameters. So Majid, it's yours.
Okay, thank you. First of all, good day for, or good afternoon or good evening for chairs and for conference meeting. Our article about a review for the piano key weir, hydraulic characteristics between modeling and modified based main and auxiliary geometric parameters. So the novel technique of hydraulic structures, PKW, piano key weir, is primarily confident and dispersed. So the available gaps must be comprehended in this field of research to provide significant insights into experts and assist researchers in getting them. As a result, a review is done depending on 4 explorer databases. So first of all, when we first about methods, piano key weirs and the PKW and its applications in spillways is the most essential keyword in this study. It had been a restricted study to English literature, although it had taken into account all PKWS spillways, I mean piano key weirs, to find the target articles. 4 digital databases were combined there through, first of all, Web of Science and Science Direct and IEEE Explorer and Scopus. Also, it was looked at Google Scholar and other websites. These databases adequately cover piano key weirs and their application in spillways, as well as provide a thorough overview of current research in a variety of disciplines. A literature search was conducted first by filtering and the screening of about 3 iterations. A literature search was conducted first, followed by 3 iterations of screening and filtering. All unrelated articles were deleted in the initial phase of screening and filtering. Duplicates and irrelevant articles were deleted in the second iteration by scanning the title and abstracts. The full text articles screened in the second iteration were carefully evaluated in the final iteration. The author quality criteria were applied to the iteration steps as shown in the figure number 1. So about results from this technique, we show or we draw or we make a taxonomy. So as shown in figure 2, the taxonomy in this work, for example, show how groups of developing, modeling, and modified receive disproportionate attention in review and evaluation as evidenced by the performance of their categories at the experience of integrated solution and frameworks. The taxonomy of modeling studies in the current work, for example, suggests that the academics are more likely to propose frameworks for developing and operating piano key weirs using modeling, in addition to highlighting the lack of studies on the development of piano key weirs by focusing on auxiliary geometry parameters and comparing the results to those relying on the main geometry parameters. And the last, the taxonomy also highlights the lack of the studies on the development of piano key weirs by focusing on auxiliary geometric parameters when using the nonlinearity of geometric for this parameter. In conclusion, the findings show that it is hypothesized that perpetuals may aid in the enhancement of the piano key weir function. Most of the prior research has focused on rectangular piano key weirs of type A. Furthermore, studies have paid a little attention to the impact of the parapet walls, nonlinearity, and in comparison to other linear parapet walls. Upstream water level flow condition, the arrangement of the nonlinear parapet walls, installment, and the discharge coefficient of piano key weirs to assessment to optimum performance. The development of the piano key weir is based on the modification of the main, the cross-sectional shape and secondary parameter nonlinearity parapet wall. At this, I'm done. Thank you. I will happy if there are any notes. I hope to answer in the QA chat.
So Vachit, thank you very much for your presentation, and thank you very much for keeping the time very exactly. This gives us enough room for the next presentation, which will be given by Chang Li. And Chang Li will talk about a study on the hydraulic geometry in different hydrological periods based on one-dimensional hydrodynamic model. So Chang Li, the floor is yours.
Hello, everyone. Could you hear me and see me?
Yes, we can hear you and we can see you, but your presentation is not yet on the presentation mode. You are still on the working mode in the PowerPoint.
I click it. Okay. Good morning,
now
good
it looks
afternoon.
Good.
Okay, thank you. Good morning, good afternoon, and good evening, everyone. I'm Li Chang. I come from the State K Laboratory of Hydrology, Water Resources, and Hydraulic Engineering in China. It's my great pleasure to share my work online with all experts around the world. The topic of my presentation is the study on the hydraulic geometry in different hydrological periods based on one-dimensional hydrodynamic model. As we know, hydraulic geometry is one of the main ways to research river bed evolution. Its application in waterway of the Xijiang River could make predictions about the evolution and developing trend of the ridge. It also provides a reference basis of systematic management and development in waterway regulation planning. However, there are relatively few studies on hydraulic geometry and river bed stability during different hydrological periods when there is a lack of scoring and silting data for such a fine ridge as Guiping Wuzhou of the Xijiang River. The fine ridges are in a dynamic water and sediment dynamic balance for a long time and should have a stable hydraulic geometry. There have been some imperial hydraulic geometries in plain rivers where there are a few studies and application of alluvial rivers in mountainous areas. In my study, a one-dimensional hydrodynamic model was established for Guiping Wuzhou Ridge of Xijiang River, and the method of selecting fine ridge and establishing hydraulic geometry was analyzed and discussed, which provides a reference for waterway regulation planning. I selected the Guiping Wuzhou Ridge as a study area, which is located in the lower reaches of the Xijiang River, China. The total length of the Guiping Wuzhou Ridge is about 186 kilometers. And the sediment in the Guiping Wuzhou Ridge mainly comes from the upstream of the Hongshui River. The river bed is composed of clay, limestone, sandstone, etc. The riverbed is mostly bedrock and pebbles, and some areas are covered by sand. The annual sediment content is only 0.385 kilogram per cubic metric at Wuzhou hydrological station. However, due to the abundant water discharge of the Xijiang River and the large amount of suspended sediment transport, it has become the river with the largest sediment load in Guangxi province, China. In the study, the hydrodynamic model is based on the invariant equation. The continuous equation and the boundary condition are shown as follows. The river width and average water depth of each section was simulated by using the established one-dimensional hydrodynamic model, and the hydraulic geometry of each section was counted. And during the low water and mid water periods, the hydrologic geometry generally showed a downward trend from upstream to downstream. In the lower water periods, the diameter of the most section were less than 1.20, except the sections near Guiping hydraulic project upstream. It shows the river section was generally narrow and deep and was not easy to scour. In the middle water period, the diameter of each section was between 0.35 and 1.01, indicating the section tends to be narrow and deep. Besides, the river section was not easy to scour, and the riverbed material was more difficult to be disturbed than the riverbed material. In addition, the symmetrical of downstream near the Changzhou was relatively stable, and the navigation conditions of the channel were better than those of other reaches. Well, as for the conclusions part, the one-dimensional hydrodynamic model established in this study can better simulate the basic river data such as river width and average water depth. At the same time, hydrologic geometry with power function significance under different hydrological periods in the Guiping-Wuzhou Ridge of the Xijiang River were also established from the result of the stable slope coefficient calculated based on the hydraulic geometry. Of the three sections, Guiping, Jiyutan, and Pingnan in the lower water and mid water periods were relatively large, and the river band were relatively unstable and easy to scour. The water flow condition in the remaining section of the ridge were better. Okay, that's my presentation for you. Thank you very much.
Thank you very much, Cheng-Li, for your presentation about your hydrodynamic model. And I'm wondering whether there are the presenters in the room of the next poster 111. I didn't see any of the presenters, like Hu Lin Hu Yordi or Arbaiza or Crospoma or Samuel Ismail Quisca Astoka Huana. I'm sure I pronounced the names totally wrong. However, I hope there's any of the presenters here of poster 111, the poster which is dealing about Toma Grande Dam. So I don't see any. That's a pity. I was really looking forward to learn a bit more about this dam and the way how to choose the best option for the different dam alternatives. However, if there's nobody, then I would suggest that we just proceed to the next presentation. And Niels and I, we decided on sharing the announcement of the posters and presentations. And that's the moment where I would hand over to you, Niels, to present the next poster.
Thank you very much, Silke. Then we move on to the next speaker, Lakshmi Narayana, and co-authors on the velocity fields around tandem piers on mobile bed.
Yes, sir. Sir, am I audible?
Yes, we hear you.
Yes, sir. Good evening to one and all. So, myself, Lakshmi Narayana. Today, I'm going to present one of my research topic called velocity fields around tandem piers on mobile bed. So basically, I would like to share what is the flow physics around in single pier and tandem pier. So how the hydraulic engineers will of the hydraulic engineers can use my study. So based on our study, how the spacing of the piers can finalize. So in this in this scenario, so I would like to present some fluid mechanics called streamlines and vector fields I would like to show. So around the tandem piers. So in past, however, many studies are done on single pier, but very few studies are done on tandem or staggered arrangements at different angles. So what I presented is when the flow is approaching to any hydraulic structure, as in when a three-dimensional pattern will develop at the foot of the pier called the horseshoe vortex. So to calibrate this horseshoe vortex, many models has been generated around the single pier, but however in tandem pier or staggered pier it is still missing. So to suffice this problem, my analysis may useful. So in my study, what the observations compared to single pier are 20 to 30% of average velocity has been reduced around the rear pier in the tandem case, which has been validated by using the power spectrum analysis. So the velocity power spectrum reveals around 30% decrease in the strength of the wake vortex behind the front pier and in front of the rear pier. So it is resulted in formation of lesser scour around the rear pier. And from the fluid mechanics point of view, the streamlines and velocity vectors are presented, but the size of the horseshoe vortex. So it has been observed at the front pier, we can have the horseshoe vortex size is large compared to rear pier. So again, from this point of view, also we can say there is a tremendous reduce of scour around the rear pier. So as our studies confirm to only mobile bed, so I'm sorry, our studies confirm to only tandem case. So the staggered arrangement is still I need to do experimentations. So on a conclusion, I can say compared to single pier, tandem piers are very better. Yes, sir. Okay, thank you, sir.
Thank you. Thank you very much, Lakshmi.
Okay, sir. Thank you.
Thank you. I will. We will have a discussion on your presentation later on. I'm looking really forward to that. Then, yeah, we are not so bad in time now, but we can still move on to the next speaker, Alejandro Nardin, with co-authors on the suspended sand load in the lower Uruguay River.
Thank you very much, Professor Ruther. I am here to present this work we have made. We were very happy with the results that we obtained, so this is why we jumped directly to publish some data we gathered. But the key concept of this presentation, I guess, is the methodology we used. So I will stop a little bit, taking advantage of the presence of the Dr. Ruther on the audience, who has some experience on this topic. And well, we work in the Uruguay River because I work in this administrative committee which deals with this reach of the river, which is shared between Argentina and Uruguay. And the lower reach is downstream a dam, which is Salto Grande Dam. And in spite the Uruguay River may be in the 30s of the largest rivers in discharge, it is very understudied compared to other rivers of this size. So we had some contracts of dredging coming on during the 2018 year. And we decided we had to start doing some field measurements to have some idea of what the dredging volumes will be and to compare it with the effective dredged volumes. So we started to look in the bibliography, and we came up with this methodology of using ADCPs to estimate the suspended sediment load. And since we had a ADCP Sontec M9, and we were in contact with Ricardo Suppiani, who has a very well-developed methodology of using RDAs ADCPs from the Teledyne brand, and we tried to use somehow use the M9 to get the same results. But since there's no published data from M9, considering all the terms in the so-called sonar equation, we had to come up with some sort of methodology to get all these terms we didn't have to produce the same results as they get for the Teledyne RDA ADCPs. So we took advantage of the simultaneity of measurements, and with these two combined measurements, we gathered all the other terms we didn't have for the sonar equation, and we somehow reverse engineer it. I say this term, but it's very, very general, but we can go farther if you want. And well, we used this, and we solved the sediment concentration for all the measurements we had since 2014 to 2018. And we gather all the points for constructing discharge rating curves for discharge and for sediment transport, for sediments, for sand concentration, I mean. And since we had these two curves, we could easily use a limnometric value from a near station and convert it to effectively discharge and sediment transport or sediment load. And as we integrated these curves, we got the load or the yield for the year, and we published it in this last graphic we presented, gathering a result of 2 orders of magnitude between the lowest and the highest transport yield in a year. And since 2003 was a El Nino year, it was a very loaded year, and we got this 1 order of magnitude from the mean value in the discharge, in this I mean in the suspended load. So I think I was very happy because this was the first time we have some data like this in the Uruguay River. I think this threshold behavior I speak in the conclusions, it is a little bit we observed during some morphological studies in the area, but it is somehow reflected on this load calculations. And well, since there was no data, the previous data in the area, this is very nice work because it is a kickstart for the next investigations we are planning to continue and to do. And I hope we can get better results and adjust somehow these curves to better fit the reality. I mean, this is the closest we are from the reality right now, but we know we can achieve better results in the future. So this is pretty much it. So thank you very much.
Thank you. And also here, yeah, looking forward to discussion with you. Nice. Okay, then we move on to our last speaker already in this session with only 6 contributions then. So we have Saifik Razali on the modeling of the effects of vein on hydraulics and sediment transport in a diversion channel. So please.
Thank you. Okay. in this study, we are focusing on the operational problem associated with branching channels. Water intake increases over time due to sediment accumulation. The sediment accumulate at the entrance of that branching channel. So, so this success of the branching channel project depends on the design that can correctly maximize water discharge and optimize the percentage of the sediment discharge reduction. So meaning that we want the most water discharge, but also the most that has the most optimized amount of that sediment reduction. You want, they can still reduce a lot of sediment. Okay. This study implies that the optimum vein arrangement and the branching angle that will maximize the water discharge and optimize percentage sediment discharge reduction is the 60-degree branching angle. In the 60-degree branching angle, with one row flat vein, because it managed to maximize the discharge by 34%, resulting in the most optimized amount of sediment discharge reduction equivalent to 91.20%. So what we use is a physical model, a sand bed physical model comprised of two main channels. So one is a main channel and then another one is the branching channel. Okay, the main channel is measured by a 12.25 milliliter long, 0.313 meter wide, and 0.6 meter deep. And the branching channel also measured at 2.75 meter long, also at the same depth, 0.6 meter deep. Okay, so as we can see here, based on the we can see here, these are the basically the schematic of what we have done in the lab is in this physical model. So these are the 3D schematic of the model, and these are the exactly the laboratory laboratory where we put in the lab. Exactly. So as a conclusion, we can see that based on the flat vein 60-degree branching angle has among the most highest water discharge ratio. There is about 34% based on this graph, and the flat, you can see the comparison between the flat and the L-shaped vein comparison. You can see that the flat vein with 60-degree branching angle has the water discharge ratio of 34% and the highest sediment discharge reduction of 91.2%. So as we can see here, it's proven that the flat vein with a 60-degree branching angle has exactly managed to have the most amount of water discharge, and then the most optimized of this water sediment discharge ratio. Okay, so that's all from me. Thank you.
Thank you for this energetic presentation. Excellent. Thank you very much. So yes, so we have some extra time actually to discuss all these interesting presentations. So I would like to open the floor for discussion. I thought we will get much more questions. So beforehand, Silke and me decided to go through the papers chronologically. Yeah, I think we maybe switch to open floor and just ask questions to your colleagues. And yes,
there's a
please.
First question in the chat. Which
there was one in the chat, yeah?
Yes, there's one question, and I think it's going to the presentation about the piers. What instruments or data acquisition system did you use to characterize the velocity fields? Was the horseshoe vortex the most important, or did you find any other particular? So I think the question goes to Lakshmi.
Yes.
Yes, exactly.
Yes, sir, I would like to answer. Sir, we during the experimentation, we used an acoustic Doppler velocity meter to record the velocity signals around the bridge piers. And the next question is, was the horseshoe vortex the most important, or did you find any other in particular? Yes, sir. The horseshoe vortex is only the responsible for eroding the sediments. So we need to concentrate more on horseshoe vortex, how to quantify the horseshoe vortex, what is size, what is the strength. So the study is very important if you quantify it. So it will be definitely useful to the hydraulic engineers, so that they will arrange the prayers in a proper way. So this is what I would like to answer.
Maybe I can add a question to you, Lakshmi, about your presentation. So I saw that you had one kind of setting of the piers between the front pier and the rear pier. Did you also make some variations to bring that more on a universal level? So, or is it only this specific setting of size of pier, distance between the piers, and water depth, which gives you this results? Or would you say this is universally applicable, your results? And or how could we bring your results to a more wide application of your findings?
Yes, ma'am. Yeah. So actually, my concentration is how the flow physics is differentiate between tandem pier and staggered pier when the spacing is fixed and the flow conditions are fixed. So
yeah, I know that you have a fixed situation, but how would it be if you go to a different place and your distance between the two piers would be a different one? Or the relation between the size of the piers and the water depth, for example, something like that.
Yes, no. My study will definitely be useful for a rough hydraulic bed condition. All the rough hydraulic bed conditions, my study will definitely use. For the smooth bed, the study will not be useful, ma'am. So this is I would like to say.
Okay, so my question was not about whether we are talking about a rough bed or a smooth bed. It's more on a more general application of your results. You have now a specific setting where you have two piers with a certain distance and you have a certain water level, and this gives you a certain kind of vortices. But how would this change if you have a different geometry?
Of course, ma'am. We need to carry more and more experimentations by keeping the spacings, but my study is confined to only a single spacing. So definitely in future I will carry more and more experimentations at different spacings, so that I can come to conclusion that yes, this is the proper spacing in tandem arrangement. So as far as my study is concerned, I focused only at a particular arrangement. My interest in on arrangement, not the spacing. So at the moment I can't 100% satisfy you that yes, this is the exact application I can say.
Okay.
Yes,
good. So there's still some work to do, which is always good in science, that we have still enough room for new research. Thank you very much.
Yes,
so maybe Niels, you have another question.
Yes, I would like to follow up a bit on that, since you have this really nice vortices between the piers. What was the measurement raster? Was it the huge amount of points you took, or what did it take you to create these nice figures?
Sir, yes, ma'am. Yes, sir. I used MATLAB only to generate these streamlines or velocity vectors. So basically, I interpolated and I generated the data in the MATLAB by adding some coding. So I plotted, sir.
So what was the distance between your two piers?
Yes, sir. Exactly 2 times of the diameter. The diameter is 8.8 centimeter. So at the center to center is
16
2 times of diameter.
Okay.
Yes.
So how many measurement points did you have in between the two piers in the longitudinal wise?
Yes, sir. In between the pier, it is possible only at a single plane. I can take only 3 readings.
Three.
Yes. At different elevations. Again, and I need to take. So all around, I taken around 50 to 60 data points at different locations.
Nice. Okay. Very good. Excellent. Yes. Somebody else more on this paper or on other contributions maybe? But maybe then we can start from the top. I have some questions.
You mean from the top, the first presentation?
Yes, exactly. Yeah. I was wondering the Vistula River. How sensitive you think your data will be? You said you're going to take ground measurements, truth measurements to compare your data with from the EO data. And yeah, I was wondering, do you have an idea on how many different fields or how many different areas you have to take to get a good calibration of the data or validation even?
Yes, thank you for your question. Yes, I used the level of a river to calibrate the information extracted by satellite data. And it's possible to calibrate the results with very high spatial resolution images to effect a comparison with Sentinel-2 images and very high resolution images as true condition to calibrate the results obtained by Sentinel-2.
Okay. But in your outlook, you say that you want to take calibration data or ground truth data.
Ground truth data, yes, it's possible to calibrate with information on the site, but in this moment I don't have ground truth on the site. For this moment, I don't know.
Okay. And do you have hydrology data or discharge data?
Discharge data we have, and but I don't have the possibility to extract by satellite the discharge.
No.
I need to free satellite data to level, but I don't use this data for the moment. It's possible to comparison the results with the high spatial resolution, to comparison wet channel with the true condition on very high resolution images.
Okay. So yeah, before you do that, then in the end you could really go into the process investigation, right? Is that what you want? So what is your goal of the study in the end? Not only to identify these indexes, but the indices, but you also want to study processes, right?
Yes, the aim is to combine information by satellite data and hydraulic analysis with, I don't know, a graph and other software.
Okay, good. Thank you.
If you come to processes, may I add another question? So you mentioned that you have a time lag between the flow condition and the concentration that you could get, or the information on the concentration. So I didn't really see it in detail, or maybe it was too small for me, for my old eyes, to see the time lag, whether you first had the concentration peak and then the hydraulic peak, or was it the other way around?
There are high peak lag time between discharge and satellite observation, turbidity and water contact.
Yeah, but it was first the high peak in discharge and then the concentration peak, what you got from the satellite images, or was first the higher concentration and then the highest discharge?
No, sorry, I don't.
If you have an offset between the two peaks, between the peak of discharge and the peak of the sediment concentration or the turbidity, is first the peak of the discharge and then the turbidity, or was it the other way around?
The peak, the first peak is discharge, and the second peak is turbidity and water contact.
Okay, but usually it's just the other way around, that first the turbidity increases and you have first the turbidity peak and then the discharge peak comes behind that. What is the reason for that, that you have a different observation?
This is important to investigate this problem, this aspect with daily discharge. Quindi comparison daily discharge and the information extracted by satellite data.
Okay, what was
this is a monthly information.
Okay, you mean it comes from the aggregation of your data. So if you had a different time scale, then it would be better or more detailed and more exact?
Yes.
Okay.
There may be a physical explanation. We observed that in one of our project as well, where you have very saturated soil, a very steep slopes, and then after the peak of the flood has disappeared, then the sides collapse, and then they contribute like a plume to the river. But this was a very small river with steep. Yeah,
that's a different process then, because that's the reason why I was asking about the processes, because typically you have the surface overflow, and this brings you the sediment concentration, which comes before the hydraulic peak or hydrologic peak occurs. But if you have that collapse of the banks, then this is something different. Okay, thank you. Very interesting presentation about your satellite image. Thank you for that.
Thank you. Thank you for your question.
So I'm wondering whether there are questions from the audience. So I don't see anything in the question and answer box, and I don't see anything in the chat. So please feel free to ask your questions in the Q&A box, and not only from our side, but also from the whole audience, the whole group of the audience, people listening to the presentations. I'm sure that you have questions.
While you're thinking, all of you, 73 participants, including us. Alejandro, so what was the motivation of using an M9 instead of the RDI? The pure lack of the instruments, or?
Yes, we have already four of M9s. They were bought to measure discharge and not thinking about this, obviously. And well, Ricardo is located in a university 350 kilometers from here. He is my PhD advisor. And so we said, okay, let's try to do it with this instrument. We couldn't get him here to measure every single time. So, and I think one of the best contributions of this work is that you can, once you have established the intercalibration between the RDI and the M9, then you don't need anymore the RDI, because you get the calibration of these acoustic parameters from the cell size, for example, and the acoustic frequency. So you can use the same, I say calibration, but it's not a calibration. It is a calculation of the acoustic parameters for the M9.
Exactly. Yeah.
So you can use them to all the data series you have. So if you have like 300 discharge measurements, you can process the 300 and get all the results from suspended sediment, even though if you don't have all the information. Perhaps there is a difference there, because this equation depends on this sediment size and depends on the fine sediment concentration, but you can get it from the historical values or from something else. I think like a estimation equation like Rusle model or something like that. You can get a value of the fine sediments, and then you can calibrate it.
Okay, but right now your study, your data is only concerned or only valid for the suspended sand, right? For the coarser material. Yes.
Yeah. Actually, the equation that is used in Ricardo's publication and also mine takes the value divided into two categories: the fine sediments and the coarse sediments. Because of the Paraná River and the Uruguay River has somehow more or less the same diameters. I think Paraná River suspended sediment is around 100 microns and Uruguay River is 120 or something like that. The difference is practically negligible in the errors of the results. So you can more or less compare the methodologies. And I think with this separation, you can either have one of those. If you are certain that there is no sand transport, for example, you can attribute all of the signal losses to the fine sediments, for example, and use it that way. Yeah. But we are now focusing on the sand because this is the component of the sediment transport we couldn't have, because we can have measuring from a different methodology, like moving dunes or something like that. We can have the bottom transport or the bed load.
Yes.
And we can have the suspended fine sediments with a simple bottle, but there was no other way we can get the suspended sand.
Yes, but I'm wondering, where is your threshold value between finer and coarser material? Where did you set
62 microns. 62
microns. Okay.
Yeah.
But I'm wondering whether this is really true. If you say, if you make once a calibration for the coarser material and then you get the rest from any other sources, and this is good enough for your calibration. I don't know whether you ever made a real calibration to test this and to prove that your hypothesis that you just put here, whether this is true. Yeah. So from my experience, from the field measurements, and I did a lot of field measurements, it is totally different. You get a very wide scatter and your results are not that precise as soon as you have a scatter and a difference in the grain sizes.
Well, we're actually
if we come to hydrologic interesting event like peak discharges, then you really have coarser material. And then, especially in this case, you would like to have a good calibration, which is then maybe not good enough for your case. What would you say for that?
Actually, I agree with you. We are getting some information from the diffractometry measurements from the sediment to make a better assessment of this topic. But actually, we think we are comparing this information we're getting, like comparing to nothing. So even though we can have one order of magnitude error, it will be better than nothing. So we also are trying to compare this information with the volumes effectively dredged. So we will have somehow like a indirect comparison with the field data from the dredges. So, or from actually not from the dredges, but from the trenches they make and how do they feel. So
how
we
is
have some,
How is the total transport relation here? What is the dominant size? If you talk about dredging now, what is the processes here in this river?
Okay, well, actually, it's a river rather complicated because the dredging part occurs in the ridge. I don't know if you can see no, you cannot see it, but in the middle, which is sort of behaving like a delta there, the river, because it's somehow constrained from downstream from the La Plata River, which varies in height. But from upstream, the dam closes the sediment input. So it is somehow constrained from upstream and from downstream, and the sediment is moving, and the bed load is not as high as you may think. We have measured this from a flood, and in the flood conditions, the bed load is only around 10% of the sediment load, complete sediment load.
Yes,
so
yes.
I don't know if I answered.
And yeah, totally. And then you have, in addition, the finer material. And if we can see your poster again, I'm not sure what the unit was of the two cross sections here. Was it the backscatter, or was it already the calculated?
Yes, it's the suspended. It's the concentration.
It's a concentration already. So it's okay. Okay.
Yes, we do have a question in a Q&A box. So there's one person who asks, how did you deal with the fact that the M9 uses two frequencies and selects the cell size by itself and changes the frequency as well as the cell size by a hidden algorithm by itself?
Yeah, yeah. that will probably be answered in my PhD dissertation, but I will share you the, yes, we deal with it vertical to vertical. I mean, we took the vertical and we calculated point by point all the parameters we didn't have, and we fitted with an equation that varies with the frequency, with the cell size, and with the I mean frequency, cell size, yeah, and the depth, of course. And so with this we have all this data we need to solve the equation.
Mm-hmm. And
but there is like these six different, sorry, there's like six different equations you get from this fitting.
Mm-hmm. Okay, and maybe I just can read the comment from Frederic. He just supports what I said before. It's more a comment, but that's what he's writing. He has the same experience as the one I reported, that if you have too large granulometry, not lab type solids and suspended solids, this gives a bit of deviation in the results. Mm-hmm.
Yeah, of course, but this is what I said. You know, it's better compared to nothing, and we are not yet in the place to start assessing all the errors of the methodology. We are just trying to drop it to the world, and maybe people who are more interested in data science can approach it from that direction.
Yes. That's what I realized. Good luck for you that
thank you very much.
Starting from the scratch. And
yeah,
nothing to compare with.
Yeah. Thank you very much for your input.
But I guess you can build on Ricardo's work, and then you will have the same database in the end, what we have from the Paraná River.
Yeah, of course.
After all,
I hope so.
Yeah. Yes, but the frequency shift in the M9 is really tricky, and I'm not sure if you have do you have access to the software itself, or do you have the closed just the user interface?
Well, actually, I was working with the MATLAB export data.
Yeah.
So when you process, you can export one MAT file, and then there is even some more information that one knows. You know, you have to scratch a little bit, and and then you get some data.
Yes, you have it. Yeah, I have it hidden there.
Yeah.
Good. Very good.
Well, and I have to apologize. I mentioned that Frederic is and said he has a comment. It is she. Sorry for that. So
and she wants to read your PhD report. So please provide or exchange.
No, I haven't presented yet.
Aha, you haven't defended yet. Okay.
So another reason to finish soon.
yeah, of course. Okay. So that's why I'm really thankful for your input, because it will really help on the writing of the dissertation.
Very good, very good.
So I think we have another 15 minutes, but we have another 3 papers which we did not yet discuss.
Exactly.
If that's fine with you, Niels, and with all the rest of the community, I would suggest that we move on to another presentation to discuss it.
Yeah.
I do have questions to all of the 3. Maybe I start with the one from Sia Fikrasali talking about the veins. And I have more or less a comparable question that I already had with the peers. I see that you have different settings of the veins in different angles and different positions. And you said the optimum setting was a 60-degree angle. But is this true for all settings, or does it depend on the specific share between the ratio between width or slope or discharges or grain sizes or length of the vein? So did you make variations in this perspective as well?
Yes, the important variation that we compare is the type of the vein and the number of rows that we compared. So in the study that we done is based on the branching angle of 60-degree and the 30-degree branching angle. So based on that, we look at like, okay, what is the type of vein? The number is it a flat vein? We use flat vein and L-shaped vein. You can see also as well in the photo, there's an L-shaped vein. So, and then we also compared with also a one row flat vein, 2 rows flat vein, and then 1 row L-shaped vein and 2 rows L-shaped vein. So that's the variation that we focus on this study.
But you had always the same sediment. So your mobile bed, you made an investigation on the mobile bed. That was what I see from the pictures. But the sediment distribution was always the same.
Yes.
So you didn't. Would you expect that you get different results if you change the grain sizes?
Yes. A heavier sand, heavier sediment might affect the data.
And then you would get a different distribution of the sediment, which would go in the side channel, or stay in the main channel, or what would you expect? What is the difference then?
What would I expect? I think the result in terms of the vein type, I think you can see a little bit of the same result, but I think the sediment reduction would be a little bit lesser if the sediment is a heavy sediment. Will be so it more accumulate. It would more accumulate at the entrance of that branching channel. I think will be more. The accumulation will be more.
Okay. So your recommendation would be for a specific situation, you always need site-specific modeling tests. Is that right?
How was what did you say the second angle where you were investigating?
30 degree.
30. Okay. And why not 90 degrees?
Why not 90 degree? Because we are 90 degree. Based on what we think is that the 90 degree will not show a bigger much difference compared to the, what we want to focus on is like having an angle, and then we want to focus on the type of the vein, the type and the arrangement of the vein. Which one shows more reduction on the percentage? So that's the focus on the study.
Would you consider the angle as the most important parameter, or is it also the length of the vein and the number of the veins? And I
think the number of the vein and the type of the vein would be most affected. Like more number of vein would produce a lower number or percentage of sediment reduction. Based on the study being done.
What do you think is what you investigated or analyzed or found out? What is the major process, hydraulic or flow process, which helps you to stay the sediments in the main channel and divert the water? What does this vein do?
The vein, I think what the vein do is like it's automatically it's kind of like. It kind of slow down that the water flow coming from the main channel to the branching channel. It a little bit slowing it down, so it just like kind of like having a vortex in the branching channel. So so that the sediment kind of accumulate, affecting that they accumulate in the entrance of that branch channel. I think that's why what the function of vein is.
Okay. So I have a more out-of-the-box question. We were right now looking into sediment bypass tunnels and how to make it the other way around, right? To have most of the sediments with the least amount of water to the diversion channel. So what would be your recommendation to place the veins? Just mirror-wise, or is there any? How would you?
Is the tunnel ever branching, or just one straight tunnel or something like?
Just stay the same angle.
Or stay the same angle.
Same situation, same geometrical situation. Just the effect should be opposite.
Oh, you are. Oh yeah. Okay. I think the still like, because of the number of vein would exactly automatically would slow down. Slow down that water discharge. So the more rows that you put, 1 row, 2 row, and 3 rows, even more rows you put, you're gonna slow down that, gonna make that water would gonna be a vortex in the middle of that branching. So the more rows of vein, I think that would exactly, if you want like a lower water discharge and then a higher sediment reduction.
Okay. Okay.
But is this totally true? So I follow your hypothesis that the more veins you have, the more you slow down the hydraulic conditions. But this is true because this is a kind of roughness element then. But the higher they become, if they are not that small, that short, then it's more like a contraction, and then you might have an increase of the flow velocity between the veins. So what is the threshold in height or in length of the veins to either act as a roughness element or as a change in the geometry and thus an increase in the flow velocity? You know what I mean?
Well, you mean what the height that would be recommended in this as the based on the height? We use around 2.6 meter, 2.60 m exactly. Like just want to see like because the channel is quite small, so we just want to fit like 2 rows of veins. So we don't exactly have a specific reasoning for the height because it's a small. We want to fit the 2 rows vein exactly. So in this study, this is exactly the study only focus on the type and the numbers of rows of veins. So the height is not the focus on this yet.
Okay, thank you. Any other question for Siafik Razali about the veins and the experiments about that? I see nothing in the question and answer box.
No.
No. But I would have a question to Chang Li. So you were talking about this, the one-dimensional model, and I was a bit wondering because you were stating, maybe the first question is, what was the main aim of the study? So you investigated the width and the water depth and the sediment parameters, but what was the main aim in this more general study?
Thank you very much. I use a one-dimensional model to calculate the water depth and other parameters to find whether the channel is scalding or other conditions. It's my
So it was mainly about the scour processes, whether you have large scours. Okay. And then you are stating that your 1D model can better simulate the basic river data. What do you mean better? Better as a 2D model, or better as a 3D model, or better in terms of what?
Oh, that's next. I want to work on this.
Pardon me?
Well,
I didn't hear your answer. Sorry, I was just from the voice. I couldn't hear. Maybe it's my loudspeaker, but maybe you can just repeat your answer.
Okay. Could you hear me?
Yeah.
Now we hear you. Yes.
Okay. Your question is what I want to do in the next study.
No, my question was, why do you say that your 1D model is better in terms of simulating? Your last sentence is that your study can better, or your 1D model can better simulate the basic river data, such as river width and average water depth. And I'm wondering, better as what? So is your 1D model better than a 2D model, or or what do you mean is better? Better than what?
Better than the channel condition before.
Okay, so it's not the modeling. You mean you have results which show that you have a change in the channel condition?
Yeah, I use the modeling results compared to the the testing data.
Okay. Did you also think about using or applying a 2D model, or is this too much data, or why did you go for a 1D model?
Why I use the 1D model?
Yeah, exactly.
I just began to learn this model, so
Okay.
I use a basic study.
Okay, okay, I see.
Thank
So
you.
Niels, you also want to ask a question, or?
Yeah, I had the same question about the better, but
Okay.
there's another better in the conclusion, which says the water flow condition in the remaining section of the reach were better. Also here, it's just obvious that you have to ask what do you compare your results with?
Yeah. Compared to the testing data, the testing data is we go to the field observation from upstream to downstream. This data part.
Yeah, I think we just have another 5 minutes or so, and I would also pose some question to Majid, and if you allow, Niels.
Go ahead, go ahead.
So last but not least, so Majid,
yes,
very interesting presentation, and I liked your approach to go through all the literature and see what is the most important or the most obvious keywords. And I'm wondering a bit. So what your hypothesis in the end was, okay, there is a lack of literature about certain areas in the Keynote PIV's investigation, and this is where you assume there is more research needed. But couldn't it be also the other way around, that there is no more research needed, and that's the reason why there is nothing more published, and that's the reason why you don't find these keywords?
So please, could you please allow me to share something?
Sure, sure.
Because I have about around 17 page about review, but you know the poster a little size. So let me share something. Okay.
I think it's the secretaries.
Yeah. No problem.
The host who have to do that.
Yeah. Okay.
Here.
So if you see this Excel sheet, you see, this is like a filtering for all literature review of papers. I collect about around 416 papers. The topics focus 100% on the piano key weir. But there are many statistics, and I have many papers, but this is very important for researchers. If you see, there are a sample from this paper from 2012 and 2021. There are focus from the Web of Science. You know, the Web of Science as a clairvet. So that's mean very interested for the topic of piano key weir. And when we see the second here, the second figure, we see the increasing for the research to focus on the piano key weir. If you see 2006, when the first light seen for the piano key weir in Real in France, and Labyrinth researcher. So if you see in 2019, focus on piano key weir, and there are another charts here that's very important for me, for my as a PhD student. That's very important for me to focus on something of type of piano key weir from the fourth type of piano key weir. So there are from another sample of papers, there are a focus on, there are type A and B and C and D for piano key weir. That's dependent on this name, dependent on the overhang of piano key weir. So a rectangular piano key weir, that's focus on for most of recent researcher. And if you see here, I have a figure about when I search about the Q1 or Q2 about ranking for the journal that published for the piano keywheel. If you here, I have a sample for Q1 and Q2. Here, the increasing for Q1. That's mean so interested for piano keywheel. Piano keywheel is very important now because of climate change and global warming. You know, the rising of sea level, and then we need to, instead of gate of spillways, you know, you need many maintenance and cost. So the piano keywheel is instead of Labyrinth spillway and for costing, for reduce the costing of maintenance. Yeah.
I'm sorry, Majid, but I think, oh, sorry, Silke as well, to interrupt. I think we have to close the session. Yeah. However, yeah, I hope there's not there's still some research left to do on piano keywords. And if you like,
that's true.
Professor Ahmad in the chair of the next session. Hello, and
hello, Professor Uttar. Professor Silke. Yeah.
Hi, good to see
you.
Meeting
after a very long time.
Yes. So he's an expert. He's an expert on that. So you have to refer to him as well.
Exactly.
Okay, Silke, shall we close the session?
Yes, good idea.
Yes. So thank you very much, all of you, for this very interesting and wide range, broad topics presentation. Thank you very much, and I really enjoyed it.
Yeah, big thank you also from my side to all of the presenters. I know that you were in the focus, especially from the two of us with all the questions, and I'm very happy that you gave so many interesting answers and more deeper insights in your research, and I wish you all the best and put all your motivation in your further research, and I'm sure you will do, and I'm happy to see you soon again, either maybe in the next online Young Professional Congress, and even better if we can see face-to-face in the next one of the next IHR congresses. Yes. So have a nice evening. See you soon.
Thank you. Bye-bye.
Bye.
Thank you. Bye. Thank you, Silke, Anil, for this.
Hello, good evening all. On behalf of IAHR YPN committee, I welcome you all in our today's fourth session, that is hydraulic machinery and transient flow. This session will be hosted by Professor Ahmed and Professor Victor. Professor Ahmed is faculty at Indian Institute of Technology, Roorkee, India, and Professor Victor is faculty at Department of Mechanical, Kyoto. Sir, now floor is yours, sir.
Well, thank you, Dr. Manish. And I welcome Professor Victor. Hello, Professor Victor.
Hi, Professor Hamad.
Hello.
I am
Hello.
Victor. Nice to see
Yeah.
you again in this season.
Yes, after a long time.
Yes, a long time, but we collaborate with the younger people and the younger research in this meeting.
Yes, yes.
Okay,
yes.
Professor, it's my pleasure that you introduce the first presenter, and I introduce the second presenter. Okay.
Yeah. Well, in this session number 4 of this IHR conference, we have 7 papers, right? Under
I
this.
have 9 papers, or it's only 7 because I received 9 papers, Professor.
No, I think 7 papers. 1, 2, 3, 4,
7
5,
papers are
6,
there.
7.
7
7
papers.
papers.
Okay.
7 papers.
Yeah, 7 papers. And each paper is allotted 6 minutes for the presentation. Of course, this is on the poster mode, right? And after the presentation, we'll go through the question and answer session. I think in between, we should not disturb the authors or the presenters. Let them present first. And after this, you see presentation of all the 7 papers, we enter into the question and answer session. Well, this session, this deals with the hydraulic machine and the transient flow. This is a very, very important topic, okay? Because the transient condition, this is very unique. We are not talking about the steady flow. We are talking about a transient condition of the, you see the steadiness, right? Because between the two steady flow, we have you see one transient condition, right? And how that is affecting the machinery. So that that is going to be discussed in particular session number 4. So let us start. And in this connection, I would like to invite the first author of this paper number, that is the poster 3.
Hi everyone. Can
Hello.
you hear me?
Yeah.
Yeah.
So you take 6 minutes for the presentation.
Yeah. Okay. Thank you. I can start to present. I am Emanuele Quaranta from the Joint Research Center of the European Commission in Italy. I work in the Water Directorate. And this paper, the title of this presentation is Power Decay of a Low-Head Kaplan Turbine due to common vegetable bodies ingestion and accumulation. The Kaplan turbine under investigation is a micro Kaplan turbine rated with a head difference of more or less 5 meters and a flow rate of more or less 650 liters per second. So the nominal power is 30 kilowatt, but considering the global efficiency of the plant, the produced power is 18 kilowatts. So the global efficiency is approximately 60%, which is a typical efficiency of this very low head power plant equipped with reaction turbines. During operation, we observed a strange phenomenon, as you can see in figure 2, where the power decreased from the installed power of 70, 80 kilowatts to 15 kilowatts over 4 days. If we stopped the turbine and start it again, the power again established to the maximum power, but then again started to decrease. We tried to search some literature, scientific paper about this, but we did not find any evidence or any scientific paper that investigated this phenomenon. So we decided with the company that owned this power plant to open this distributor of the turbine, and we found that the distributor was full of debris, vegetable debris, in particular leaves. And we also found that during the elaboration of the performance of this turbine, during the decrease of power, the flow rate remains constant. So it was the efficiency that reduced. And this was due because the accumulation of these debris and these leaves changed the flow field. So for example, altering the velocity triangle theory. And so the efficiency of the turbine reduced. And the stop and start cycle allowed to reestablish the nominal power because the rapid changes in the pressure during this start and stop cycle allow it to act as a sort of cleaning process. And so by these case studies, we would like to stimulate future researches on this topic, especially for the micro hydropower sector, because micro turbines are smaller than common turbines, so they may suffer of this phenomenon more than the big turbines. And so we would like also to share our key points of this case studies, that is the reduction of power, that was mostly done caused by the reduction of efficiency rather than the reduction of the flow rate, and also the fact that by a stop and start cycle, this debris could be cleaned, and so the situation can be restored to the original one. So thank you for your attention.
Well, thank you, Quaranta. Now we move to the next paper. Daniel Novara.
Daniel Novara is here.
Hello. Hello, everyone. Thank you for the introduction. So I'm Daniele Novara from Trinity College Dublin, and the topic of my poster is micro hydropower energy recovery and a practical application and long-term monitoring of it. So in short, micro hydropower from existing water pipes consists of adding a turbine generating some electricity instead of otherwise dissipated electricity, and this is typically done in existing water networks such as drinking water or irrigation. However, the application of the technology for very low power outputs, even below 5 kilowatt, is something that has been investigated in theory, but has found very limited applications in practice. And one class of hydraulic turbines that has been investigated as particularly suitable for this type of peak or hydropower applications in existing conduits are pumps turbines, which consist of off-the-shelf centrifugal pumps in which the flow is reversed so that they can operate as turbines. So in practice, they are kind of a Francis turbine, but without moving parts, at least similar to that. So during the course of this research, myself and the team, we installed two of these devices, both rated with less than 5 kilowatt, at two sites, one in Ireland and one in Wales. And then we proceeded to monitor how well they performed for a long period of time. The first device was is in a drinking water network in the south of Ireland, and produces just about 3 kilowatt out of a flow of 17 liters per second and a head of 36 meters. And as you can see from the first figure, since the commissioning, which happened in October 2019, for the first few months of operation until April 2020, it operated almost constantly with a very good capacity factor, generating between 1,500 to 2,000 kilowatt hour per month. Afterwards, during the summer 2020, the production was lower, and that's just because simply the river from where the water comes from gets seasonally dry. And then the other things that we can observe is that between say October 2020 and April 2021, we would have expected a higher power generation similarly to the winter spring 2019-2020. However, the monthly generation was considerably lower, but that was due to an airlock phenomenon that kept occurring and has then since been solved. And then by the end of the spring 2021, again the river started to dry. But overall, the performance were very satisfactory. There were almost 16,000 kilowatt hour generated over just the first 12 months of operations. And the second site instead is located in North Wales, and it's on a stream serving like a rural farm. And it was also commissioned at the same time as the first one in October 2019, as you can see from figure number 2. And it produces a similar monthly power output around 1,500 kilowatt hour per month until February 2020, when unfortunately it was damaged by a storm. Then it was briefly brought back online again in between August and October of the same year, but then a second storm occurred. So then it is currently awaiting repairs, and it's expected to be brought back online in January next year. So this turbine is slightly bigger than the first one. It's about 3.7 kilowatt. However, the two sites are pretty similar. So as a conclusion, we can say that the monitoring campaign showed that especially the first site in a rural Irish water network performed according to the design parameters for for the first year of operations. Instead, the results are inconclusive for the second site. We will continue monitoring it after the needed repairs. Thank you.
Well, thank you, Mr. Novara. Okay, nice presentation. Okay. Now the next presentation is the numerical simulation of cavitation in Pelton turbine injector. Navam Srivastava.
Hello everyone, I am Navan Srivastava, PhD scholar at National Institute of Technology, Warangal. My topic is numerical summation of cavitation in Pelton turbine injector. Most of the small hydropower plant are basically a run-of-river type, and in India, they are mostly situated near the geologically young mountain range, Himalayas, which is a source of continuous sediment particles. When these sediment particles strikes the turbine material, erosion of material, and that is material loss take place, and which changes the design of the component, and which due to which efficiency of turbine decreases. In the Zehab and Harmanian paper, we found that at partial loading, cavitation means synergic effect of cavitation and erosion is found at partial loading, due to which erosion increases significantly. So we can say that cavitation is one of the reasons. It acts like a catalyst for the erosion. This cavitation, when combined with erosion, it acts like a catalyst which increases the erosion rate significantly. So our aim of this paper is to find the region, cavitation prone region in the Pelton turbine injector. So we have done this volume of fluid method analysis. We have found that near the nozzle ring, negative pressure is, we find that negative pressure at near the nozzle ring, which indicates the cavitation phenomena. And we have done the transient analysis also. Transient analysis using the Schner and Scour cavitation model, and we have found that bubble growth near the nozzle ring for about 100 to 150 microseconds is there. Then we have compared our result with Zehab and Harmanian paper, 2020 paper, and there the erosion in that paper was maximum and near the nozzle ring only. Means the region where we have found that the cavitation, same area, the erosion was maximum. So we can conclude that cavitation is one of the main reason of the enhancement in erosion. And we can conclude that one of the means partial loading. At partial loading, cavitation, there is chance of cavitation at partial loading of Pelton turbine. When partial loading of needle, there is chance of cavitation, which enhances the erosion rate. And in future, there can be two future scope. Firstly, we can design the Pelton injector, which is cavitation free, means cavitation is not there. And secondly, we can do the quantitative analysis in how much the erosion is increasing when cavitation is present, means how much cavitation is affecting the erosion quantitatively. Thank you.
Well, Mr. Srivastava is a good topic. Okay. And I understand you have used this numerical technique for the, you see, identifying the zone where the cavitation can occur. Okay. So we'll enter into the question and answer session later on. Let me call the next presenter, Mare. Pumps as a turbine regulation study through a decision support algorithm.
Thank you. You hear me?
Yeah, you are audible.
Yes.
How are you? Fine?
Fine, thank you.
Yeah. It's good.
Take it easy, don't worry. Speaking slowly is the first step.
Well, good evening, everyone. First, let me introduce myself. I'm Maël Lemar, third-year PhD student working in Redon and attached to the Institut de Recherche du Puy-de-Dôme in Lorient in France. I'm under the supervision of Professor Philippe Mandin and Professor Jean-Louis Lanoiselle. Today, the topic I intend to discuss is the regulation of pump used as turbines. Two regulations have been studied on 3 wheel sites through a decision support algorithm developed by the authors. So what about the regulation method? The hydraulic regulation called HR and the hydraulic electric regulation called HER are visually explained in figure 1. In figure 1 on the left graphic, the hydraulic regulation is presented. In blue, we can see the operating curve of the path. So how work this regulation of the pump as turbine that I call path, sorry. So how work this regulation? If the flow rate is too high by respect of the path operating, a pressure reducing valve that I call PRV in parallel will be past the overflow. It's named PRV2 on the scheme. If the pressure is too high for the operating of the path, the pressure reducing valve in series with the path will absorb the overpressure. For the other regulation, so the hydraulic electric regulation, the only difference is that a frequency inverter is added. So the frequency inverter allows to manage the rotational speed of the path, as shown on the graph on the right. The frequency inverter allows to increase the operating zone of the path. So these two regulation methods are added in the decision support algorithm. So the algorithm allows to any user to easily estimate the energy production and the payback period for a site. So the algorithm is presented in figure 2. So how it works, there is 3 input files, a pump as turbine dataset, the cost of equipment needed for a path installation, and a measurement dataset which have to be implemented by the user. Once the measurement are implemented, the algorithm can be run. The first step is of the algorithm is to calculate an optimal point. So the optimal point is the couple of head and flow weight, which give the best potential of recoverable energy. Then in step 2, with this optimal point, the algorithm will select some pump as turbine from the database around this point. Then for each selected pump as turbine, the algorithm will calculate the yearly energy production. So how the algorithm do this step? First, it will repair where the data is. It means if the data is in the overflow zone or the overpressure zone, for example, then the algorithm will calculate the characteristic of the path at this point, and so the energy production at this point. So the algorithm will do a loop for each data and for each path. Finally, the path giving the best yearly energy production will be selected, and the cost estimation will be calculated, and a payback period will be estimated. So the software has been used to study 3 wheel sites located in Brittany, in France. The result are presented in table 1. First, we can observe that the adding of frequency inverter increase the energy production of the 3 sites by respect to the HR, even if the gain is different from each site. But we can observe in economics terms that the payback period is largely increased with the adding of the frequency inverter for every site. This is explained because the frequency inverter, it's an expensive device and its lifespan is it's low. It's between 5 and 10 years, and it's assumed to be 8 years in the algorithm. So the HER, the hydraulic electric regulation is less economically viable than the hydraulic regulation. To sum up, the poster presents an innovative algorithm which allows any user to easily estimate the energy production and the payback period of a pump turbine installation. The poster also shows that the hydraulic electric regulation is not economically viable, but give a better energy production. I would like to acknowledge the European Union for the funding through the IAHR for Water project. Thank you for your attention. If you have some question, it will be a pleasure to answer it during the coffee break.
Thank you, Dr. Mare. Okay. I think you are doing your PhD, or have you completed?
No, I'm still in a PhD student.
Okay, that's good. Okay, so let us move to the next presenter. And the paper is Operation of a Pumping Station, Selecting the Number of Active Pumps by Candilejo.
Yes, hello. Let me share the screen first. Can you see the screen?
Yes. Yes. You are audible and your screen is also visible to us.
Okay, thank you very much. All right. Thank you all for attending this Congress, and thank you the ER for organizing it. And I am Araceli Martin, and I am going to present our work, which is called Operation of a Pumping Station, Selecting the Number of Active Pumps. And this work has also been carried out with the help of Francisco Javier Martín Carrasco and David Santillán Sánchez. All right, so what is this paper about? The aim of all this research is to solve two questions. Well, in fact, to solve a few questions, but the main one is how many pumps should be working when I need a station to provide a certain volume of water? So that is my main question. And this question has been typically answered with complex iterative algorithms that are very heavy in the computers and require a lot of computational work. But we took the question and analyzed it from an analytical perspective. And we analyzed it from this perspective. So if we want to provide a certain volume of water, let's call it V, what we want to do is to minimize the energy that is spent to provide that volume of water. So we want to minimize the energy. And it is very convenient to analyze it from the unit energy required to pump a cubic meter of water, which is this E. So it's very, very convenient to analyze it from the perspective of this specific energy. To solve the question, how to pump a volume of water, the answer should be, well, you should pump it minimizing the energy spent. And that also means minimizing the specific energy spent. So if we decided to pump the entire volume of water with just one pump, this would be the volume that we would pump during the whole time, and this would be the energy consumed. But if we decided to pump the entire time with two pumps, this would be the volume that we provide, and this would be the energy consumed. And we can see here two rectangles, and that would be the energy spent. But let's say that we don't want V sub 1 or V sub 2. We want an alternative volume. We want a different volume, V star. How do we provide that volume? Should we pump the entire volume with just two pumps, and this would be the energy consumed? or can we combine the number of pumps? Well, if we combine the number of pumps, it would be what figure 2 says. If we combine the number of pumps, we could pump a little bit with just one pump and a little bit with 2 pumps. And this would be the energy consumed. And if we compare it with the solution 1, we can see that there is a lot of energy savings that are shown in this rectangle. So the answer to how to pump a certain volume of water should be answered with, you need to combine the number of pumps. But a different question rises. Okay, I need to combine different number of pumps, but how many? Should it be 1 pump and then change into 2 pumps? Or should it be 3 pumps and then change into 5 pumps? What's the answer to that questions? Okay, so we have combined a certain numbers of equations that correspond with the conservance of specific energy. I mean, the energy that you provide with one configuration plus the energy combined with another configuration should be equal to the final energy. The time that you pump with one configuration plus the time that you pump with a different configuration should be the full time. And combining all of this equation, we have been able to found the equation of the specific energy corresponding to whatever volume of water. And this equation is in fact this equation, which is a hyperbola. And that is really interesting because it means that if we wanted to provide a random variable value of water, we could easily see what it would be, the best energy, the least amount of energy, and the best pump configuration. So we would have to provide a little bit of time with 1 pump and a little bit of time with 2 pumps. And this applies for any pumping station that we can think of. And that is the case of figure 3. In figure 3, we have a station, we have a representation of a station with 3 different pumps. Here we can find them. And these are the convex hyperbolas that show what it would be the best and the least amount of energy. So this one is the curve that is the lowest. And if we wanted to provide this volume of water, volume V star, the best configuration would be to find the lowest convex hyperbola. This would be the energy consumed, and determine that the best configuration is to pump a little bit with 1 pump and a little bit with 3 pumps. And this leads to a series of curves that are easily provided by the designers and that could be easily used in the operation of a pumping station. And I would like to thank all of you for your attention, and I'm open to any questions that you might have at the end of the session.
Thank you, Martin. Okay, it's a good presentation. Now let us move to the next paper. Martin, we discuss about your paper after completion of the presentation of all the papers. Okay. So please stay with us, right? We return back to you.
Okay. Good evening, everyone.
Next, yes.
Okay. My name is Xilong Ying. Come from Tsinghua University, China. And my presentation is about analysis of flow characteristics of pump turbine transit process. In modern society, the demand of growth of the regulation is increasing, and the pump storage power stations are very important in the power system, and the pump turbine units need more start-stops per day. As an important comment of the unit, the research of the steady-state flow phenomena of the pump turbine has been widely studied, while the unsteady flow characteristics in the transit process are more complicated and have not been explored in depth. We researched a prototype reversible pump turbine unit of a high-height pump storage power station and analyzed the pressure change of the unit under startup and shutdown conditions. The 3D calculation domains of pump turbine units consist of 5 parts: spring casings, stays wine, guide wine runner, and a draft turbine. As shown in Figure 1, the pump turbine has a rate head of 545 meters and a rotational speed of 428.6 revolution per minute. As a rated head, the rated output power of the turbine is 357.1 megawatt, and the number of the runner blades is 11. The number of the stay wines and the guide wines are both 20. Based on the time-varying data of the pressure, flow rate, and the rotational speed during the turbine start-up process from one-dimensional pipeline calculation, a total of 11 key time points are selected in order to better describe the physical phenomena. Steady-state calculations are performed for these 11 key moments. The spring casings inlet to set to total pressure for these calculations, and the draft tube outlet is set to static pressure. It can be seen that in the initial stage of the startup process of the pump turbine from 9.6 seconds to 16.7 seconds, the guide wines opened gradually, and the flow rate, rotating speed, and the pressure level of the guide wines and the runner also increases gradually and slowly. Then at 18.4 seconds, the guide wine opening is reduced to prevent the speed from exceeding the rated speed. Thus, the flow rate is reduced, and the pressure level of the guide wines and the runner is also significantly dropped down. After that, the rotating speed of the runner continues to increase, but with a similar incremental ratio than before, and finally stabilizes near the rated rotating speed. Then from 30.7 seconds to 100.8 seconds, the guide wines also open a little bit more gradually until the unit enters speed no land operation condition. Meanwhile, the pressure distribution of the spring cases, draft tube, guide wines, and runner stabilizes gradually. At 201.6 seconds, the startup process is finalized, and the unit is ready to connect to the power grid. Similarly, based on the time-varying data of pressure, flow rate, and the rotational speed during the turbine shutdown process from one-dimensional pump line calculation, a total of 7 key time points are selected in order to describe the physical phenomena in detail. The pressure changes of the turbine during the shutdown process is shown in Figure 3. It is clear that the initial stage of the shutdown process from 0 seconds to 10.5 seconds, the flow in the runner is stable. The water flows smoothly among the curvature of the blades, and it is obviously that the pressure distribution of different blade channels shows a rotational symmetry predictably. The pressure level gradually decreases from the inlet to the outlet of the runner. It is also clear that during the shutdown process, the overall pressure distribution of the runner gradually decreases in general. In conclusion, during the beginning of the start of press, the guide wines open and then close while the pressure of the runner increases and then decreases. Then the guide wines gradually open and the pressure of the runner stabilizes gradually. During the shutdown process, the pressure distribution of the runner gradually decreases. Okay, that's all. Thanks for your attention.
Thank you, Mr. Zilong. Hello?
Professor, we listening to you?
Yeah. So let us complete the last paper, and then we discuss about the all the presented papers. The last one is the 3D simulation of positive surge waves, turbulent structures, and anisotropy and aeration pattern.
Hi, hello everyone. Okay, So hi, welcome to my presentation, and my name is Jordan Li. I'm from York University in Canada, working together with Akash from the VIT in India, and also my supervisor, Dr. Karimpour. So we have been working on the 3D simulation of the positive surge waves, focus on the turbulent structure, anisotropy, and also the aeration patterns. So we performed the 3D simulation with open source CFD software named OpenForm, along with the large ID simulation for the turbulent modeling, and with the K equation sub-grid scale model. And also we applied the interform solver, which is based on the volume of fluid method to capture the two phases of the flow, water and air. So the computational domain has a minimum mesh size of about 0.0025 meters. With the periodic boundary condition, we can apply the 3D simulation for the surge waves. So we cover the surge flow number from 1.71 to 2.13, which is in the range of breaking surge waves, where we can observe more aeration to happen. And here the equation 1 is the governing equation for the large eddy simulation. It's also known as a filtered Navier-Stokes equation. And the figure 1 here shows a sketch of our computational domain, where you can see the 3 rigid walls with a breaking surge propagating towards the downstream of the domain. And the ARR basically shows the area of refinement, you can see, is along the passage of the surge wave. So for the result, we present the first aeration patterns here, and also averaged aeration patterns. And you can see that at the toe, or the surge toe of the surge wave, basically is the lower end of the surge wave. See the air concentrates near the toe. This is supported by our another plot of the turbulent kinetic energy, where you can also observe a strong turbulent kinetic energy near the surge toe. And for the envelope here, which is bounded by the green line and orange line here, shows where the aeration happens the most. This area extends further down towards the lower of the domain. So it go in depth with a higher surge flow number. So this is also reported by other literatures that studied the surge waves. So another result we include here is the perturbation. We did the quadrant analysis of the velocity perturbations, first in the XY plane, the first row, and the second row is for the YZ plane. So you can see that for the XY plane, the second and fourth quadrant dominate. So that indicates ejection and the sweep behavior of the perturbation, which leads to a positive production of the turbulent kinetic energy. And on the other hand, for the second row in the YZ plane, let's see they are evenly distributed among 4 quadrants. So that leads to no turbulent kinetic energy production. So basically that's all I want to talk about for this poster, and thank you for your time.
Thank you, Mr. Lee. It's an interesting paper on the surge analysis, and you have used the LES for the simulation, in particular the aeration process. So that is a good advancement in the field of the numerical modeling of the transient flow in the open channel. Okay. In this session number 4, we had 7 posters presentation. And you see the presenters have already presented. Okay. Now this session is open for the questions, and our presenters will be requested to answer those questions. Professor Victor, would you like to start with some question from your end?
Of course. Thank you, Professor Hamad.
I
have some questions. First is for the power decay of Lockheed Kaplan, going into order. How do the power plant control the introduction of a big bodies, because we saw that you put leaves on other things, but how do you control the big bodies to go inside to the Kaplan turbine?
Thank you. Yes, it is possible to reduce the amount of vegetable bodies that goes to the turbine by using racks among upstream of the plant. The problem that is in this plant was an irrigation canal in a very rural environment, and sometimes, especially after storms, there were a lot of vegetables and vegetation inside the river. And the problem is also if we use very fine racks upstream of the plant to avoid the vegetation, all this vegetation stacks on the racks, on the net, and so generate, in any case, power losses and flow rate reduction upstream of the plant. So it was quite a tricky problem.
Okay. David Ferrars has some questions.
Yes,
David
I just raised the hand because I had a question related to this presentation. Emmanuel, my question is, have you considered the use of screw turbines to solve such kind of problem? Of course, it would imply to change everything, no? But
you say the Archimedes screw turbine.
Yes.
Yeah. This turbine was depends also on the site characteristics, because in this case there was no space for the Archimedes screw, and I don't know why. So substantially, we examined this problem after that the turbine was already installed. So this was a choice of the company to install a micro Kaplan turbine and not an Archimedes screw. But yes, an alternative may be an Archimedes screw or a water wheel that are gravity machine, and their behavior is very good in relation to sediment and vegetation, also with fish. So yes, our gravity machine can be an alternative to micro Kaplan turbine in this context.
Okay, thank you.
Thank you.
Well, Mr. Kuranta, my question. Hello, Mr. Kuranta. Yeah. You see, mostly the vegetation that is in the under the floating conditions. Most of the vegetation that is on the surface. So could you put some floating booms, right, to retain this vegetated material upstream of the turbine?
Yes, some floating platform or floating weirs can be used to divert vegetation, but we found that a lot of leaves and vegetation also stayed not on the surface of water, but in the center of the canals. So yes, with floating platform, we can a bit mitigate the problem, but not to solve it.
Okay.
Perhaps some advice is you can consider some angles in the racks, because the most people is the people put it in the 90 degrees angle, and this is the main issue than the thing. But if you put it in some angles and you calculate these angles, you can put it to some vegetables go outside to this one, and you can return.
Okay, yes,
this
to
is
divert vegetation, similar to alpha rack for fish, that they divert the fish laterally. Similar, yes.
That is the issue that I think that this can be possible, but you need to understand the angle, because the angle is the main parameter for that one.
Thank you.
Okay, this is only my advice. If you consider, you can research it. Okay, thank you. And because for the time, Professor Ahmad, I go into the paper 2. I have some question for paper 2, the performance monitoring of 2 peak hydropower pumps as turbines over time. Using pumps as turbines, did you estimate the efficiency and the possible applications? Because you introduced us that you use the pumps as turbines, but can you consider you can estimate the efficiency?
Thanks for your question. Yeah, the efficiency in the overall flow to wire efficiency of both devices is around is slightly above 50% when you consider all the losses, including generator and transmission and so on.
Yes, of course, because pumps using as turbines, pads, is more than normally is 50 to 60. No, it's more possible to 60. Sometimes you make some electrical arrangement and you can get it more. But this is only the question. And another thing, what is the application that you study the pumps pads? Because we study pads because we would like to apply it in something. What is the application?
Yeah, the application would be quite unconventional hydropower or energy recovery. So in most cases in which it would make more sense to have a pump turbine instead of a bespoke conventional turbine would be those on a small scale, first of all, and secondly on infrastructure which is already built. So yeah, especially pipelines for drinking water or irrigation or industrial cooling. So situations in which good part of the infrastructure is already there and the potential of the amount of power to be recovered is relatively small, definitely probably less than 100 kilowatt. In this case, it was quite extremely small, like even less than 5. Those are the best cases in which we saw that these devices are applicable.
I understand you, because in Ecuador we studied a path because we are going to apply it for small towns or a small village. I'm going to apply for a small farms because they need electricity and solar electricity is not possible. So on a solar panel is not possible. So we applied this case. Another thing on the final equation is which could be the main problem of the transient flow of using pumps as turbines? What is your experience? Which could be the main problem of transient flow?
Since these pump turbines application that we've seen are normally on a small power and run quite constantly, they don't have a lot of startups and shutoffs. So the main issues would be related to runaway in case there is a grid loss or the generator gets disconnected, and therefore the turbine would accelerate instantly, and this could cause problems in the pipeline, of course, as a pressure surge, especially if the whole pipeline is pressurized in case of a water network, but also to the same device in terms of vibration and torque.
Yes, that is something because after we study paths, we understand some particles are very complicated because we adapt to the runner. So we adapt to the runner to using pumps as turbines, and the impact of the tangential impact inside to the impeller is complicated. So this is some question that we ask many people because we have these problems in Ecuador. Thank you very much for your kind answers.
Thanks to you,
Professor Ahmad.
Yeah. Is one question, Mr. Novara? Mr. Novara?
Yes, I hear.
Hello. How are you?
Very good, and you?
Yeah. You see, you mentioned about some natural events, right? What was the scale of that natural event that damaged your power plant?
So we don't have we don't have like historical data on that small stream, but anecdotally, it's something which the owners of the site said that it hasn't happened in the last 50 years, such a storm. They got quite a lot of water also inside the buildings that they have on site and so on. So it was actually what damaged the unit was not the flooding itself, because the water didn't reach the powerhouse that was a little bit higher up, but instead the flooding brought down the hill a huge amount of small stones, like flat and small stones, the size of a coin, let's say. That entered that went past the gate, the mesh, and then cause an erosion damage in the runner.
Because this is miniature type, I say miniature type of the plant, okay? It's just 17 liter per second discharge. Okay, this is too low, right? Okay, thank you. Any other question to Mr. Novara from the audience?
I think that is the people is a little shy. So we're going to the paper 3, and after we can make questions, some questions in the mail. So the third paper, numerical simulation cavitation in Pelton turbine injector. Sorry, Professor Ahmad, I need to tell you this one. I love cavitation because I did my PhD studies in cavitation, so this is one of the more interesting topics for me. Sorry, this is very interesting. As in this context, how did you perform as your numerical simulation? Did you use cavitation model? Can you explain something? Because we would like to understand how did you carry out your numerical simulation and cavitation model?
Mr. Srivastav? Mr. Srivastav? He's, I think he's, Mr. Srivastav? I think, have you heard the question from Professor Victor?
Yes, sir, I have heard.
Okay. So please explain about this cavitation.
Okay. We have used this Senner-Sor cavitation model using 3 phase, water, air, and water vapor. And we have found a water vapor fraction is found near the nozzle ring actually. Means contour of water vapor is as you observed near the nozzle ring.
No. Have you done some CFD modeling? Sorry, Victor, sorry.
No, don't worry. This is the question that I did.
Mr. Srivastav?
Yes, sir.
Have you used some CFD model that comprises the 3 phases?
Mixture cavitation models.
Okay.
Which cavitation model did you use?
Senner-Sor.
Senner-Sor. Okay. This is how I understand you. Because the problem of the Senner-Sor, because I suggested you use it, did you use weir model or any other heterogeneous model? Because in the homogeneous model, the problem is in the condensation and the vaporization part is not the similar way. It's different because in the condensation, you have a nucleation part that is not considered in the normal cavitation models. So that in this context, you have some bubbles that are not real, or some cavities are not real. Did you just test with other cavity models?
No, sir. No, sir.
Yes, I advise you that you need to prove with other cavitation model, because the problem is the cavitation is not a homogeneous process. It's not similar to the condensation and the vaporization part. They are different. So you should prove other models and to test, because in the injection part, in the Pelton turbine, we need to understand how to be this heterogeneous model. Okay, this is only some advice.
Thank you, sir.
No, it's okay.
Mr. Srivastav, it would be interesting to see what is happening to the pressure on the surface of this needle, I mean the injector, okay? But I could not see any pressure distribution or what is the velocity that is on the surface of the needle or velocity perpendicular to that needle. I mean, what is the velocity distribution or the pressure distribution? Because you can get the idea from that, I mean, from the analysis point of view, the zone where you have the pressure lower than the vapor pressure.
Yes, sir.
Right? What is happening to the pressure pattern?
Yes, sir. We have mentioned this pressure contour in our main paper. Due to the space restriction, we have not presented in poster. but it is present in the main paper.
Yes, that would be interesting to see how the velocity that is changing, how the pressure that is changing. Okay. Any other question from the audience? I think audience must ask 1 or 2 questions.
Of course.
I mean,
this is
not, this is not a question and answer session. I say this is a interaction session. Okay. So don't take as a question, right? This is just interaction.
Yes, we need more people than Professor Ahmad and me and I, because this is a discussion. It's very interesting because these topics you should apply in your PhD studies and in the industry. So it's very important to make the questions discussion.
So now we can move to the next question.
The next is
Mr. Mare.
Yes, I think it's me.
PUMPA is a turbine regulation study through a decision supports algorithm.
I have one question, Professor Ahmad, in that one, because you present 2 regulations, hydraulic regulation and electrical regulation. How much to improve the efficiency to use electrical regulation in comparison to the hydraulic regulation? That part I little lost. Please, can you repeat this one?
You want me to explain again the regulation? Is that?
Yes. Because you put it the electrical regulation, yes, and you said the electrical regulation can improve the efficiency of paths. So,
not the
how much?
Efficient
or the production of the electricity.
Yes, the production of electricity, because without the frequency inverter, there is only one operating curve at the frequency of the grid. And so, because I studied the installation of path in the water distribution network, so the flow rate and head condition are variable. So add the frequency inverter allow to increase the operating zone of the pump pass turbine, and so it can improve the production, because it will be possible to turbine more flow rate and head.
Okay, but to say that it's not possible to implement, why is it not possible to implement, or complicated to implement the implementation? Because I listened something.
No, it's possible to implement the frequency inverter, but
this,
but it's not economically viable, because the inverter have a low lifespan compared to the path installation. So in terms of economics, it's less reliable. It increased the payback period.
Okay, thank you. Professor Ahmad, you have...
Well, Mr. Mare, you talk about the pressure reducing wall.
Yes.
Means just by the removal of the pressure reducing wall by some pumps, right? Could you explain this? I mean, what is the function of this pressure reducing wall? Okay, and replacing that one by some pumps for the turbine installation.
Why there is some pressure reducing device in the water distribution network? Is that the question?
Yeah.
Yes, because there is in the water distribution network, there is some flow leakages. There is some leakages, and those leakages are directly related to the pressure in the pipes. So to limit those leakages, the water companies have implemented in strategic location some pressure reducing valve in the water distribution network. But so it tuned the problem of water leakages, but there is still some waste energy within the pressure reducing valves. That's why it's put a pump as turbine instead of a pressure reducing valve, able to recover a part of this energy.
Was very interesting, Manuel Lamer. Thank you very much for your answer your questions. I don't know if Professor Ahmad has any other question or the audience, because
no. I don't have any other question. We can expect some question from the audience.
Yes,
David Ferraz, please.
Thank you.
Yeah.
David,
please.
A question for Mel.
Yes.
Because you just mentioned that PRVs are used to reduce pressure and therefore to reduce leakages in the network. So I was wondering if in your economical analysis to justify the pumps as turbines, if you also include the reduction of leakages in this economical analysis.
No, I don't consider it, because yes, I think it's already considered by the water company before, while the installation of the existing PRV. But no, I don't consider. But it should be interesting to consider it.
Wherever you have a PRV, of course, this has been already done. But if it's a new place where you don't have yet a PRV, maybe it's interesting to include such kind of factor in the economical analysis, especially because in some water distribution systems, leakages might be very high, 40%. So it will be an impact and quite an important factor in this analysis.
Yes.
Thanks.
Thank you.
Thank you, David, o David en español. We are going to the next paper, next posters for the questions. Is the operation of pump station, selecting the number of the pumps. Araceli, Miss Araceli.
Yes.
Yes, Miss Araceli, nice to see you. Did you carry out a sensitivity analysis for your study? Because did you do an empirical model based in experience, based in some graphics? So did you carry out a sensitivity analysis to know?
It is not an empirical analysis. It is an analytical analysis, in fact. And we did not carry out any sensitivity analysis because it doesn't proceed in the procedure. I mean, the method is only to determine the number of pumps that you should use during the operation. It's more like a guide for help for operators. Like, let's say that you're in a pumping station and you want a quick answer on how to pump a certain volume of water. With the curves that we provided, that are analytical curves, you should quickly find out what is the best combination for your pumps. So there is no need for an analytical analysis, but we did carry out a few analytical analyses in other studies that are very close to this. For example, we did carry out an analytical analysis for the efficiency of the pumps and how that affects the design, but that is a completely different issue, in fact.
Yes, because sometimes you have analytical analysis, but the sensitivity analysis is not carried out only. It's not carried out in the focuses in the experimental part. It's carried out in the equation. For example, you propose an hyperbole equation, yes. So this sensitivity analysis said which parameter of your equation are more sensitivity, or could be introduce an error for your selection. So this is something like sensitivity analysis because you have some hyperbole equation.
I mentioned a different word, but I was meaning sensitivity analysis. But there is no place for a sensitivity analysis in this equation because it's just analytical and it's not empirical. So
yeah, but you have some parameters that you have in your equations, of course, you know.
Oh yeah.
And these parameters you can change, or you fix the parameters.
Yeah, but you see, these parameters depend on the initial situation of your pumping station. They are something, they are an input data. let's say.
It's an input data, of course, but you have an input data. For example, you have your hyperbole equation, but in this hyperbole equation, for example, some parameter could be or introduce an error for, I don't know, say it, for precision, for accuracy, or for that one. So this is something that, this is the parameter analysis, because you have one equation. This is analytical or experimental part, but you need to know which parameter could be the main issue for introduce an error in your selections.
Yes, I get what you're saying. And as I said, we are aware that the different parameters, the different input parameters might have an input and like a result in your design or in your operation decision. And it's something that we've been taking a lot of attention in different studies, especially on the pump efficiency, how the variability of the pump efficiency affects a design and operation, also how the design flow rate affects your final design. That is something that we've covered out like in real depth, but that is in different works. And not only how it affects the operation, but also and more especially on how it affects the design, more for the design stage.
Yeah, because
but it is
work
really
is very,
important. I agree with you. Like it's really important.
Yes, it's very important because in analytical or experimental, you have some equations, and this equation you should have some parameters that should be considered. So that is the main issue that the people don't believe sometimes, because the equation is simple, it's hyperbole, and you said which parameter make introduce an error, which parameter can be sensitivity, the more sensitivity in the equation. So this is because, for example, if I am in the PhD tribunal, I make this question because it's quite complicated. Said one hyperbole can reproduce this one. So it's quite easy and it's very applicable.
The aim of the analysis that the aim of the research that we presented is not to define how the curve varies. Is for you to be able to design those curves, and so that you can use them. So it's not really like an answer of how the curves are. It's more like a guide for designers, for operators to build their own curves. It's more.
Okay. In this part, okay. Did you carry out some experimental parts, some experimental issues for compare?
We did not carry out experimental, but we did apply these to real cases. In fact, we did carry out a real case of a big network, big hydraulic network in Madrid. And hopefully we will be presenting that work soon enough in a paper.
And the accuracy and precision, because it's two different concepts. The accuracy and the precision of this equation in the comparison to the real case. Did you have something?
I mean, this equation is just it's analytical, so it's not, because it's not empirical. It doesn't have an error.
Because you compare with the real case to apply it, you know,
yes.
You have some errors because you have some errors because your equation is your equation. But for example, for me, I use your equation, of course. For example, I'm going to apply to your equation, but I need to understand why is the accuracy to the real case and which should be the precision. There are two concepts. The precision should be compared with other programs, CFD, or any numerical simulation. And the accuracy should be applied or to understand with the real case or experimental part. So that is for example, you said this equation is more for, or this kind of graphics, this is a guide for the designers. Okay, with the designer error, and we said, okay, this is it's a good precision, but which would be the accuracy or the precision? This is something that
we carried out an analysis of something similar to what you're saying in this real case in Madrid that we analyzed. We compared the results of our curves. Our curves tell us that in this moment of the day you should be pumping with 3 pumps and then change it to 2 pumps. And we obtained the cost, the energy cost, and the money expenses that you would have, and we compare them to those that the operators had like in their real life before. with their own like life-handed decisions, and we analyze the energy savings and the costs, and they are tremendous actually if you do them like more not just by common sense but also based on an analytical procedure. So it is similar to what you're saying. We compare it to those money costs that you would have had in a real situation to those that you could have if you applied the method.
Okay, this is only one advice, because if you're writing a scientific paper focusing in hydraulic part, most of the people, I am sure to make this question, because most of the professors here are reviewer in the hydraulic and the fluid mechanics papers, and this is the issue. You propose in the economical papers, perhaps you have something different, but this is the question that some people to make to you. Okay, Professor Ahmad, I don't know if you have any question.
Yeah. No,
Thank
we
you.
have the shortage of the time, so let us move to the next presenter. Okay.
Okay, thank you. The
Thank
next
you.
presenter, thank you, is Ying Xiaolong. Ying Xiaolong, 你好，今天怎么样？我是一个微科多，我在清华大学毕业了。Yo soy Víctor Hidalgo también. I am graduated in Tsinghua University 6 years ago in your department. So nice to see you, the new generation of Tsinghua University students.
Nice to
so
see
Miss Silong, how do you consider the because when you make a numerical simulation, or you did a numerical simulation with the moving mesh and static mesh, you have some phase considerations. Which should be your phase consideration? Because it's very complicated to do a numerical simulation between a moving mesh and a static mesh. Can you explain something, how you resolve the problems? Because we need to understand that part.
Actually, we to analyze the pressure change of the unit under a startup and shutdown conditions, we choose some extreme points of pressure, flow rate, and rotational speed during the turbine shutdown and startup process from one dimensional pipeline calculation, and assume that this data changes uniformly during the process. So we give it a steady state calculation are performed for these extreme points, and we also get the extreme points of the flow, field, pressure, and some other data in the process.
Okay, I understand a little bit. Perhaps after I make another question. And the finished one for me is, what is the turbulence model that you use in your simulation to capture the transient effects? Which was the turbulence model that you use in your simulation? Omega, Key CCT, which turbulence models?
The real pump turbine is in some city in China, and we just created a mesh for that real pump turbine, and then we get the extreme points of the one-dimensional pipe calculation.
Okay, but for example, if you use Key Omega CCT, you have some results. If you have Key Omega Epsilon, you have other results for transient part. So which was the turbulence model that you use? In Chinese said, Nita monita, ni yo kanshema llega so wankada monita. Ni yo shema tonsita susha da fanfata.
模拟的是，
你说你的模拟的这个网咖有什么输出的用了？你明白吗？差不多在模拟的有模拟的在 CFD 的模拟，对吗 ？CFD 的模拟有用这个 Key Epsilon、Key Omega SCT 还是 Key Epsilon 的模拟的？你用什么
K omega.
Q omega CCT. Okay, is the traditional one. Okay, that is no. It's for me. Thank you, Silong Ying. Professor Ahmad, do you have any question?
Zilong. Hello.
Yeah. Hello.
Are you fine? Are you fine?
I'm fine, and you?
Yeah. You see, you consider different transient condition, shutting down the pump, starting the pump. Are you getting me?
Maybe my network is not very good, and can you repeat it?
Okay, no issue. We move to the next presenter.
Thank you very much.
Next presenter, Mr.
Ying.
Yeah.
Yes. Is the final presentation is the 3D simulation?
Yeah.
Perhaps
yes.
You are Li Shuarang.
Yeah, that's correct. Yeah.
Nice.
Hi.
Okay. Hi. Okay. I worked more than 10 years in OpenFont, so that I am very happy to see that some people use OpenFont. In this context, I have one question. Why do you use less? Because you can apply other turbulence model like mixed turbulence model like SAS, scale adaptive simulation. Because let's use a lot of computer, yes, a lot of computer research. And the SAS, perhaps you have some similar research, but this is this one. The final one is, do you use or did you apply parallel simulation to reduce the time of simulation? This is two questions. The first one is, why did you not use a mixed turbulence model? And the second one is, did you use a parallel simulation for that one? This is my.
Okay, like why did I use mixing turbulence model?
Why did you don't test or use mixed turbulence model like SAS, scale adaptive simulation, because you apply less, and you apply less for one reason, but perhaps you can improve it, the time of research or the simulation, using a mixed turbulence model. You consider or you didn't consider?
Okay. Actually, no. Actually, I never consider about the turbulent the mixing model, and yeah, so I will consider that for the future research. And for the parallel processing, yes, we did apply parallel processing to speed up the computational. Yeah.
Yes, this is good because in the parallel simulation you reduce the time, and I'd advise to test scale adaptive simulation. This is a model we propose.
Okay. Yeah,
we validate it. So what should be interesting that other people use using OpenFont now, and you can test and you can give some backup and we can share something. Thank you very much.
I see. Thank you.
Professor Ahmad, is your time.
Yeah, Mr. Lee. Mr. Lee.
Yeah, okay.
Hello, how are you?
Yeah, I'm good. How are you?
Good.
Yeah.
Well, you have analyzed this dam break scenario.
Yeah.
Okay. Now, what was the process of this dam break? I mean, how this boundary condition that was changing with respect to time, whether that was a impulse type or some gradual.
Okay.
You have a channel, right?
Yeah.
In the upstream, you have a storage of the water. You might have put a gate. Okay.
Yeah, that's true. Yes.
Now that gate is suddenly you have opened or gradually you had opened.
Okay, so that is we simulate it as a suddenly open gate. So basically, from t equals to 0, the water is constrained behind the gate, and at the next time instance, the gate is suddenly open, the water start propagating towards the downstream. Yeah.
Your aeration is high near the toe of the surge.
Yes, that's true. Yeah.
Right?
Yes.
Could you explain why so? Why the aeration is more near the toe?
Sure, yeah. So that can be explained by the shear of the velocity, the shear at the surge toe. So like, see the downstream, basically it starts from a no velocity. So it's just still water, but the upstream you have like a surge wave propagating. So there is like a shear between these two near the toe. So or you can call it like a velocity gradient. So that's why it causes a lot of aeration near the toe.
Now you have used this open foam software, right?
Yeah.
What are the governing equation for the aeration process that you had used?
Okay, so for the aeration, yeah, we have a
because there you have a mixture of air and the water, right?
Yes.
Actually, these positive waves, once that positive waves that is collapsing, right? That is entraining the air. And that's why you have the air contents, very high air contents on the frontal face, right?
Yes, yeah. So yeah, we have the.
Would like to know what are the basic equations that you had consider in this open form software for this aeration process analysis?
Sure. So it's a governing equation based on the volume of fluid matter. Is a function of alpha water. So it's a volume fraction of water. So there is a governing equation incorporated with the solver interform itself. So with like advection terms, like a transport equation.
You had considered the two-phase flow.
Two-phase flow, yeah. So one, so for alpha water to be 0, the alpha air will be like 1. So they sum up to 1 like that.
Well, no more question from my end, but any question from the audience?
I think
any question to any question to any presenter?
I think the people is going to leave us. So first, I would like to thank you very much, Professor Hamad. It's very nice to see you again. I suppose 3 years ago in Japan, I see you, I suppose.
Yeah, yes.
Yes, I am sure.
Yes.
And thank you very much for the younger group that organized this symposium and this meeting. Thank you very much. And we are very, how to say it, very grateful to see the people to present something new and some research that we can apply for the industry in science and different topics. This is my speech, Professor Hamad.
Yes, yes. Thank you, Mr. Professor Victor, and thanks to all the presenters and the audience. This was a very nice session. And you see, once we are talking about transient, okay, so something which is very dynamic there, okay, because this we are talking about the unsteady flow, right? And we have seen the, you see, the young presenter who have presented very well, and the contents of this presentation, materials of the presentation, that was wonderful. Of course, due to having some limitation of the space, because this was a poster presentation, okay, they could not share all their results, but they are in a very good direction, okay. And you see, we wish you see, please keep this one up, right, and work hard in your area, okay, and come out with a good paper in the IHR, okay, right? So you see the outcomes that should be in the form of a good research paper in the any journal of the IHR, right? So thank you once again. And here, this is going to be in India is going to be midnight, okay. The host is also from the India, is my student, Dr. Manish Pandey.
Thank you, sir.
and he might be waiting. So thank you, all of you, and see you again.
See you again,
Right.
Professor.
Thank you.
Thank you.
Thank
Thank you
you.
so much.
Thank
Thank
you.
you.
Thank you.
Thank you.
See you in the future.
Thank you, sir.
Hello, everyone. Welcome
Hello.
to the next session. Hello.
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 Hi, Professor Felder.
Eteno. Oh, okay. You're doing the introduction. Hello.
Yeah. Okay. Only few seconds. Welcome, everyone. Good morning, good afternoon, good evening to everyone, depending on the specific site you are. I am Gaetano Crispino, and I'm a component of the organizing committee of the second IAHR Young Professional Online Congress. There is also Emanuele Quaranta.
Hi.
Hi, Emanuele.
Hi.
This is the session Hydraulic Structures, and this session will be chaired by Professor Rita Carvalho from the Civil Engineering Department of University of Coimbra in Portugal, and Professor Stefan Felder from the Water Research Laboratory of University of New South Wales in Sydney. Thank you. Thank Professor Carvalho, thank Professor Felder for accepting our invitation to add this session. And obviously, many thanks to all the speakers, all the authors of this session who will present their poster. I will load, me and Emanuele will load the poster speaker by speaker at the beginning of each presentation. So each author only needs to switch on the camera when his or her round will get and present their own work. Now I spread now the word to the chairs of the session. So please, Professor Carvalho and Professor Felder, the microphone is yours. Thank you.
Thank you, Gaetano, and thank you, Emmanuel, for hosting this session. So I think we are in good hands. And I hope if we've got any technical issues or any other questions, you will be able to help us. Before we start the session, I would like to introduce my co-chair or the second chair, the joint chair, Rita. So Rita will do the chair the roundtable afterwards, and I will do the chairing of the first sessions of the presentations. I hope that all the presenters are here. I tried to check, but I think we've got most of them here. So I hope that we can have a full range of presentations in the topic of hydraulic structures. We've got a wide range of topics today that we want to get through. So all of you will have the chance to present, and then in the roundtable, we will ask questions and provide feedback on your presentations. Okay, let's get started with the first presentation. It's on modeling the structural response of a dam to earthquake-induced dynamic stresses. And I believe that the first presenter is Binyam Sisha.
Yes, that's correct.
Yep, welcome. So if we can load the first poster, please. And you've got about 6 minutes, 5 minutes, so that we get through all the posters, and questions will be asked at the very end.
Perfect. Can I start?
Yes, the floor is yours.
Okay. Thank you for the opportunity provided. My name is Binyam Sisha, and in this collaborative research, a gravity dam's structure response to an earthquake event was modeled. So dams are essential structures for navigation, hydroelectricity, and flood mitigation, but pose a significant threat to downstream communities in the event of an earthquake. Earthquake increase the hydrodynamic pressure and inertial forces acting against the stability of dams. Henceforth, predicting expected deformation and stresses on the dam body to a probable earthquake event is often an integral part of the dam design. But depending on the analysis type chosen, predicted deformation and stresses may vary. So in this regard, choosing a method representative of the actual system is important. So in this investigation, resulted obtained by 3 techniques was compared. The first one was a static model. The second and the third being one-way and two-way FSI models. So in response of a dam to forces of uplift, weight of dam, and hydrostatic pressure can be easily computed using a static model. However, when earthquake-induced hydrodynamic stresses and inertial forces are present, the use of FSI simulations helps gain accurate understanding of the system. In one-way FSI models, only the fluid pressure acting on the structure fluid interface is transferred to the structure solver, whereas in two-way coupled simulation, the displacement of the structure is additionally transferred to the fluid solver, which is expected to increase the accuracy. So with this in mind, the study area was located in Ethiopia. It's Gilgal-Gibe Dam. It's made of reinforced concrete. And so the particular study area where the dam is located is known to have a 20% risk for 7 to 8 Richter scales earthquake, which probably which will occur within the the service period of the dam. So in terms of the model, ANSYS fluent and ANSYS mechanical were used. So the computational domain is presented in figure 1. There you see the red one is for the structural analysis. And during the static analysis, that was the only mesh used, not the fluid part. But for the coupled simulations, both meshes were used. So that the boundary conditions does not influence the results on the dam. So the downstream and upstream boundaries were stretched further from the dam body, as you see, 750 meters downstream and 300 meters upstream. And with respect to grid cells for the dam geometry, about 2 meters were the elements used. In terms of the fluid domain, 1 up to 5 was used, where 1 was close to the dam, and somehow to the downstream section where we expected to have a flow on the spillway, because this also is a 2-phase simulation. So the water level up to the reservoir, to the maximum reservoir water level was water, but above that was air. So the refinement you see below the dam is so as to capture, let's say, the turbulence when the flow dissipates over the spillway, but we didn't see that, not that much important. So in terms of the result, so the results are presented in figure 2. The first one presents the total deformation with the time, and the 3 are presented here. Okay, so in terms of panel A, so the maximum deformation in the dam body predicted by the two-way couple FSI model linearly increased with time, while that predicted by the other models were smaller. And this linear relationship was actually started around 2, which is the time where we have the maximum ground acceleration. So it could be related with this. In terms of the panel B, what is visualized there is the minimum principal stress. So more or less here, we try to see the tensile stress for which RCC dams are not good because they're made of roller compacted concrete and its tensile strength is not that much. So we try to see this as well. And also there are other results which are not presented here, but generally we observed that the forces, the stresses are within the allowable limits. Okay, with that I conclude my findings. So stress predicted by the different models shown different stress time relationships. The stress predicted by the different models were within the safe limits of the dam. The high deformation predicted by the two-way couple FSI model was attributed to its accuracy, but we recommend further investigation on the matter. Okay, so with this, I thank you.
Thank you very much, Biniam. That was a very nice presentation. Yeah, you sticked perfectly to the time allocated. And with this, I would like to remind everybody to please post questions in the Q&A chat that you can find at the bottom of your screen. So please post your questions there and we will cover those in the question and answer session afterwards, in the roundtable afterwards. So with this, I would like to present the next presenter who will present on 3D computation and hydraulic modeling of stepped spillways, variable section for gravity and RCC concrete dams. So I believe the presenter should be Ghidaoui Fabian. I actually haven't seen him, so I hope he's here. Okay. Can you please make yourself known if you're here? Or the second speaker on this paper would be Samuel Astokahuana. Are you here? Okay, if not, let's move on to the next presentation. And this presentation is on the discharge capacity of labyrinth weirs by physical modeling, influence of weir orientation. And the presenter here is Alicia Ross. Are you here, Alicia?
Professor Felder.
In the attendees list.
Yep. Yeah, but I cannot add her as a panelist. I have to ask some time for Alicia because the IAHR secretary should give her the right to participate in the session as a panelist. So we can skip her presentation.
I also can't.
Yeah.
Who was that? Oh, yeah. Okay, good. So we skipped the presentation by Alicia. So you will manage this in the background so that she can present then the poster afterwards. Correct?
Yeah, thank you.
Okay, great. Okay, then I would like to give the microphone to Xiao Yang Shen, who will present on the influence of crest shapes on trapezoidal piano key weir hydraulic performance.
Hi, everyone. I hope you can hear me well.
Yes, great. Floor is yours.
Okay, so thanks for the kind introduction. It's my pleasure to speak here today. And my name is Xiaoyang Shen, and I'm from the University of Federal Armed Forces in Hamburg. My topic today is about piano key weir. So it's an innovative type of nonlinear weirs and has been gaining growing attention in the past 15 to 20 years. Due to its small footprint and efficient hydraulic performance. Numerous studies have been carried out to optimize the planform geometry of piano key weir and in order to maximize its hydraulic efficiency. However, less attention has been paid to the crest shape of this type of hydraulic structure. And most of the previous studies were conducted with piano key weir models only with flat crest. So the question is, would this type of weir be more efficient with other crest shapes, such as half round or quarter round crest? To answer this question, 4 piano key weir models with different crest configurations, as you can see here in the poster, and there are flat crest, half round, and quarter round in up and downstream direction, respectively. They were examined within the present study with focus on discharge capacity and net behavior. And all the physical models were fabricated exactly in the same size via 3D printing technique. So all 4 models are 300 millimeters high with a standard symmetrical planform with a key width ratio equals 1. And only the crest shape differs. And our experiments were conducted in a horizontal flue. Discharge were measured via magnetic inductive flow meter, and flow depth was determined at a distance of 5 times weir height in upstream using point gauge and ultrasonic sensor. All the model runs were reproduced twice in order to minimize human error in the measurement, and final results presents the mean value of our collected data. In addition, as suggested by several authors, our results, only results with a minimum upstream total head of 3 centimeters were included for quantitative data analysis to avoid size scale effects related to surface tension. And that's the vertical line you can see I draw in this second figure. So the second figure in the middle of the poster compares the discharge efficiency of tested models in terms of discharge coefficient. The x-axis presents the relative upstream total head. And it can be seen clearly that the flat crest configuration provides obviously the lowest discharge efficiency, and up to 30% increase in discharge capacity can be achieved if the flat crest was changed to half round crest. Although this efficiency gain decreases with increasing heads, an overall improvement of more than 10% can be expected as long as the relative heads does not exceed 0.5. So furthermore, we can see that both quarter round configurations generally show identical trend and offer up to 15% improvement of discharge efficiency relative to the flat crest configuration. However, minor deviations was observed at very low heads, as you can see here in the figure, which indicates that this quarter round crest in downstream direction might be more sensitive to surface tension relative to another quarter round model. And in addition, we can see here within the range between 0.4 to 0.6 of the x-axis, piano key weir with quarter round crest in downstream direction, that's aligned with the circle marker, deviates unexpectedly from the discharge coefficients of the quarter round upstream configuration. That's aligned with the square marker. And the possible reason could be the different net behavior. The rectangular edge guides the nav trajectory so into this vertical direction and generates air cavity formation downstream of the crest, as shown in the figure in the right. And this increases the flow depth and makes the outflow less efficient. And as the upstream head grows, this effect becomes less significant due to increased turbulent mixing, and the air cavity formation gradually diminishes. So overall, our investigation confirmed that for piano key weirs, significant efficiency gain could be achieved by replacing rectangular weir crest to half round or quarter round crest, and especially at small heads. And depending on the crest shape and upstream total head, different net behavior will be generated that could affect the hydraulic performance of this structure under certain conditions. So yeah, that's my presentation, and thank you for listening.
Great presentation, well done. Thank you. Again, questions please in the Q&A chat at the bottom of your screen. Great, so we come to the next presentation, which is by Lisbeth Alvarez-Meya on microscale hydrodynamic analysis of flow in circular piles with shallow spherical cavities using CFD. Are you there? Lisbeth? Yeah, I think you're muted.
Probably in this presentation there is the video because the speaker cannot be present here, I think.
Okay, so there's a video presentation.
Yeah.
Okay, great. Thank you. Don't have sound.
Hello everyone, I'm Lisbeth Alvarez, a master's student at IAHR from the Autonomous University of the State of Mexico. The study we developed is named Microscale Hydrodynamic Analysis of the Flow in Circular Piles with Shallow Spherical Cavities using CFD. The incorporation of rocks and surfaces in bridge piers has mechanisms for reducing the depth of the scour, requires a comprehensive study of the flow behavior. Application of CFD techniques is ideal for analyzing the hydrodynamics of highly turbulent flows. In this study, CFD was used to evaluate the hydrodynamic behavior of the flow around the pile with a surface finish based on spherical microcavities under a translate simulation scheme BOF. Tetrahedral mesh with a size of 5 mm and to 0.2 mm and has input condition a flow rate of 7 liters per second and flow depth of 0.07 meters. The exit condition was type outlook and the condition type wall in the channel and the pile. BOF model was used in open channel, phase 1 air, phase 2 water, and CC2 for turbulence, step size of 0.05 seconds and number of time steps 500. The results were validated with the physical model experimentally analyzed with the PIV technique, concluding that spherical cavities decrease turbulence energy around of the piles. Characterization of the flow corresponds to the detachment of the vortex structures in the age range of the Reynolds number. Verifying the relevance of the parameters, models, and assumed conditions. The presence of the spherical cavities in the wall of bridge supports constitutes a potential application of rock surfaces in engineering. The results obtained allowed us to propose different configurations of the spherical cavities, seeking to optimize the arrangements for different flow conditions. It's all. Thank you very much for your attention.
Okay, thank you very much, Lisbeth. I can see you are on the panelists stream, so I hope that we can have you for the question and answer session afterwards, but I guess Gaetano and Emmanuel will confirm that. Okay, again, questions please in the Q&A chat at the bottom of your screen. Okay, and we move on to the next presentation by Preet Patel on impact of surge wave fruit number on the transport of microplastics. Very interesting.
Can I share my screen?
Yes, the floor is yours, and share your screen, please.
Thank you. There we go. So I hope you can see my screen.
Yep.
Thank you. So first, I would like to thank IAHR for this opportunity. And so, hello, everyone. I am Preet Patel, master's student in the Department of Civil Engineering, York University, Canada. And my academic advisors are Dr. Magdalena Kroll and Dr. Shoka Karimpour. Today, I'll be presenting my research on the influence of breaking boards on the transport of macroplastics. So since the start of plastic industry, 8.3 billion tons of plastics have been manufactured. And of this, nearly 6.3 billion tons have ended up in landfill and aquatic environment. And as a result, annually, we have 275 million tons of plastic waste being generated. Of this, approximately 12.7 million tons enters the marine environment. And it is estimated that 80% of that originates from land-based sources, while the rest, 20%, comes from marine and offshore activities. The plastic wastes are carried to aquatic and marine environment through various pathways, namely rivers and coastal activities, such as surge waves, tsunami waves, and flood events, and coastal activities, including improper dumping, mismanaged plastic waste, and so on. Now, these two parameters, contributors, namely rivers and coastal activities, play a crucial role in transferring plastic waste from inland sources to marine environment. And to investigate this transfer process of plastic debris, solid micro-sized plastic balls with various densities were introduced into a surge wave. So moving on to the methodology. Transport of foreign debris and natural sediment are influenced by the transient turbulent bore. And to explore this, a hydraulic flume was used to generate a breaking bore, a surge wave, with a surge wave for a number of 1.7 and 2.3. And solid micro-sized polypropylene and acrylic plastic balls with a diameter of 2.54 centimeters, 1.91 and 1.11 centimeters were introduced into the surge wave. Now, since this transport occurred within a few seconds, a high frame rate camera was utilized to capture the macroplastics involvement in the surge wave, along with acoustic displacement sensors to record upstream and downstream water depth. Now, upstream and downstream are respective. So before the surge wave is referred to as upstream, and behind the surge wave is referred as downstream. Data obtained from the experiments were processed in post-processing and were then analyzed using an open source particle tracking velocimetry program, Tracker, which was developed by the US Department of Energy. And so moving on to the results. Initial observations from the experiment showed that polypropylene balls were transported vertically and were engaged in the roller at the forefront, while the acrylic balls had no vertical transport at low surge or forward number. Now, the entrainment of these polypropylene balls increased as the surge wave forward number increased, and the polypropylene balls were transported further upstream. So that means further upstream with the surge wave. In addition, the transport towards the upstream direction increased as the polypropylene ball size decreased. So that's so when we tested 2.54 centimeters and 1.11 centimeters, when we compared them, 1.11 centimeter ball, a smaller ball, had a higher transport in the upstream direction. Now, although the acrylic ball had no vertical motion, the horizontal transport of acrylic ball was highly influenced by the transient recirculation behind the surge wave. And the horizontal transport was more evident once again as the acrylic ball size decreased. And so these are initial observations, and for polypropylene ball size, one thing was noted that the strength of the roller had significant impact on the transfer mechanism, and for acrylic ball, the transient recirculation had significant impact on the transport mechanism. Now, the transient recirculation of breaking board, again, as mentioned, recirculation zone and the roller strength played a crucial role in the transport of polypropylene and acrylic balls. Now, to further understand this transport process, future experiments will be carried out, and they're being carried out as of now, and in which we consider a wide range of surge wave forward number. So that is surge wave forward number of 1.4 to as high as 3.6. And along with that, we consider one more polymer, which is high density polyethylene, and with three different ball sizes of 2.54, 1.91, and 1.11 centimeters. And thank you so much for listening.
Thank you very much, Preet. Very nice presentation. again, questions please in the Q&A session panel at the bottom of your screen. Okay, the next presenter is here as well. I see as well that Alicia has been added to the panelists directory now. I suggest we continue now with Fluvial Al-Sabari first, and then Alicia, I come back to you after the next presentation. So the next presenter is Fluvial Al-Sabari, who will present on large eddy simulation of the free surface impact on the wake of the circular cylinder.
Yes, hello everyone. It is my pleasure to present in front of you. My name is Fawaz. I'm from Saudi Arabia, and I'm currently a PhD student at Cardiff University. So actually my presented work is large eddy simulation of a single horizontal cylinder with considering the impact of a free surface on the hydrodynamics of the cylinder. Actually, the significance of this research is due to the free surface motion arise in many engineering applications. In our study, the two-phase simulations, we simulated a turbulent flow with the Reynolds number at 13,000 and 4 Froude numbers based on the submergence depth ranging from low Froude number to high Froude number. We used to perform the large eddy simulation, the in-house code Hydro 3D to solve Navier-Stokes equations and the level set method phi distance function to predict the free surface. In terms of our results, you can see in figure 1 the profiles of water surface elevation. For the case with Froude number 0.31, the experiment and large eddy simulation agree relatively well, with less underestimated by the large eddy simulation for the drop behind the cylinder. We can see as well as the Froude number increases, the water level upstream of the cylinder increases, and the drop behind the cylinder also enhances. The case of Froude number 0.26, which is the highest submergence steps considered in this study, we can see the drop behind the cylinder is mostly negligible. And in terms of how the deformation in the free surface influences the cylinder wake, we show in figure 2 the span-wise vorticity at different Froude numbers. It can be seen that at low Froude number, at Froude number of 0.26, the free surface behaves remarkably like a rigid surface with the little or no large scale surface deformation being observed. At larger Froude number, the surface curvature was more pronounced, which at higher Froude number, for example, at Froude number 0.53, it tends to create a flux of positive vorticity into the flow. Also, the instabilities by the free surface breaking was seen to interact with the von Karman vortices from the cylinder wake, with changing the wake dynamics downstream the cylinder. For the shallowest case considered here, Froude number 0.53, we have seen the von Karman street is highly constrained by the free surface proximity. Other cylinder hydrodynamics were also calculated in this study, like the drag force. We see in the flow in the figure here, we include the result as well from free shear layer rigid surface that with the black points, and we can see in general the mean drag coefficient increases with the increasing Froude number, and also the differences with and without considering the free surface deformation also increases. To conclude from the results showing here and from other results we have, the result emphasize or evidence the need for resolving the free surface layer to fully capture the wake dynamics and for more accurate forces result, especially for Froude number larger than 0.31 or 0.3. Thank you.
Thank you very much, Fawaz, for this presentation. I would like to now go to Alicia who we missed earlier, to give her the chance to present on discharge capacity of Labyrinth weirs by physical modeling, influence of weir orientation. Alicia, is it working this time for you? Oh, you've got, yeah, thank you. And then we do Christian afterwards. Okay, Alicia, you're on mute at the moment. Can you unmute your microphone, Alicia?
Hello, everybody.
Great, it works. All good. The floor is yours.
Hello, everybody. My name is Alicia from Universidad Politécnica de Cartagena, and I'm going to expose the research that has by title Discharge Capacity of Labyrinth weirs by Physical Modeling, Influence of Weir Orientation. The Labyrinth weir is usually postulated as an interesting solution to increase the capacity to release floods from dams and weirs, mitigating some negative effects triggered by climate change. The readjustment in the configuration of the discharge line allows to regulate the water level and increase the discharge capacity. Despite these advantages, their hydraulic behavior is markedly three-dimensional. With this way, mostly of the design procedure has been experimental. The main focus of this research was to evaluate the orientation influence of Labyrinth weirs through the determination of the discharge coefficients. For this purpose, two steel plate Labyrinth weirs of different angles, 15 and 35 degrees, in normal and in invert orientation, were tested in a hydrodynamic channels. The experimental campaign was carried out in a hydrodynamic channel with an effective measurement length of 12.5 meters and a cross section of 0.3 times 0.45 square meters. The channel operates on a recirculation system with a maximum flow rate of 14 liters per second. The longitudinal slope is variable between -1 divided by 200 and 1 divided by 40. A digital readout lengthometer has been used to measure the depth of the water with resolution of 0.01 millimeters. The geometry of the tested spillways consists of a single cycle steel plate Labyrinth with a thickness of 5 millimeters and width of 0.3 meters. The height of the weir is 0.103 meters, and the size of the crest is rounded with a radius of 2.5 millimeters. The total crest length is 1.099 meters for a sidewall angles of 15 degrees and 0.472 meters for alpha equal to 35 degrees. These spill geometries were tested in both normal and invert orientation, with the channels in horizontal position, and were installed on a raised platform to avoid submerged condition due to the limitation in the outlet capacity of the channels. That, like we can see in figure 1. Here we have two Labyrinth weirs with sidewall angles of 35 and 15 degrees in normal orientation, with the bears facing to the downstream side, in invert orientation with the pegs facing to upstream side. In figure 3 is a skin of the top view of the Labyrinth weir, where the different variables have been represented, like the thickness, the flow orientation in normal, the flow direction in normal orientation, the sidewall angles, and the width of the channel. Following with the results, this graph represents the discharge coefficient versus the relative height for 15 and 35 degrees layering weirs. The points are the values obtained in these studies in normal orientation, yellow points, and in invert orientation, blue points. And the lines are the result of time by crosstown and chalice with their weights in normal orientation. As we can see, the influence of the weir orientation is not significant. The results are similar to those obtained by crosstown and chalice for quarter round layering weirs when the relative head is greater than 0.35. And they are also similar to those obtained for half round layering weirs when the relative head is greater than 0.5. The results are similar even when for a smaller relative heat between 0.2 and 0.3 for 15 degrees layering weirs. The large difference obtained for small to moderate heads may be explained by different weir geometry, scale effects, and erosion conditions. In conclusion, the determination of the discharge coefficient continues to be the topic of the study by various research, normally by physical modeling. And in this study, the influence of the weir orientation on the 50 and 35 degrees layering weirs was found to be small, in line with that obtained in other studies. Thank you for your attention.
Thank you very much, Alicia. Glad that it worked, that you could be added and that you could present. Okay, questions after our final speaker. And our final speaker is Christian Kröner, who will present on failure of a penstock as an example of an extreme load case and countermeasure to reduce the impact of such load case.
Okay, thank you very much for the introduction. First of all, I would like to apologize for my voice. Unfortunately, I've caught a cold and I hope my voice is loud and clear enough to be understood. I would like to talk about a holistic approach to identify a potential risk of a broken penstock in high-head hydropower plant and how this risk can be reduced or even suppressed. I would like to divide my presentation in two parts. The first part will relate to the load case as such, and the second part will relate to a potential countermeasure. To the first part, up to now, it is commonly known to consider a plurality of different load cases in the planning stage of a hydropower plant. However, a break of a penstock is not commonly considered in such planning stage. Therefore, we would like to analyze such load case as an extreme load case and determine the impact of such load case. The impact can be considered as a flow rate increase of water discharge out of a broken penstock. Therefore, we created a 1D numerical model using Wanda Liquid version 4.2 by Deltares to determine such a flow rate increase. However, in Wanda, there is no boundary condition available to simulate such break of the penstock. Therefore, we have to use the available boundary conditions. For simplification, we assumed that the break of the penstock will occur immediately and completely. Therefore, the boundary condition can be considered as being a local pressure drop within the waterway. Therefore, we can take an available downstream boundary condition of Wanda and reduce the head suddenly in a specific time to simulate a break at the position. As you can see in figure 1 of the poster, we examined some further boundary conditions, but the one shown in figure B shows the best results. That is, we have a defined edge height and two valves which are controlled so as to simulate the break of the penstock. In figure 5, you see a comparison of the results of the model with Bernoulli's equation. That's the two columns on the right of figure 5, and one can see that they correspond to each other. However, the flow rate limiting influence of cavitation is not considered up to now. In Wanda, there is a cavitation module which aborts the simulation in case the vapor pressure is exceeded somewhere within the system, and therefore it is expected that the result is too low, as can be seen on the left column in figure 5, the 216%. Therefore, we created an adapted model within Wanda with a monitoring module, which monitors the whole system with respect to the pressure. And in case somewhere within the system the pressure drops below the vapor pressure, the outflow boundary condition is automatically adapted so as to reduce the discharge of the water. Accordingly, we assumed to simulate the discharge limiting impact of cavitation. In order to prove this assumption, a small-scale physical model was created in the laboratory of the University of Innsbruck, as can be seen in figure 2, which was adapted to simulate the break by controlling an outflow valve. Then, in figure 5, the comparison between the small-scale result, the results of the small-scale model and the individual adapted Wanda model nearly exactly correspond to each other, which are the red and the light purple columns. In the next step, I will come to the second part, which considers a possible countermeasure, which is a submerged wall, which can be placed within the waterway to hold back water from flowing out of a broken penstock. In figure 3, a numerical model is shown in which the submerged wall is included. And then we had the opportunity to implement such a submerged wall in a real hydropower plant, which is depicted in figure 4. As a result, the numerical simulation results are in a good range with respect to the measurements conducted in the real implemented submerged wall. However, there are some measurement deficits in the real world implementation of the world, such that in a future approach we try to implement further measurement points to get better correspondence of the real world implementation and the 3D numerical simulation. That's from my side. Thank you.
Thank you very much. Great presentation. So we had a number of really interesting presentations. We were missing one presentation, the second one. Did the presenter turn up in the meantime? Emmanuel Gatano, do you know if the missing speaker? Okay, so the missing speaker didn't turn up. That's okay. So we had a nice range of presentations, and I would like to thank all presenters. You did really well. So it was a great round of presentations. And yeah, we've got now plenty of time because all of you stick to the allocated time. So we've got plenty of time in the round table now to discuss, ask questions, and provide important feedback to your presentations. And with this, I would like to hand over to Rita, who will guide us through the roundtable discussion.
Okay, thank you, Stefan. Thank you all the presenters. We had a very different presentation from dams, from piano keys, labyrinths, some pillar surface, some surge waves and their influence in macroplastic transport. Penstocks also wake from cylinders, so we have a lot of different application and different cases. We had a lot of questions. Thank you for the participants that have did a lot of questions that have some already answered, but there are still some questions that are not answered. So we have some question just to do a resume from what kind of elements, of type of elements to them enhances that was used, and Biniam had already answered that he didn't use the solid 45, but it could be also considered in this part. Also, we have some question about the boundary condition used for this presentation, and Biniam had already answered as well, and saying that the lateral boundary upstream of the dam was a velocity inlet, and a small velocity representative of reservoir flow was considered. A pressure outlet was considered for the dam downstream lateral boundary, and from the boundary which fits the dam body, no slip was considered. Okay. Is there any more question about Biniam presentation?
Yes, I have one question for him. I have read in his poster that he wrote that the stresses were within the safe limits. Can you give us some details about these safe limits? How were quantified, and which was the source or the regulatory source of these safe limits? They were originated from the specific country law restrictions, or they were derived from standards, from international standards?
Thank you for the question. Since the dam is already constructed, I had access for the design document. And in the design document, they actually did this similar investigation, but not considering FSI, but rather they did a transient structural analysis. And on the document, they have detailed, in a sense, they have given, for example, the ultimate tensile strength of the RCC concrete, which is about 5 megapascal. And the comprehensive strength was given to be about 20 megapascal. Of course, the different section, so this is an average value because the different section of the dam has different strengths. So when I say they were safe, especially, so with respect to, of course, the fear often with earthquakes is that the stress associated with the tensile strengths. And in my analysis, the tensile strengths were all less than this. So that's why I said they were with the safe limit. It was in terms of the tensile strengths.
Okay, thank you.
You're welcome.
Okay, thank you. Is there any more question for Biniam?
I'm actually wondering, Biniam, so is there an effect of if your reservoir is full or if it's empty? Is there an effect on your earthquake safety?
Yes, there should be, in a sense. Actually, the stress becomes much amplified when the reservoir is full, because somehow, of course, again, it depends upon which direction the earthquake is propagating. But in the design, So, so often two analyses are made. So one is with the reservoir full condition and when the reservoir is empty. And when the reservoir is empty, if the earthquake propagates, for example, toward the reservoir, then it could actually it would increase the overturning moment. So, but since my interest was to see the hydrodynamic, so to see if considering the extra pressure due to the hydrodynamic loads would provide, let's say, would increase the stresses I mentioned earlier. So our focus was on a condition where the reservoir is full. But I also did an investigation with an empty reservoir. But of course, here we will not talk about the hydrodynamic loads.
Okay, thank you.
Okay.
Okay. Thank you. Is there any more question to Binian? Okay, thank you. Maybe we can have more after. Let's see about the second presentation we had from Xiangyang, piano key. So we have some question about the discharge coefficient and about the parameters that were used for dimension analysis. And Xiangyang had already answered that calculate the discharge coefficient as a function of the total developed length using the Pauline formula. Is there any question for Xiangyang? There were also some question about the shape of the crested, and he answered that he did, as he said in the with the 3D printer, that they printer different crests for doing the comparison.
Yep, correct.
I've got questions if nobody wants to jump in, but please, anybody else? Yeah, the floor is for everybody to ask questions. So you mentioned scale effects, and you mentioned that you minimized this by, I think you had 3 centimeter overflow to minimize surface tension effects.
Correct.
But are there any other effects where scaling could be an issue? Because you've got a small scale model. Are there any Reynolds effects? Are there any other effects from, for example, the material or the scaling, how you scale it between your model and the later probably concrete structure?
Actually, definitely, because we used our 3D printer with a resolution of 0.2 millimeters for our model. And we also have tested like different models with a rougher surface, like with 0.4 or even 0.8 millimeters a surface. And there will be actually some air enchainment issues for these models. And I would say, like for concrete weirs where the surface is relatively smooth, and there would be some difference between model and prototype. That is possible, actually.
So are you studying this phenomenon or these observations in more detail? Because, I mean, having a follow-on question is like, what is the practical recommendation? Because if you want to bring that to the real world, how do you make that translation then?
We have actually tested some models, like with different surface roughness. And for 3D printers, it's actually not that a big deal, because we tested like 0.4 millimeters surface. And in the results, what we see as our data, it makes, I would say, nearly no difference. But like for the nap trajectory, if the air enchainment, there is some difference. But if we talk about our data, the I would say the difference is less than 2%. That we have done some experiments for this.
But if you say like the NAP is different, so how would this potentially affect then your prototype? I mean, this is always, it's probably not a comment particular to you, but whenever we do small scale physical modeling and we have the purpose to do that later in the real world, we obviously need to consider how this will operate. So this is very interesting. If you say like small changes in your roughness change your NAP. So what would be a recommendation for a practitioner? Is there something they need to be aware of or something they need to be concerned about? What would you recommend?
I would say in the reality, if we're normally building with these concrete weirs where the surface are relatively smooth. So we actually don't have like these issues. These issues arise, especially when we have some rough material. If the surface is not like that smooth, then we have issues. So I don't think that will be a big problem if we are building with concrete.
Okay, thank you.
Okay, so it seems like the third presentation that we had a lot of different surface with some cavities that really had some influence on the flow, in spite of being a very different phenomena. I think that we don't have here the presenter Lisbeth because he presented as a video. I don't know if she could answer, but there is no question at the moment for that presentation as well.
Sorry, Professor Carvalho. I have one small question for Xiaoyang before skipping to the next presenter.
Okay.
Maybe he already specified this issue, but I got my connection lost for a few seconds. Have you specified the resolution of the 3D printing? Which was the accuracy, the resolution of this method when the model was fabricated?
Yeah, we have actually
we talked about that.
We tested like 3 different resolutions. 0.2 millimeters, 0.4 and 0.8. And for data analysis, it does not make that much difference.
Okay. Oh, sorry for the repeating question.
No problem.
Thank you, Xiaoyang.
Okay, so we don't have for the third presentation any question. And I don't know if Lisbeth could also answer. So we keep for the, we have a question here for the software used. Okay. So about the fourth presentation, that is the paper number 100 about the surge wave from fruit number. We have here, sorry, we have here some questions about the order of Navier-Stokes equation. And we have already answered that he used fifth order Ueno for convective terms. I don't know if there is any more question about that presentation that we have for Fawaz. Let me see, okay.
I'm actually wondering about the practical application again. I mean, just as a comment again, like more bigger picture comment. So we are all engineers, so we want to do things that make the world better, and in the water space, that's in particular important. So I'm just wondering. So that's a question I could ask also to other presenters, but to Fawaz. So what's actually the practical significance of the circular cylinder more generally, and then your particular study itself?
Actually for the circular cylinder, it is used in many engineering applications, such as cavitation, boiling, bubbly flows, hydrodynamics, open channels, rivers, and in our case, we use it for the case of natural flood management practices. for it is acne to the tree branches. So we use now just one single cylinder, and in the future we are going to use different horizontal cylinders and different arrangements and different gap between them, trying to see how is the wake behind these arrangements with the cylinders.
So they're simulating trees. So it's
Yes.
basically like trees exposed to water.
Yes.
So like mangroves or other types of trees.
Exactly, as it's used for natural flood management.
Okay, so it's more like a nature-based solution approach, and you want to understand the fundamentals of this flow.
Exactly.
Okay, that's really important to understand, because that's a really important problem you're addressing. So it's probably worthwhile always to add that at the beginning, so that people understand, like, all right, that's where it's coming from. So anyway, that's just a comment. Yeah.
And you consider just one cylinder fixed, and did you try with several ones?
This is what are we going to do next. So currently we are doing just one single cylinder and trying to see how the free surface proximity affect the wake behind the cylinder and the wake dynamics with their interaction with the free surface. So next in the near future, we are going to use different arrangements of the horizontal.
So you
cylinders.
analyze different position of the cylinder near the surface and far away, and you will consider as well several cylinders?
Yes.
Okay. You talk about some porosity models in the paper. Is how you mean here some porosity models?
I mean like the gap between the horizontal cylinder that we are going to do next. We are going to consider what the change on the cylinder wake if we change the gap between these horizontal cylinders.
Okay, so we'll expect from near future to have such results that will be very interesting. Thank you. Is there any more question for us?
Hello.
Okay.
I was trying to write the question in the chat, but it's because I can't access the Q&A. But anyway, are you going to investigate fluid structure interaction, since a tree probably will move, and that again has an effect on the flow and on the riverbed most probably?
Actually, we are dealing with fixed cylinders, and we are using the immersed boundary method for that, with non-slip cylinder. Yeah, so we are not working on moving trees. Maybe in the near future, if we finish area with the fixed cylinder, we are going to consider that as well.
Thank you.
Okay, thank you. Is there any more question for Fawaz? Okay, so we have here some question for Alicia as well. Let me see, because this is very good. Okay.
No, she's not anymore in
she's not anymore,
no, in the session.
Okay, because there was a question that is not was not answered. Okay. So we have. Let me see. We have. We didn't talk about the presentation from Preet, surge waves, the influence of fruit numbers. And we also had the penstock presentation. I don't know. I didn't see any question for that. Okay, I was just skipping on that, but maybe there is some question to do. about the failure of the penstock. Is there any question?
Yes, if I may ask a question to Christian Kroner. If he thinks that monitoring and digitalization would help in preventing penstock failure.
In general, I would agree, but in my specific research, this did not play any role because I used the digitalization only for monitoring purposes and not for preventing anything.
Okay.
I've got also a question. So you mentioned, and this is really great that you're doing it. So real world measurements, and you mentioned something about challenges, and I can imagine that this is not easy. So how do you do those measurements, or how do you attempt to do those measurements?
In the particular case where we implemented the submerged wall, we had only one pair of differential pressure sensors. One of them was positioned upstream of the wall and another one was positioned downstream of the wall. However, the whole location is hard to access, and therefore it was not really possible to add further pressure sensors. And furthermore, the configuration of the transition of the water gallery to the penstock was quite with steps and edges and recesses and so on, and therefore there are needed a plurality of further sensors to get all these informations.
Are you planning to install these?
We would like so, but the operator is quite sensitive for such an approach because he had to stop his electricity production, and as you can imagine, this is not in his favor. Therefore, we hope so that we can once more access the tunnel, and furthermore, the tunnel has to be emptied first to place the sensors in an appropriate manner. However, we do not know if this is possible when it is not empty. Yes, we will see. We're trying to get some further measurements.
Great. And to follow up on this, so how important are these measurements for validation? In your case, you've got a small scale model, and then you've got a CFD model. So do you think like these measurements are needed or for results, conclusions?
There is one specific aspect which is not clear to us, which is not completely clear to us. That is the variation of the loss coefficient. That is, over time, the loss coefficient varies very much. And this could be monitored in the physical small scale model and in the 3D numerical model as well. That is one good point, that in both models this could be monitored. It would be nice to have a third measurement like this real world implementation to verify this. We could we correlated the variation with the pressure within the search tank, but cannot found any specific relations between these two variations. And this is ongoing search object.
Well, great. Good luck with that. Would be really good data.
Okay, thank you. So we still have some minutes. I would like to ask again if there is any question for Preet about impact of surge wave flood numbers. I have a question because this is also a very interesting presentation, and I would like to know some more details about the methodology with some properties of the camera, and if it is very difficult to distinguish the ball with the surge. Is Preet already here?
think he left.
Ah, he left. Okay. So
instead, there is now Alicia. She's
okay.
in the no, only for a few seconds. Sorry, she has just disappeared.
Okay, because it's still some question for Alicia that was not answered about the longitudinal slope, but if it's not there. Okay, so
there's Preet. Preet is coming back.
Ah, okay. Hi, Preet.
Hi there.
We was talking about your presentation, and I would like to ask some more details about your methodology and about the request for the camera, and if it is very difficult to distinguish the ball between the search and the I am also interested in this kind of results, and I would like to have the opportunity to have some suggestions.
Right. Yeah. So I was streaming off of YouTube because my internet's weak, so Zoom was popping on and off, so I was listening there. So to answer the question on methodology, yes, the camera that we used was the GoPro camera, and so we needed something that had a high frame rate, and which was obviously affordable. So GoPro camera had a frame rate of 240 frames per second, which was sufficient for us to analyze data. Though we were recording at 120, we didn't need to use the full capacity of the GoPro slow frame rate. So that was that. And now with the distinguishing between the particle and the surge wave. So what happened was at higher Freud numbers, so the limitations of the experiment of our methodology was that at the higher Freud numbers, air entrainment would be significant, and these particles would be hidden behind these air entrainment, specifically the positively buoyant polypropylene and high density polyethylene particles. And so when that happened, that was the limit when the particles were fully covered by the air entrainment. And so we were not able to go beyond that Sergio Freud number. And so we were not able to test any higher Freud numbers. However, for acrylic, because the particle was heavier and it was mainly sitting on the flume bed, it still had a little vertical motion due to the recirculation behind the surge wave, but mainly because it was sitting on the flume bed, we were not limited by higher Freud numbers, so we were able to go as high as even 2.6 and 3. And again, the issue with these positively buoyant particles was that even if we are able to distinguish between the particle and the air entrainment, the more important aspect is the particle tracking velocimetry program able to identify that particle or not, because we have about 20 runs per Freud number per ball and per ball size. And so in total, we have more than 1 million frames. And it is not possible for us to just go in and identify each particle. So even if we are able to identify the particle and then the air entrainment, it all boils down to the capability of the particle tracking velocimetry program that we're using.
Okay, thank you very much. So I noticed there is some talks here in questions. I don't know if anybody wants. We still have some 2 or 3 minutes. Is there any more question about one of the presentation?
I've got another question for Preet. So you use spherical particles, right. But plastics and microplastics in the environment are not necessarily spherical. So how do you make the translation between the two?
Yep. So because what's happening is that, again, it would all boils down to the limitations of our program. And so we did try to use oddly shaped particles to test out these systems, to test out different shapes. But again, if they're not identical, then it has an impact. It is just not possible for us to, for the program to identify these particles, and it makes it very challenging for us to even identify this their projection, their trajectories and their transport mechanism. And so the next step, along with testing wide range of Freud number, is to test different shapes and different bit larger size wouldn't be a problem, but testing different shapes, for example, something of a like, let's say a plate, by plate I mean like a 2D surface, like a 2D plastic piece, or an irregular 3-dimensional shape, and so on. So we're working on improving, along with testing different Freud numbers, improving the particle tracking dosimetry program. So if if we're able to do that, then we should be able to look at different shapes as well.
Great, thank you.
Okay, thanks for the question.
Okay, thank you. We still have 1 minute. I was looking if Alicia is here because we have some questions still not answered for her, but I'm afraid she's not. Okay. So thank you for all the participants. We had a very interesting section with a different presentation, and we thank you all the presenters and all the participants. Thank you. I hope to see you again soon.
Thank you for having
Stefan,
us.
I don't know if you want to add something else.
Yeah, I would also like to thank all the presenters. I had fun. It was a good presentation, and you're all on a good track for your research. And yeah, I'm looking forward to some of the results that are coming out. And I also want to thank Emmanuel and Gaetano for helping with this session. It was very good.
Thank you. Thank you.
Thank you, Professor Carvalho. Thank you, Professor Ferder, for your precious contribution to this session. Thank you very much.
Okay.
See you tomorrow.
So thank you. Bye-bye.
For the last day of the conference.
Okay.
Bye.
Bye-bye.
Bye.
Bye.
Bye-bye.
Thank you, everyone. Thank you. Bye.
Bye.
Bye. Okay. Thank you, Gaetan.